Hello there, and welcome to Nightfall Science. Tonight, we drift beyond Earth's atmosphere to ask whether another intelligence could be quietly listening to our planet right now. Settle into the darkness, let your breathing slow, and imagine Earth glowing like a small blue signal among the stars. Let's begin. At this moment, Earth is not silent. Radar beams rise from the planet's surface. Spacecraft commands travel toward distant machines. Navigation satellites transmit precise timing signals. Television towers, mobile networks, scientific observatories, aircraft systems, and communication antennas release electromagnetic energy into the surrounding sky. Most of these signals were never intended for the stars. They serve people, vehicles, satellites, and instruments close to Earth. Yet a small portion escapes. It passes beyond the atmosphere. It crosses the Moon's orbit. It moves through the outer solar system and continues into interstellar space at the speed of light. Earth has been announcing its technology without planning to do so. The announcement is uneven. It does not travel as one clear message. It is formed from countless transmissions pointing in different directions, operating at different frequencies, and changing from moment to moment. To a distant observer, Earth would not sound like one voice. It would resemble a shifting field of artificial energy surrounding a living planet. The question is whether anyone is listening. There is currently no confirmed evidence that an extraterrestrial civilization has detected Earth, monitored it, or directed a message toward it. No SETI search has verified an extraterrestrial transmission. Earth remains the only world known to contain life, and every possible listener beyond it remains hypothetical. But a lack of evidence does not make the question scientifically empty. Humanity already knows that technology can be detected from a distance. Radio telescopes identify spacecraft millions or billions of kilometers away. Radar measures asteroids. Astronomers examine the atmospheres of planets orbiting other stars. Receivers can distinguish weak patterns hidden beneath natural noise. If another civilization developed instruments based upon the same physics, it could search for signs of Earth, in many of the ways humanity searches for signs of other worlds. It might listen for radio transmissions. It might watch for laser pulses. It could measure the gases in Earth's atmosphere. It may notice artificial chemicals. It might observe the planet crossing the face of the sun. Or it could search for heat, satellites, and other traces of organized energy. These observable traces of technology are called technosignatures. They include deliberate messages, but they also include anything technology changes strongly enough for a distant observer to measure. Radio signals, laser emission, industrial atmospheric compounds, unusual infrared heat, artificial structures, and artifacts are all possible examples. Listening is therefore broader than waiting for words. Someone could be listening to Earth without understanding a single human language. They may never hear music. They may never watch a television program. They may simply detect that one small planet produces radio energy with patterns unlike those normally created by stars, lightning, magnetic fields, or natural atmospheric activity. Artificiality could be recognized before meaning. A narrow transmission might reveal a machine. A repeating radar pulse could reveal measurement or navigation. A signal shifting according to Earth's rotation might reveal that the transmitter is attached to a spinning planet. Several emissions appearing from the same planetary system could reveal a network. The listener may know that technology exists here while knowing almost nothing about the beings who created it. This is similar to how humanity might discover another civilization. The first evidence may not contain a greeting. It may only contain organization. To understand whether Earth can be heard, it helps to imagine the planet from far away. From nearby space, Earth is bright, active, and crowded with transmissions. A receiver near the Moon would encounter communication satellites, radar, television, navigation signals, and countless other emissions. From the outer solar system, those signals become weaker. From another star, most become extremely faint. Radio waves spread as they travel. When energy expands outward, it covers an increasingly large area. The same amount of power becomes distributed across a wider surface. A signal that is strong near Earth can fade into the radio background after traveling only a small fraction of the distance between stars. This is why the common idea of Earth's radio bubble can be misleading. There is an expanding region reached by human transmissions, but the boundary is not one smooth surface. It is formed from overlapping signals of very different strengths. Some are broad and weak, some are narrow and powerful. Some travel in nearly every direction. Others form focused beams that illuminate only a thin path. A civilization may exist inside the region reached by terrestrial radio waves and still detect nothing recognizable. Its receiver may be too small. It may examine the wrong frequency. It may observe at the wrong time. A powerful beam may point away from its planet. The signal may arrive beneath the noise of its own star. Distance determines whether the transmission has arrived. Technology and geometry determine whether it can be noticed. Recent research has attempted to calculate how visible Earth's present technologies would be if an observer possessed instruments comparable to those humanity currently uses. The results suggest that Earth's strongest detectable technosignatures are not ordinary television programs or mobile calls. They are powerful radar transmissions. Under favorable assumptions, emissions like those once produced by the Arecibo planetary radar could be detectable with present-day Earth-like technology from distances reaching thousands of light-years. By contrast, leakage associated with mobile communication would be detectable only from the nearest stellar neighborhood, with one analysis estimating a maximum range of roughly 4 light-years under suitable observing conditions. These numbers do not mean that every civilization within 12,000 light-years has heard Arecibo. Planetary radar is highly directional. The telescope concentrates energy into a beam aimed toward a particular asteroid, planet, or region of space. Only systems lying close to that direction receive the strongest transmission. The beam does not wash evenly across the galaxy. It is more like a narrow lighthouse ray crossing an enormous dark landscape. Most locations remain outside it. A world positioned inside the beam might experience a brief and powerful radio event. The signal could rise above the ordinary background. Its narrow structure and changing frequency might appear technological. Then Earth's rotation, or the radar's movement, carries the beam elsewhere. The listener receives one fragment. If its telescope was not active during those minutes, the event passes without detection. Earth may send thousands of powerful signals while touching only a tiny number of possible receivers. Direction matters as much as distance. The same is true for communication with spacecraft. NASA's Deep Space Network uses powerful antennas to send commands toward missions spread throughout the solar system. These transmissions are focused near the positions of spacecraft and planetary targets, rather than broadcast across the entire sky. Research examining decades of Deep Space Network activity has found that its beams are concentrated strongly near the plane in which the planets orbit. A distant system located close to that plane may have a greater chance of crossing one of these transmissions than a system positioned far above or below it. An observer could therefore learn something from the direction of Earth's radio activity. Repeated beams move toward planets and spacecraft. Their timing follows human exploration. A receiver watching long enough may notice that the transmissions do not point randomly. They gather around the solar system's orbital plane. They follow moving targets. They begin and end according to organized schedules. Even without decoding the content, the pattern could reveal that the source is communicating with machines traveling around its star. The listener might reconstruct parts of the solar system by following our beams. Mars receives many spacecraft commands. The region near the Moon contains growing communication activity. Distant probes receive narrower and more carefully aimed transmissions. The radio pattern would reveal not only Earth but the paths along which its technology is spreading. Someone listening carefully could notice that one planet is beginning to reach beyond itself. Yet even the most powerful Earth signals do not provide a simple map of humanity. A radar pulse contains technical structure, but it may not carry an introduction. A spacecraft command is encoded for a particular machine. Without knowing the system, the listener may recognize artificial modulation while remaining unable to interpret it. The message may appear compressed. It may resemble noise. Error correction, encryption, multiplexing, and digital encoding can make a transmission difficult to understand without prior knowledge. This creates a curious possibility. Another civilization might already possess recordings of Earth signals. It may have confirmed that they are technological, yet it may still be asking what they mean. The listener and the sender could be separated not only by distance, but by incompatible assumptions. Human technology divides information into patterns created for human machines. An unfamiliar intelligence may approach those patterns differently. It may recognize repetition without recognizing language. It could identify images without understanding what the images represent. It might decode measurements while missing emotion, humor, or culture. A television broadcast crossing interstellar space would not arrive as a clear picture waiting to be watched. The receiver would need to identify the carrier frequency, isolate the signal, correct for motion, determine the modulation system, and reconstruct the encoding format. Even then, the transmission may have weakened too much for its content to survive. Recognizing a machine is easier than reconstructing everything the machine says. Earth's strongest introduction may therefore be accidental and incomplete. It may say only, something here organizes energy, something here builds transmitters, something here measures the sky. The planet itself offers another path. Radio technology has existed for only a tiny fraction of Earth's history. Life has been changing the atmosphere for billions of years. Long before the first antenna was built, sunlight passed through air containing oxygen, water vapor, carbon dioxide, methane, and other molecules. A sufficiently capable distant telescope could study those gases. The exact interpretation would depend upon the planet's environment. No single atmospheric substance proves life by itself, but combinations of gases, surface temperature, liquid water, seasonal variation, and planetary context may suggest biological activity. Someone could become interested in Earth before hearing its technology. The planet may have been visible as living long before it became visible as intelligent. This creates a possible sequence. First, an observer discovers the sun. Then it detects Earth moving around it. It measures the planet's size and year. It studies the atmosphere. It notices gases that remain far from simple chemical balance. The world becomes a target for continued observation. Millions of years pass. Then, very recently, narrow radio signals begin appearing. From the observer's perspective, a biologically active planet has developed technology. The transition may be unmistakable. The planet that once revealed only clouds and chemistry now produces radar. A patient listener would witness Earth crossing a threshold. Geometry can make this discovery easier for some observers. From a narrow region of the galaxy, Earth passes directly in front of the Sun once each year. During this transit, the planet blocks a tiny portion of sunlight. The dip repeats every 365 days. A distant astronomer, using the same basic transit method employed by humanity, could determine Earth's orbital period and approximate size. Some sunlight would also pass through the atmosphere, carrying chemical information. Only stars positioned near the correct line of sight can observe this transit, but systems within that region possess a particularly clear method for discovering Earth. This region is known as the Earth Transit Zone. It is not fixed forever. Stars move through the galaxy. Over thousands of years, some enter the zone while others leave. Research using stellar motion has identified nearby systems that have had, or will have, positions from which Earth can be seen crossing the Sun. Some of those systems may also have received human-made radio emissions during the recent technological period. A civilization within this zone would have a reason to place Earth on its observing list. The planet announces its existence through a repeating shadow. Its atmosphere may suggest biology. Its radioactivity may later suggest technology. These different signs would arrive together from the same coordinates. This combination could make Earth more compelling than one unexplained radio signal. A listener would know where the transmission originates. It could connect the radio source to a rocky planet moving through a temperate orbit. Earth would not be an anonymous burst in the sky. It would be a world. But the word now becomes complicated across interstellar space. No distant observer sees Earth exactly as it exists at this moment. Light and radio require time to travel. An observer 4 light-years away receives Earth as it appeared roughly 4 years earlier. Someone 50 light-years away observes the mid-90s. Someone 100 light-years away sees Earth around 9. At 1,000 light-years, the modern technological planet has not yet arrived. The observer sees Earth during the early 11th century. Cities exist. Human civilization is active. But radio, radar, satellites, aircraft, and electric lighting remain far in the future of the light reaching that location. This means there is no single Earth being watched across the galaxy. Every distance receives a different chapter. Nearby stars can receive recent technology. More distant stars receive older radio history. Beyond the expanding reach of those transmissions, observers can only study earlier Earth through reflected sunlight and atmospheric chemistry. The galaxy contains many versions of this planet at once. To one system, Earth is a world of early radio. To another, it is a world before industry. To another, it is a planet inhabited by ancient humans. Farther away, dinosaurs still move across its continents. At greater distances, complex life has not yet appeared. Earth's history expands outward as layered light. A listener does not choose which era it receives. Distance chooses. If another civilization is monitoring Earth from a nearby star right now, it is monitoring Earth's recent past. Its instruments may currently be receiving radar transmitted several years ago. It may be observing weather systems that have already dissolved. It could be studying cities that have already changed. The humans who produced a particular signal may have moved, aged, or disappeared before the signal reaches the receiver. Interstellar observation is a form of archaeology performed with light. The same delay applies in reverse. Suppose a listener around a star 50 light-years away detects Earth's technology and immediately sends a reply. The reply requires another 50 years to reach us. From Earth's perspective, 100 years separate the original emission from the response. The listener may have answered promptly. Humanity experiences a century of silence. A civilization 100 light-years away could only now be receiving Earth's earliest recognizable radio era. Even an immediate response would arrive around the year 212. Silence today cannot reveal whether such an answer has already begun its journey. The message may be moving toward Earth while remaining decades away. The phrase "is someone listening right now" therefore contains two different moments. There is Earth's present, and there is the listener's present. They cannot share the same instant through ordinary electromagnetic communication. Each sees the other through delay. A civilization observing a 4-year-old Earth may be acting in its own present, but humanity will not learn what it does until its response completes the return journey. The conversation unfolds between historical versions of both worlds. This delay could encourage passive observation. A distant society may listen for centuries before sending anything. It may gather Earth's radio emissions and compare them over time. The first transmissions appear simple. Later ones become digital. Radar grows more powerful. Satellites multiply. Communication shifts toward narrower beams and cables, reducing some forms of leakage while increasing others. The listener watches technology change. It may infer conflict, cooperation, exploration, and industrial growth through patterns of energy. It could learn that transmitters appear on moving objects around the planet. It may detect missions traveling toward other worlds. Humanity's technological history becomes a long, faint signal. Why would another civilization choose to listen? Curiosity offers one answer. Human astronomers search for life without knowing whether it exists. They observe thousands of stars because the question itself has value. Another intelligence may behave similarly. It could survey nearby planetary systems automatically. Large receiver arrays might monitor millions of frequencies. Computers could separate natural radio events from artificial candidates. Earth may enter a catalog. A machine notes the planet's oxygen-rich atmosphere. Later, it detects radioactivity. The system increases observing time. No individual being needs to sit beside the receiver. The listening could be automated. A civilization may operate telescopes that continue searching for generations. The observer might not be biological. It could be an artificial intelligence built to survey stars. It may maintain instruments long after its creators stop participating directly. A listening network could function like a lighthouse in reverse. Instead of sending continuously, it waits for signs that another world has become technological. When radar appears, it records. When a planet begins communicating with spacecraft, it classifies the system. When the evidence becomes strong enough, it may decide whether to answer. This idea remains speculative. There is no evidence that such a network exists. But it follows from technologies humanity is already beginning to develop. The Allen Telescope Array and other radio facilities scan the sky for narrowband signals that may indicate technology. Automated systems process enormous datasets and reject terrestrial interference. Another civilization could use comparable methods with greater sensitivity, longer observing histories, or much larger instruments. A larger receiver changes what can be heard. Radio astronomy depends partly upon collecting area. A broader array gathers more energy. Longer observation can also help. A faint continuous signal may become detectable when measurements are combined over time. Better computing can search more frequencies and drift rates. A civilization only modestly more advanced than humanity may hear technosignatures that humanity would struggle to detect from the same distance. The estimates describing Earth's visibility with present-day Earth instruments are therefore not absolute limits. They are comparisons using one technological level. A listener with a collecting array spread across a moon, planet, or swarm of spacecraft could reach farther. It might detect weaker emissions. It could separate Earth from the Sun more precisely. It may recognize individual classes of transmitter. At the same time, Greater technology does not guarantee interest. A receiver must still point toward the solar system. Its search software must still consider our signal type worth preserving. The civilization may use communication methods so different that terrestrial radio appears primitive or irrelevant. It might not monitor the frequencies Earth uses. Its instruments could focus upon planets around different kinds of stars. It may not exist during the period when Earth is most detectable. Capability, attention, and timing must overlap. This makes listening a rare alignment of many conditions. A technological civilization must exist. It must be close enough or possess sufficiently powerful instruments. Its receivers must observe the sun. The correct frequencies must be examined. The observation must occur while Earth emits something detectable. The signal must be separated from natural and local noise. Then its artificial nature must be recognized. Any one missing condition preserves silence. Earth can be inhabited, technological, and broadcasting while remaining unnoticed. The same lesson applies to humanity's searches. A lack of detection does not show that no one is transmitting anywhere. It shows that nothing confirmed has appeared within the small portions of direction, frequency, time, and sensitivity examined so far. The listener and the sender may repeatedly miss one another. Earth sends radar toward an asteroid. A distant receiver looks 1 month later. An alien beacon crosses the solar system. Human telescopes observe another star. Two civilizations can be active beneath the same galactic sky without their narrow beams ever meeting. Perhaps this is happening now. Somewhere around a nearby star, an instrument may be pointed toward the sun. It may be collecting the radio history of Earth. The signal reaching it could contain radar, satellite transmissions, or the leakage of ordinary communication. Software may be examining the patterns. The planet may already be classified as technological, or perhaps every nearby telescope, if any exist, points elsewhere. Perhaps Earth's emissions have crossed empty systems. Perhaps the nearest listener lies beyond the distance our technology has reached. Every possibility produces the same experience here: silence. There is no way to look at silence alone and determine its cause. The question becomes testable only through continued observation. Humanity can search nearby stars for signals that might be directed toward Earth. It can study systems located in the Earth transit zone. It can examine whether unusual transmissions repeat when Earth crosses particular orbital positions. It can search archival data for signals overlooked by earlier methods. It can also ask what Earth looks like from the outside. By understanding our own technosignatures, researchers learn which nearby systems would be most likely to detect us. These systems may become especially interesting SETI targets. A star positioned to observe Earth's transit already possesses a natural reason to notice the planet. A world lying near the direction of powerful radar or spacecraft transmissions may have received unusually strong evidence. A civilization there might choose to respond along the same path. The search can become reciprocal. Which stars can see us? Which transmissions have passed near them? When did those signals arrive? When could a reply return? The night sky can be organized not only by distance, but by communication opportunity. Each star represents a different timeline. For some, Earth's radio age has not begun. For others, the first signals have arrived. A few nearby systems are already receiving emissions from the 21st century. If anyone lives there and possesses suitable instruments, the listening could be happening now. But the strongest signals are not the ones most people imagine. The radio traces of daily life fade quickly. Powerful radar and directed communication travel much farther. Earth's clearest voice may not be entertainment, language, or music. It may be the pulse of a machine measuring an asteroid. A beam created for one practical task may become the first evidence of humanity detected by another world. The recipient may not know what the radar was measuring. It may not know what humans call Earth. It may simply notice that one point beside the sun became briefly, unmistakably artificial. Then the signal ends. The receiver waits. Days pass, years. Perhaps another beam crosses its system. A pattern begins to form. One technological event becomes two become a history. The listener turns more instruments toward the small blue planet. And without anyone on Earth knowing, humanity gains an audience among the stars. Earth's radio history does not travel through space as one expanding message. It travels as layers. Each layer contains a different version of the planet. The newest signals remain close. Older signals have traveled farther. The earliest radio emissions occupy the outermost edge of humanity's technological presence, while the transmissions produced today are still crossing the nearby solar system. From a great distance, these layers resemble the rings inside an ancient tree. Each one marks a different period. A receiver around the nearest stars may encounter modern radar, digital communication, spacecraft commands, and satellite navigation. A listener farther away may receive earlier analog broadcasts. Beyond that region, Earth still appears biologically active, but technologically quiet. The planet's radio age has not reached the entire galaxy. It has reached only a small neighborhood. The Milky Way stretches roughly 100,000 light-years across. Human radio technology has existed for only a little more than a century. Even the oldest signals have traveled across only a tiny fraction of the galactic disk. If the galaxy were imagined as a wide continent, Earth's radio history would still surround its home like a small pool of light around one house. Most stars remain beyond it. Most possible listeners have not received anything made by human technology. The silence from those places tells us nothing about whether someone lives there. Our signals have not arrived. For nearby systems, the situation is different. The light travel delay is short enough that some of Earth's recent technological history may already be reaching them. A planet around a star 4 light-years away receives transmissions produced roughly 4 years earlier. At 6 light-years, the delay is about 6 years. At 10 light-years, the observer sees a technological Earth from approximately a decade ago. These are not ancient versions of humanity. They are recognizable versions of the present era. Satellites already surround the planet. Powerful radar operates. Spacecraft communicate across the solar system. Digital networks dominate much of human communication. A capable observer within this nearest stellar neighborhood would not be waiting for the first weak signs of radio technology. Those signs have already arrived. But arrival does not guarantee detection. A signal must still be strong enough. The receiver must still be sensitive enough. The correct frequencies must still be examined. And the sun's own radioactivity must be separated from the much fainter emissions of the planet beside it. This last challenge is easy to overlook. From another star, the sun and Earth appear extremely close together in the sky. Even though the planet is separated from the star by about 150 million kilometers, the angular distance becomes tiny across interstellar space. A distant radio telescope may collect energy from both within nearly the same beam. The sun produces radio emission naturally. Its atmosphere contains hot plasma. Solar activity generates bursts, storms, and a broad background of radiation. Earth's technological signals must rise above this much larger stellar source. The listener does not simply hear Earth in an otherwise silent sky. It tries to recognize one small artificial pattern beside a noisy star. Human astronomers face the same challenge when studying exoplanets. A planet can be billions of times fainter than its star in visible light. Radio contrast can sometimes be more favorable, especially when the planet produces a narrow technological signal while the star radiates broadly. A narrow radio line may stand out even when its total power is small. The listener can divide the received energy into millions of fine frequency channels. The sun's natural emission spreads across many of them. A transmitter may occupy only one. Within that narrow channel, the artificial line becomes easier to distinguish. This is one reason SETI searches often focus upon narrowband signals. Technology can concentrate energy. Nature usually spreads it more broadly. Earth's communications, however, are not all narrow and simple. Modern systems use complicated forms of modulation. They spread information across ranges of frequencies. They change rapidly. Some are deliberately designed to resist interference or unauthorized reception. To an alien receiver, these signals might not resemble the ideal beacon that human SETI programs often imagine. They may look like structured noise. A listener could detect that the energy is unusual without understanding how to recover the information. This is similar to standing outside a distant city and seeing a faint glow behind clouds. The glow proves activity. It does not reveal the conversations occurring inside each building. The first extraterrestrial conclusion about Earth may therefore be modest. The planet produces artificial radio emission. The details come later. The listener could begin by measuring repetition. Earth rotates once in roughly 24 hours. Transmitters move into and out of view as the planet turns. A distant observer may notice that certain frequencies become stronger and weaker, according to a daily rhythm. The pattern would not be perfectly smooth. Human technology is distributed unevenly. Oceans cover much of the planet. Large populations and radar facilities cluster across continents. The radio brightness may rise when one region rotates toward the observer and decline when it turns away. Over many days, the listener could estimate the length of Earth's rotation. A technological signal would begin revealing the shape of the world carrying it. The yearly orbit creates another pattern. Earth moves around the Sun at nearly 30 kilometers each second. Its motion changes the observed frequency of radio signals through the Doppler effect. During part of the orbit, Earth moves slightly toward the listener. During another part, it moves away. The frequency shifts gently back and forth. This change would repeat every year. A careful observer could distinguish a transmitter located on Earth from one located on the Sun or elsewhere in the solar system. The signal would follow the planet's orbit. It would trace an invisible path around the star. If the observer already knew that a rocky planet occupied that orbit, the connection would become powerful. The radio source and the planet would move together. The listener would no longer be studying one anonymous signal. It would be studying technology attached to a world. Rotation and orbit could also separate Earth's transmissions from human spacecraft. A signal from the Moon follows a different motion. A transmitter near Mars follows the orbit of Mars. A spacecraft traveling outward changes speed and direction in its own way. An advanced observer monitoring the solar system over many years could classify our technology by motion. One group of signals remains bound to Earth. Another circles nearby. Others move between planets. Some gradually travel away from the Sun. Humanity's expansion through the solar system could become visible as a growing set of artificial trajectories. The radio environment would resemble a faint moving diagram. Earth remains the brightest center. Satellites form a nearby cloud. Lunar communication creates another group. Mars missions produce more distant points. Probes in the outer solar system become weak, slowly moving transmitters. A listener could watch this structure develop over decades. It might recognize that the civilization is still early in its expansion. Most activity remains near one planet. Only small machines travel farther. No strong communication network surrounds the outer planets. No artificial structures transform the star's energy. The system contains technology, but not yet on a stellar scale. This conclusion would reveal something about humanity's stage of development. Another civilization may classify worlds according to their observable energy use. A planet with only atmospheric biological signs belongs to one category. A world producing weak radio belongs to another. A system filled with spacecraft and powerful beams belongs to another. A star surrounded by energy collectors would represent something far beyond present Earth. Humanity may appear young, not because another observer knows our history, but because our technology remains concentrated close to its origin. This raises a quiet question. Would a more advanced civilization find Earth interesting? Perhaps technological worlds are rare enough that any detection receives immediate attention. Perhaps many planets produce simple radio leakage, and Earth becomes only one item within a large survey. Perhaps another society searches specifically for civilizations at our stage, because communication may be easier before technologies become too different. Or perhaps it avoids young technological planets entirely. There is no evidence supporting one behavior over another, but the physical information available to a listener can be considered. Earth is not only a radio source, it is a planet with water, clouds, oxygen, changing seasons, and a large moon. Its atmosphere has carried possible signs of biology for an immense span of time. An observer capable of studying it closely may already know that the world is unusual. The sudden appearance of technology would therefore not occur without context. Imagine a distant observatory that has monitored the Sun for thousands of years. At first, Earth appears only as a small rocky planet. Its orbit lies within a region where liquid water can exist. Its atmosphere contains oxygen. Methane appears in smaller amounts. Water vapor moves through the air. Clouds cross the surface. The colors change with seasons and vegetation. None of these signs proves intelligence. Together, they suggest a living planet. Then radio emission begins. The change occurs almost instantly by astronomical standards. For billions of years, the planet produces no obvious artificial transmission. Then, within 1 century, narrow signals appear. Radar beams sweep through space. Objects begin transmitting from orbit. Machines travel toward other planets. From the perspective of a long-lived observing program, Earth changes suddenly. The listener witnesses a biosphere becoming technological. That transition may be more important than the exact content of any one broadcast. The observer does not need to decode a language to understand that something new has happened. Energy is being shaped with precision. Transmitters follow the planet. Artificial objects move around it. The world has begun constructing tools visible from the stars. This moment may be rare. Life could remain microbial for billions of years. Complex organisms may arise without technology. Intelligence may develop without radio. Technological phases may last only briefly before communication becomes quieter, more focused, or transformed into methods difficult to detect. Earth's current radio era may occupy a narrow window. A distant observatory watching during this window is unusually fortunate. It sees the beginning. But Earth's radio brightness is also changing. Early broadcast systems often release substantial energy in broad patterns. Modern communication increasingly uses fiber optic cables, low-power transmitters, tightly controlled frequencies, and directional satellite links. Some types of leakage may become less visible even as the total amount of information exchanged increases. A planet can become more connected while appearing quieter from space. This creates a possible radio shadow. An emerging civilization becomes visible when it first develops powerful broadcasting and radar. Later, it moves toward efficient, narrow, or wired communication. The accidental signal declines. Technology remains. The radio glow fades. A listener who begins observing too late may miss the loud phase. It could study an advanced world that seems quiet. The absence of broad radio leakage would not show that technology disappeared. It might show that technology became efficient. Humanity already provides an example of this direction. Television broadcasting remains important, but much communication now travels through cables, local networks, and narrowly aimed satellite beams. Individual devices use relatively low power. Information is compressed. Transmissions are coordinated to reduce interference. From the surface, the world feels increasingly full of communication. From another star, some forms of that communication may become harder to detect. Radar remains different. A radar transmitter sends a strong signal outward and waits for a faint echo. The target may be an aircraft, asteroid, planet, or patch of planetary surface. Because the returning signal is extremely weak, the outgoing beam can be powerful. This makes radar one of Earth's most visible technological activities. A civilization listening from the correct direction could detect a pulse far more easily than ordinary entertainment broadcasts. But radar beams are narrow. They sweep rather than surround the entire planet. This creates a pattern of rare brightness. Most of the time, Earth may appear faint, then a beam crosses the listener's system. The radio intensity rises sharply. The signal may contain a carefully shaped pulse. A few minutes later, it ends. The receiver faces a decision. Was this one event enough to classify the source as artificial? A natural radio burst can also appear suddenly. The listener would search for narrow structure, modulation, repetition, and motion. It may look for the same event again, but Earth may never aim that radar beam toward the same star. A powerful human technosignature could become another civilization's version of the wow signal. Strong, brief, apparently artificial, never repeated. Somewhere in the nearby galaxy, a telescope may already possess such a record. One unexplained pulse from the direction of the sun. The signal may have been observed years ago. Researchers there may continue returning to our system, waiting for it to happen again. From their perspective, Earth may be only a candidate. They have not confirmed us. This symmetry is striking. Humanity wonders whether unusual signals are artificial. Another civilization could be wondering the same thing about ours. We may already exist inside someone else's archive. A narrow line appeared. It followed a fixed star. It lasted briefly, then silence returned. The distant researchers argue over natural explanations. Perhaps the sun produced it. Perhaps one of their satellites created interference. Perhaps a technological planet circles the star. They schedule more observations. Most nights bring nothing. Earth remains unconfirmed. Even a listener with advanced instruments must follow evidence. One pulse is not enough. It may need several detections. It must show that the signal returns from the same coordinates. It must separate Earth from the sun. It may need to identify the daily and yearly motion. Our technological presence could remain uncertain until a pattern accumulates. This means that the question is not only whether someone is listening, it is whether Earth has said enough. A civilization may be watching the solar system closely, while still lacking confidence that technology exists here. Its telescope may detect weak emissions near the threshold of sensitivity. Some resemble natural noise. Some appear briefly. The world seems promising, but not proven. The listener may wait for a stronger event. Perhaps it waits for Earth to direct a deliberate message toward its star. Humanity has sent several intentional interstellar transmissions. The Arecibo message is the most famous, but other projects have transmitted information toward selected stars. These messages travel as more organized and concentrated beams than ordinary leakage. They are easier to identify as artificial if a receiver lies within their path. But the targets are distant, and the beams illuminate extremely narrow regions. Most nearby systems have never received a deliberate human message. Earth has not announced itself equally to the sky. Some stars lie along paths of strong intentional transmission. Others receive only leakage. Many receive nothing detectable. The choice of targets creates a patchwork of awareness. One civilization might recognize Earth immediately. Another at the same distance but a different direction might remain unaware. The radiosphere is not a sphere of equal knowledge. It resembles a dark globe crossed by thin rays. Some rays are powerful. Most space between them is quiet. As Earth rotates, orbits, and points instruments toward different objects, these rays sweep through new regions. Over centuries, more of the surrounding sky may be touched. The planet gradually paints its technological presence into space, but the paint is faint and incomplete. A listener could improve its chances by studying where Earth's strongest beams are likely to go. Human radar often follows the plane of the solar system. Spacecraft communication points toward planets and probes. A civilization located near the same plane may encounter more transmissions than one positioned above it. It might infer the geometry of the system and monitor the regions where beams repeatedly pass. It could wait near the projected paths of Mars, Jupiter, or distant spacecraft. The observer does not need to listen randomly. It can predict our habits. Humanity uses predictable astronomical geometry. We communicate with Mars when the planet occupies certain positions. We send radar toward asteroids during close approaches. We track spacecraft along known trajectories. A patient observer could learn these rhythms. After identifying one beam, it may know where to look for the next. This begins to resemble true eavesdropping. The listener is not waiting for a message addressed to it. It is reconstructing internal communication within the solar system. Suppose a transmission leaves Earth and travels toward Mars. The beam continues beyond Mars after passing the spacecraft or planet. A distant system positioned close to that line may receive it later. The observer notices that the signal's direction differs slightly from the position of Earth. It points toward a moving object within the solar system. Repeated transmissions follow the object. The listener can infer that Earth is communicating with something near another planet. The content may remain unreadable. The relationship is visible. One transmitter talks. Another machine receives. Technology occupies more than one location. The observer may eventually detect the returning spacecraft signal as well. Earth sends a powerful command. A weaker response comes from Mars. The two transmissions alternate. Their time delay matches the distance between the planets. A distant astronomer could reconstruct the conversation's geometry without understanding a single bit of data. The solar system would reveal itself through timing. The delay between Earth and Mars changes as the planets move. The communication schedule follows that change. The observer may infer orbital sizes, spacecraft locations, and perhaps the speed of light used by the network. Our machines would draw a map through their transmissions. Such detailed eavesdropping would require exceptional sensitivity. Spacecraft transmitters are far weaker than large planetary radar systems. The signals are aimed toward Earth, not outward randomly. Only observers located close to the extension of the beam would receive them strongly. Yet a sufficiently large collecting array could, in principle, detect fainter communication. An advanced listener might possess instruments far beyond anything humanity has built. It could place antennas across a moon. It may combine receivers distributed through its planetary system. A large interferometer could separate the Sun from Earth and perhaps distinguish different transmitters around the planet. The effective telescope might span thousands or millions of kilometers. The listener could observe radioactivity with detail that present human astronomy cannot approach. This possibility should be treated carefully. There is no evidence that such an instrument exists, but the laws of physics do not restrict telescope arrays to the size of current human projects. A civilization able to operate across its system could create enormous baselines. Multiple spacecraft could function as one receiver. Precise clocks would combine their observations. The resulting instrument might study nearby planets with remarkable resolution. Earth could be visible not as one point, but as a structured radio world. The observer may identify clusters of emission corresponding to continents. It could see satellites. It may distinguish ground radar from orbital communication. Over time, it could watch cities and networks change. This image feels almost like being watched from nearby, but the observation would still be indirect. The listener receives old energy. It sees the planet's past. It may know patterns without seeing individual people. At several light years, even an extraordinary telescope faces limits imposed by wavelength, collecting area, and distance. A civilization does not need to observe human faces to recognize civilization. Our global systems are enough. The planet contains repeating artificial organization. That organization may be visible. Optical observation offers another route. Earth's night side contains city lights. From another star, those lights are extraordinarily faint. The day side reflects sunlight much more brightly. Clouds, oceans, deserts, and ice dominate the visible signal. Modern cities cover only a small fraction of the surface. Their upward light is weak compared with the sun. An observer using technology similar to ours would struggle to detect them from interstellar distance. A much larger telescope may eventually succeed. It could watch Earth near crescent phases, when less of the day side is visible. The night side then occupies more of the observed hemisphere. Artificial lights would still be faint, but the contrast becomes more favorable. As Earth rotates, the brightness might change according to populated regions. The same pattern would return each day. An advanced observer could compare visible, infrared, and radio data. Radio reveals technology. Night side light supports it. Atmospheric chemistry provides context. The planet begins to answer in several ways at once. Industrial compounds may offer additional evidence. Earth's atmosphere contains substances created or greatly increased by human activity. Some absorb infrared light strongly. A distant spectrograph might detect them if the concentrations are high enough and the instrument sensitive enough. Unlike radio transmissions, atmospheric gases spread around the planet. They do not depend upon beam direction. Their signals persist for years or decades. A listener does not need to observe at one precise moment. It can gather light across many planetary orbits. This makes atmospheric technosignatures slower but more continuous. A radio pulse says that technology operated during one moment. An industrial molecule may reveal that technological activity has altered the atmosphere over a longer period. The two together would be compelling. A living planet has developed industry. Its atmosphere changes. Its radio emissions appear. Artificial objects begin orbiting. The listener could watch an entire technological transition through light. Earth's carbon dioxide is also increasing because of human activity. But carbon dioxide has many natural sources and is common on planets. It would not identify technology by itself. The strongest evidence would come from combinations. Chemicals with no plausible natural production. Seasonal patterns linked to industrial activity. Radio emission moving with the planet. Night side illumination. Waste heat. Satellites. Each line of evidence reduces ambiguity. An observer may know more about Earth than Earth knows about many exoplanets, because our signals are varied. The planet does not rely upon one technosignature. It produces a collection, yet each is faint at interstellar distance. The question becomes one of capability. How large must the listener's telescope be? How long has it observed? How much information can it combine? A civilization slightly ahead of humanity may detect our strongest radar beams. A far more advanced civilization may examine the complete technological environment. This creates levels of awareness. One listener may have heard one brief pulse. Another may know Earth contains technology. Another may have reconstructed our rotation, orbit, satellites, and exploration network. Another may have been monitoring the planet for centuries. All could be described as listening. Their knowledge would differ enormously. The nearest stars receive the newest information, but they are few in number, The farther the sphere expands, the more star systems it reaches. Volume grows rapidly with distance. A sphere twice as large contains roughly 8 times the volume. As human radio history moves outward, the number of potential receivers increases, but the signals weaken. More stars are reached. Fewer may be capable of detecting the weaker emissions. This creates a balance between opportunity and sensitivity. Nearby systems receive strong recent signals, but only a limited number exist. More distant systems are numerous, but ordinary leakage may have faded beneath detectability. Powerful radar remains visible farther, but only inside narrow beams. The region of realistic detection is not one simple radius. It depends upon the transmitter and receiver. For every type of signal, there is a different listening zone. Television leakage has one. Mobile communication has another. Planetary radar has another. Deliberate interstellar messages have another. Atmospheric chemistry has another. Night side light has another. An observer may detect one signature and miss the rest. Someone could know that Earth is living without knowing it is technological. Someone else could detect one radar pulse without measuring the atmosphere. Another could identify industrial gases but never receive radio. The first evidence shapes the story the listener tells about us. If radio comes first, Earth appears as a technological source. If oxygen comes first, it appears as a living planet. If artificial chemicals come first, it appears industrial. If probes are detected moving around other planets, it appears exploratory. All are incomplete portraits. Perhaps a distant civilization is currently assembling these fragments. Its records contain decades of observations. The first spectrum suggests oxygen. Later measurements reveal seasonal changes. Then one radio pulse appears. A few years later, another. The source follows Earth's orbit. The evidence crosses a threshold. The world becomes a confirmed technological candidate. The listener increases its attention. It does not need to send a reply immediately. Observation may continue for generations. This possibility raises another quiet issue. Listening may be easier than speaking. A civilization can observe Earth without revealing itself. Sending a powerful message announces its own location. Some societies might prefer passive study. Human astronomers often observe planets without transmitting toward them. The absence of a reply does not mean the absence of a receiver. Someone may know that Earth exists and choose silence. The reasons could be simple. Its communication policy may require stronger evidence. It may avoid disturbing younger civilizations. It may consider interstellar conversation too slow to be useful. It could transmit only after detecting a deliberate beacon. It may have no interest in contact, or its observers may have recorded Earth while the wider civilization remains unaware or indifferent. Humanity cannot infer motive from silence. Every proposed reason remains speculation, but passive observation is physically easier than sustained communication. The listener collects energy already arriving. The sender must create and direct additional energy. A quiet telescope can operate without becoming visible. This asymmetry means that being observed may be more likely than receiving a reply. A civilization might study thousands of worlds and communicate with none. Earth could belong to such a survey. An automated telescope records our radio spectrum. Software classifies the planet. The information enters an archive. No message returns. From humanity's perspective, nothing changes. From the observer's perspective, a discovery has occurred. Contact exists in only one direction. This is still not evidence that it is happening. It is a reminder that the absence of incoming communication cannot reveal whether Earth is already known elsewhere. The only direct way to investigate is to look outward. Nearby stars deserve particular attention because they receive recent human technosignatures and could return a response within relatively short astronomical timescales. Systems positioned to observe Earth's transit are interesting because they may already know the planet exists. Stars near the paths of strong radar transmissions are interesting because they may have received unusually clear technological evidence. The history of our outgoing signals can guide the search for incoming ones. Astronomers can calculate where beams traveled. They can identify which systems crossed those paths. They can estimate when the signal arrived. Then they can determine the earliest date a response could reach Earth. The sky becomes a collection of possible reply windows. Some have not opened yet. Some are open now. Some passed before modern SETI began listening. A transmission sent toward a nearby star decades ago may have arrived, been answered, and returned while no suitable telescope observed the correct frequency. The reply could have crossed Earth unnoticed. It may remain inside archived data, or no listener existed. The possibilities are observationally identical until evidence separates them. This is why persistent monitoring matters. A signal may arrive once. A telescope cannot return later and recover a pulse that has continued onward. All-sky radio observatories, automated alerts, and broad-frequency coverage increase the chance that Earth is watching when an answer crosses the planet. The listener beyond Earth faces the same problem. Our signals are brief. Its instruments must also be present. Two civilizations may each possess powerful telescopes while repeatedly missing the other's transmissions. Contact requires mutual timing. This can be understood through two rotating lighthouses. Each sends a narrow beam. The beams sweep through darkness. Most of the time, neither points toward the other. One beam crosses the distant lighthouse, but the receiver is temporarily inactive. Years later, the second beam crosses the first, but the event is classified as noise. Both continue turning. Each concludes that the horizon is empty. The darkness between them is not caused by distance alone. It is created by timing. Wide-field monitoring reduces the problem. A civilization that truly wishes to discover technological worlds may construct many receivers and watch continuously. Its instruments could cover the entire sky across broad ranges of frequencies. Artificial intelligence would classify events. Short pulses would be preserved. Candidate systems would receive repeated observation. If such a network exists around a nearby star, Earth may be difficult to miss forever. Our strongest beams may cross its system eventually. Our atmosphere remains visible. Our satellites multiply. Our technology creates new signals. Over centuries, evidence accumulates, but the observer's continued existence is another uncertainty. Civilizations may not remain stable for long periods. Their telescopes may fail. Funding, culture, environment, or technology may change. An automated network could outlive the society that built it. A biological civilization may lose interest. A machine civilization may continue listening indefinitely. There is no known typical lifetime for technological observation. Human radio astronomy is less than a century old. SETI is younger still. Earth has listened seriously for only a small moment. It is possible that many civilizations listen briefly and then move on. The overlap between two listening eras may be rare. This temporal challenge joins the spatial one. The correct star, the correct frequency, the correct time, the correct technology, the correct attention. Every requirement narrows the possibility. And yet the galaxy is ancient. It contains hundreds of billions of stars. Even rare alignments may occur somewhere. The question is whether one occurs near Earth now. No observation can currently answer yes. No confirmed signal shows that a receiver has noticed us. No artificial object has approached in response to human broadcasting. No message has referred to our transmissions. The scientific record remains quiet, but Earth is detectable in principle. Its strongest radar crosses interstellar distances. Its atmospheric biology is older and more persistent. Its orbital motion can reveal the planet. Its rotation can modulate signals. Its spacecraft communication shows technology spreading through the system. A listener with suitable instruments could assemble the evidence. Perhaps this is already happening. A telescope beneath another sky may be pointed toward a small yellow star. Its receiver separates millions of frequencies. Most contain natural noise. Then one channel brightens. The signal rises gently. It drifts. It fades. The software marks the event. A second instrument turns toward the same coordinates. Nothing returns. The candidate remains open. Years later, another pulse appears from the same star. Its drift follows the motion of one small planet. The observer begins listening more carefully. Earth is still unaware. Our radar continues measuring distant objects. Our spacecraft continues sending faint replies. Our planet rotates beneath its clouds. And somewhere beyond the reach of ordinary sight, another instrument may be learning the rhythm of our world. Some stars have a better view of Earth than others. The difference is not distance alone, it is geometry. From most places in the Milky Way, Earth never passes directly across the face of the Sun. The planet circles its star from the side. A distant observer may still detect it through reflected light, gravitational motion, radio emission, or direct imaging. But from one narrow region of space, Earth becomes a transiting world. Once every year, it moves between the Sun and the observer. For several hours, the planet blocks a tiny portion of sunlight. The Sun dims by less than 1/100%. Then Earth moves away. 1 year later, the same shadow returns. The pattern repeats with the regularity of an orbit. To an astronomer beneath another sky, this repeating dip could become the first clear evidence that a planet circles the Sun. It is the same method humanity has used to discover thousands of worlds around other stars. A telescope measures a star's brightness. A planet crosses in front. The light decreases slightly. The interval between dips reveals the length of the planet's year. The amount of blocked light reveals its approximate size. If several planets transit, each creates its own repeating rhythm. Earth's transit would be difficult to detect. The Sun is much larger than Earth. The planet's silhouette would cover only a small part of the stellar disk. But a sufficiently sensitive telescope could collect many transits and combine them. One observation provides a faint dip. 10 observations strengthen the pattern. Decades of monitoring create a precise orbital history. The listener would learn that one small planet circles the Sun every 365 days. It might also detect Venus, Mercury, or Mars if its viewing angle allowed their transits. The solar system would emerge slowly through repeating shadows. The special region from which Earth can be seen crossing the Sun is called the Earth Transit Zone. It forms a narrow band across the sky. Any observer positioned within that band has the correct alignment. Earth, the Sun, and the distant telescope briefly form a nearly straight line once during every orbit. The observer does not need to know where Earth is in advance. The planet announces itself by reducing the Sun's brightness. Geometry places the clue directly inside the starlight. This makes stars within the Earth Transit Zone especially interesting in the search for extraterrestrial intelligence. Human astronomers already pay close attention to planets that transit because their atmospheres can sometimes be studied. Another civilization may follow the same strategy. If it searches for nearby inhabited worlds, Earth would be easier to discover from this narrow celestial band than from many other directions. The zone does not contain the same stars forever. Every star moves through the Milky Way. The Sun moves too. Over thousands of years, these motions change the viewing angle. A star outside the zone can gradually enter it. Another can leave. A civilization may see Earth transits for centuries or millennia, then lose the alignment as its star continues across the galaxy. The planet does not disappear. Only the repeating shadow disappears. The observer would need to switch to another method. Researchers used measurements of stellar positions and motions to reconstruct which nearby stars could have observed Earth transiting during a 10,000-year interval. They found 1,715 stars within 100 parsecs that were positioned to see Earth's transit sometime during the last 5,000 years. Another 319 stars are expected to enter the correct viewing zone during the next 5,000 years. Among the nearest stars in that study, human-made radio waves had already passed 75 systems with a past or present view of Earth's transit. These numbers do not describe civilizations. They describe opportunities. No one knows whether any of those stars possesses life. Some may have no planets. Some may host planets with no atmosphere. Some may contain simple organisms but no technology. Others may contain worlds that have not yet been examined closely. The geometry provides a possible viewpoint. It does not place an observer there. Still, the overlap is scientifically interesting. A star that can see Earth transit may already know that the planet exists. If the same star has also received human radio emissions, two independent forms of evidence could arrive from the solar system. First, a small world repeatedly crosses the Sun. Then narrow artificial signals appear from the same direction. The combination is much stronger than either sign alone. The transit identifies the planet. The radio emission suggests technology. A listener could connect the machine to the world. Without the transit, one radio pulse near the Sun may be difficult to locate precisely. It could come from Earth, a spacecraft, another planet, or interference near the listener. With the planetary orbit already measured, the observer can test whether the signal moves with Earth. The frequency shifts through the year. The daily rotation produces smaller changes. The radio source follows the same body that creates the shadow. The planet begins to reveal itself through two kinds of rhythm. One is visible, one is radio. Both repeat. An advanced observer may then examine the sunlight passing through Earth's atmosphere. During a transit, most of the planet blocks the sun completely, but a thin ring of sunlight travels through the air near the edge of the world. Molecules absorb selected wavelengths from that light. Water vapor removes one pattern. Oxygen and ozone remove others. Carbon dioxide and methane leave additional features. Clouds and atmospheric particles scatter light. The resulting spectrum contains a faint chemical impression of the planet's air. Humanity uses this form of transmission spectroscopy to investigate exoplanets, particularly planets passing in front of small stars where the atmospheric signal is easier to separate. Studying Earth across the Sun would be more difficult than studying an Earth-sized planet around a much smaller red dwarf. The Sun is large, the atmospheric ring around Earth is thin. The chemical signal would be extremely faint. A civilization with larger telescopes, longer observing programs, or instruments positioned in space might still attempt it. The observer could collect the planet's transits for decades. Each crossing adds photons. Noise gradually declines. Weak patterns become measurable. The atmosphere would not provide a simple label saying that life exists. Every gas must be interpreted within planetary context. Oxygen can form through non-biological processes under some conditions. Methane can emerge from geology. Water does not guarantee organisms, but Earth's atmosphere, surface temperature, oceans, seasonal behavior, and unusual chemical balance would make the planet worthy of prolonged attention. A listener may have watched this world for a very long time before hearing radio. Earth's atmospheric oxygen has been present on large scales for far longer than human technology. The planet may have looked biologically interesting across immense spans of time. To a patient extraterrestrial survey, radio would not introduce an unknown world. It would transform a familiar one. A possible biosphere suddenly begins producing narrow signals. The transition may appear almost instantaneous. One transit shows the atmosphere. Another arrives a year later. Centuries of observations show the same planet circling quietly. Then artificial emission appears beside it. Radar beams begin crossing the system. Objects transmit from orbit. Signals move toward Mars and the outer planets. The world changes category. It is no longer merely a possible living planet. It becomes a possible technological one. This sequence may be more convincing than one deliberate message. A message can be imitated by interference. A world changing gradually, from biological signs to technological activity, presents a connected history. The listener sees the planet before the radio age. Then it witnesses the radio age begin. The evidence has a before and an after. One nearby system once possessed the correct viewpoint. Ross 128 is a small red dwarf approximately 11 light-years from Earth. It hosts a known planet called Ross 128b. The planet has an estimated mass and size somewhat greater than Earth's and circles its star in about 9.9. Its actual atmosphere and surface conditions remain unknown. The existence of a roughly Earth-sized planet does not establish habitability or life. From the direction of Ross 128, Earth could be seen transiting the Sun in the past. The star has since moved out of the Earth transit zone. Any observer there with a sufficiently long astronomical history might possess old records of Earth's recurring shadow. Its present-day instruments would no longer see the planet cross the Sun. The geometry has shifted, but the earlier discovery would not need to be forgotten. Once a planet is known, astronomers can continue observing it through other methods. They can predict its orbit, they can listen for radio, they can search for reflected light. A lost transit does not erase the world. Ross 128 is close enough that human radio emissions have crossed the distance. The signals received there now left Earth roughly 11 years earlier. If technology exists around that star, it does not see this exact moment. It receives an Earth from the recent past. The planet already has satellites. It already communicates with spacecraft. Its strongest radar and directed transmissions already exist. A listener there may have access to both an ancient transit history and modern technological signals. Yet a response sent today would require another 11 years to return. Earth would experience more than 2 decades between the transmission that attracted attention and the answer reaching human receivers. The observer could be listening now while the evidence of that listening remains far in the future. Another nearby system will soon gain the transit view. Teegarden Star is a faint red dwarf roughly 12 light-years away. At least 3 small planets are currently catalogued around it. Teegarden's star completes an orbit in about 4.9 days. Planet C takes about 11.4 days. Planet D takes approximately 26.1 days. Their measured masses are broadly comparable to Earth's, although their atmospheres and actual environments remain unknown. The motion of Teegarden's star is expected to carry it into the Earth transit zone around the middle of this century. From then on, an observer there would gain a repeating view of Earth passing across the Sun. The 2021 Stellar Motion Study estimated that the transit view would begin about 29 years after publication, placing the transition around 2050. That date feels close from a human perspective. People alive today may still be living when the geometry changes. Nothing physically dramatic will happen to Earth. No new signal will be emitted. Teegarden's star will simply reach a position from which the planet's orbit becomes visible edge-on. The solar system will acquire a new possible audience. Light leaving the Sun around that period will require roughly 12 years to reach Teegarden's star. An observer there would not see the first transit immediately from Earth's calendar. The information must travel. Likewise, any response requires another journey back. The geometry opens around one date. The observational consequences unfold later. Suppose a technological society exists in that system. Its astronomers may already know the Sun. They may already detect some human radioactivity. Then the first Earth transit reaches their instruments. A small repeating shadow confirms the orbit. The atmosphere becomes a possible target. Radio signals can be connected to the planet with greater precision. Their understanding of the solar system changes without Earth sending anything deliberately. The observer simply gains a better angle. The possibility remains entirely hypothetical. No evidence shows that Teegarden's star contains life or listening technology. Its planets are known primarily through the motion they produce in their star. They do not transit from Earth's perspective, so their atmospheres are especially difficult for current instruments to study. The system is important because it is nearby, contains small planets, and is approaching the reciprocal geometry from which Earth's transit could be observed. It represents opportunity rather than proof. Farther away lies one of the most famous compact planetary systems known. TRAPPIST-1 is about 40 light-years from Earth. 7 approximately Earth-sized and probably rocky planets circle its small red dwarf star. All 7 orbit closer to their star than Mercury orbits the Sun. 3 TRAPPIST-1e, F, and G lie within the system's traditional habitable zone, although being in that zone does not establish the presence of liquid water, a stable atmosphere or life. TRAPPIST-1 does not currently occupy the Earth transit zone. Its observers, if any, would not see Earth regularly cross the Sun today. Stellar motion calculations indicate that the system may enter the correct zone about 1,642 years after the 2021 study, placing the beginning around the 37th century. By then, the human civilization that exists today will belong to the distant past. Perhaps humanity will remain technological. Perhaps it will have changed beyond recognition. Perhaps other forms of intelligence will study the solar system. Whatever Earth becomes, the first transit visible from TRAPPIST-1 will show the planet as it existed 40 years before the observation reaches that system. The observer always sees history. The transit zone therefore creates windows across time. Ross 128 held a window in the past. Teegarden's star approaches one in the near astronomical future. TRAPPIST-1 waits much longer. Each star moves through its own period of alignment. Some windows last for centuries. Others last for thousands of years. A long-lived civilization could notice the transition. Before the window opens, Earth never crosses the Sun. Then a shallow annual dip begins. The first event might look like an instrumental fluctuation. The second arrives 1 year later. The third confirms the rhythm. A new planet has appeared not because it formed, but because the viewing geometry became favorable. The observer could compare earlier data. Perhaps reflected light measurements already hinted that Earth existed. Perhaps radio emission had been detected. The transit supplies another piece. This is one reason stellar motion matters to reciprocal SETI. The best places to search are not fixed forever. A star that cannot see Earth today may become capable later. A star that once had the view may retain records. An observer does not need to be located in the present-day Earth transit zone to know this planet. Its civilization may have discovered Earth during an earlier alignment. Knowledge can survive after geometry changes. The same principle applies to humanity. Some exoplanets transit their stars now. Over long timescales, gravitational changes, and stellar motion may alter the exact viewing arrangement. The planets continue to exist after transits stop. Astronomical knowledge preserves them. A distant archive may preserve Earth in the same way. Imagine a civilization around Ross 128 that began astronomy thousands of years ago. Its early instruments noticed the sun dimming annually. Later telescopes studied the planet's atmosphere. The transit eventually disappeared as the star moved away from the zone, but Earth remained inside its catalogs. Generations continued monitoring the sun. Then human radio emissions arrived. The listener did not discover a random technological source. It heard a planet already known. The old transit records gave the signal a home. This scenario is possible within geometry and light travel. It is not evidence that such a civilization exists. The distinction remains quiet but essential. Astronomy can identify where listening would be favorable. It cannot place listeners there without observation. Every star in the Earth transit zone may be lifeless. Every possible archive may be imaginary. The value of the idea lies in creating testable priorities. Human SETI programs can observe stars that have a reason to know Earth exists. The search can focus upon systems that receive both transit information and radio evidence. If another civilization chooses reciprocal targets in the same way, it may transmit toward planets that can also see its world transit. Mutual visibility creates a natural meeting place. Neither civilization needs to know the other's culture. Both understand orbital geometry. A transit announces when attention is likely. It may also provide a natural schedule for communication. Suppose an observer knows that Earth crosses the Sun once each year from its viewpoint. It could send a signal timed to arrive during the transit. Human astronomers might be watching the Sun or analyzing the system's geometry at that moment. The transmission could begin shortly before the planet's shadow. It could repeat during each annual crossing. The timing itself would contain meaning. The sender appears to understand Earth's orbit. A signal synchronized with several transits would be difficult to dismiss as random. Humanity could use the same strategy. Messages might be transmitted toward known planetary systems during moments that possess shared astronomical significance. A planet passing in front of its star creates a predictable event visible to both careful observers. The transit becomes a cosmic clock. No shared calendar is required. The orbit supplies one. A listener may also use Earth's transit to measure its atmosphere across different historical periods. Industrial activity changes gases gradually. Large volcanic eruptions alter aerosols. Vegetation cycles influence seasonal patterns. Clouds shift. The chemical spectrum would not remain perfectly constant. A civilization gathering centuries of data might notice that Earth's atmosphere is changing rapidly. Carbon dioxide rises. Certain manufactured compounds appear and later decline. The planet's technological period leaves traces beyond radio. Interpreting those changes from interstellar distance would be difficult. Many natural processes affect atmospheres. A strong claim of industry would require careful modeling and highly sensitive instruments. But the listener would not need one perfect observation. It may possess an archive spanning generations. Changes that appear subtle to humanity could become clear when measured over a century. The observer could compare the pre-industrial planet with the technological one. Earth's atmosphere becomes a historical document. Humanity studies ancient climates through ice cores, sediments, tree rings, and fossils. An extraterrestrial astronomer would not have those materials. It would study light. The planet's changing spectrum would act as a distant record. Each transit preserves one small measurement. Thousands of measurements form a timeline. The listener may infer that a biosphere is altering its climate. It may notice the appearance of chemicals associated with manufacturing. Later, it might observe some compounds decline, perhaps suggesting regulation or technological change. The civilization would learn about Earth's behavior without seeing one human being. Radioactivity could add finer timing. An atmospheric change unfolds over years. A radar beam lasts minutes. Satellites multiply over decades. Spacecraft transmissions begin appearing from Mars and beyond. The observer combines slow and fast evidence. The atmosphere describes the planet as a whole. Radio describes specific machines. Transit geometry connects both to Earth. The complete picture would still contain large unknowns. The listener may not know whether the dominant intelligence lives on land, in oceans, underground, or in orbit. It may not know how many technological species share the world. It could mistake automated systems for biological societies. Human transmissions may reveal mathematical patterns, but language could remain inaccessible. The listener knows that Earth has technology. It may know very little about what it feels like to live here. This distance between detection and understanding is important. Humanity sometimes imagines alien observation as complete surveillance. A distant civilization detects Earth and immediately understands cities, politics, art, history, and individual lives. Physics does not provide this knowledge automatically. Most interstellar observations would begin as faint combined signals. The planet is smaller than a point. Its entire surface merges into one unresolved glow. Radio transmissions overlap. Atmospheric chemistry averages across oceans and continents. The observer reconstructs broad properties. Detail requires much larger instruments and extraordinary patience. Someone may be listening without knowing who speaks. The word someone may itself be misleading. The receiver could be a machine. An automated observatory might monitor every nearby transiting planet. It records spectra. It classifies radio events. It updates probabilities. No conscious observer examines Earth directly. The system may transmit an alert only after a threshold is reached. It could operate for thousands of years. A listening network built by one civilization may continue after its creators disappear. Earth's audience could be an archive that no longer has readers, or the machine itself may be the intelligence. Its creators may have transformed into artificial systems. The observer could exist across many instruments rather than inside one body. Transit searches are naturally suited to automation. Stars must be watched continuously. Tiny changes must be measured. Regular patterns must be found inside enormous datasets. Human planet hunting missions already depend heavily upon computers. Another civilization could build a survey that never sleeps. It watches the sun for centuries. The first radio pulse becomes one data point. The second strengthens the classification. The transit repeats. Atmospheric evidence accumulates. The machine reaches a conclusion. Technological activity detected. What happens next depends upon instructions written long before. Perhaps it sends a reply. Perhaps it waits. Perhaps it stores the result. Perhaps the civilization that designed the system no longer exists to receive the report. Earth may be known by a machine beneath an empty sky. The possibility sounds distant, but it follows from the difference between technological lifetimes and biological ones. A telescope can outlast an astronomer. An archive can outlast a generation. With maintenance or self-repair, an automated system might outlast a society. The listener does not need to be waiting personally during every century. It only needs instruments that preserve unusual events. This returns the question to time. A star may remain in the Earth transit zone for thousands of years. Earth's loud radio period may last only centuries. The observer's technological period may also be limited. For contact to become possible, these windows must overlap. The star has the correct view. Earth produces detectable signals. The listener possesses suitable instruments. The instruments are operating. The civilization recognizes the evidence. Then, if it chooses, a response begins its journey. Many stars may experience only part of this chain. Ross 128 may have seen Earth transits before human radio became strong enough to be detected there. Its hypothetical observers could have identified a living planet, then lost the transit view before the technological era. Yet their descendants might continue listening. Teegarden's star will gain the transit view after human radio has already crossed it. A hypothetical observer there may hear technology first and confirm the planet through transit later. TRAPPIST-1 may receive centuries of human radio history before gaining the geometric view. Each system encounters Earth in a different order. This order changes the meaning of the evidence. One listener first sees life, then hears technology. Another first hears a strange signal, then sees the planetary shadow. A third detects artificial atmospheric chemistry before any radio beam crosses its world. All may eventually reach the same conclusion through different paths. Earth is not sending one universal introduction. Its discovery depends upon the listener's location and method. The Earth transit zone offers one of the clearest possible pathways. The planet creates a repeating event. Its atmosphere may be studied. Its radio emissions can be attached to an orbit. The geometry provides a reason to keep watching, but most nearby stars do not lie within that zone. If listeners exist there, they need other methods. They may attempt direct imaging. They could measure the sun's tiny motion caused by Earth's gravity. They might detect reflected light from the planet. They may hear radio without ever seeing a transit. A civilization does not need the special alignment. The zone makes detection easier. It does not make detection exclusive. Proxima Centauri, the nearest star, does not currently see Earth crossing the sun. A listener there could still detect sufficiently strong transmissions. It might directly image Earth with an advanced instrument. It could know the planet exists through other techniques. Transit geometry is one door among several. The search for listeners must therefore remain wider than one strip of sky. Yet reciprocal geometry gives humanity something rare: a reasoned list. Instead of asking whether anyone anywhere is watching, researchers can identify stars from which Earth is especially visible. They can estimate which versions of Earth have reached those systems. They can calculate whether human radio has arrived. They can determine when a response could return. The abstract question becomes a set of timelines. For one star, the first technological evidence arrived decades ago. For another, it arrives tomorrow. For a third, it will not arrive for centuries. For one system, a reply could already have returned. For another, the earliest reply belongs to the distant future. The night sky contains these invisible schedules. A star may look like one quiet point. Around it is a communication history defined by distance and motion. Human eyes cannot see the timeline. Astronomy can calculate it. Perhaps one of the 75 nearby stars identified in the overlap between transit visibility and human radio reach possesses a telescope. Perhaps it noticed the annual shadow. Perhaps its instruments have separated one artificial signal from the sun. Perhaps Earth has already moved from an unknown planet to a monitored world. There is no evidence that this has happened. No confirmed reply has arrived. But the geometry shows that it could happen without breaking any known physical law. No interstellar spacecraft is required. No impossible telescope is assumed for the strongest emissions. Only a planet in the correct place. A receiver, time, and attention. The observer may be looking at Earth now. It would not see this evening. It would see an earlier one. Clouds would cross oceans that have already changed. Radio signals would leave transmitters that may already be silent. The listener would collect a past that still feels present from its own world. And if it responded at that moment, the answer would begin crossing the same darkness in reverse. Years would pass. The observer would continue living its own history. Earth would continue turning. No one here would know that the silence had already ended at the source. The message would still be traveling. For now, the Earth transit zone remains a map of possibility, a narrow ribbon filled with moving stars. Some once saw the planet. Some see it now. Some will gain the view in centuries to come. Across that ribbon, the sun occasionally dims. A small shadow crosses its surface. Inside that shadow are oceans, continents, cities, antennas, and every living person on Earth. From far away, all of it becomes one tiny change in light. A patient observer might recognize the world. A more sensitive one might hear its machines. And somewhere within the narrow geometry of the galaxy, the act of listening may already have begun. A listener does not need to sit beneath an open sky. It may listen from orbit. It may place receivers across the surface of a moon. It could spread thousands of small antennas through space and combine them into one immense instrument. The largest human radio telescopes already work by gathering weak electromagnetic waves over wide areas. Some use one enormous dish. Others use many separate antennas linked through precise timing. When those antennas observe the same source, their measurements can be combined. The technique is called interferometry. Instead of behaving like many independent telescopes, the antennas begin acting like parts of one much larger eye. The effective sharpness of the instrument depends not only upon the size of each antenna, but upon the distance between them. Two dishes separated by hundreds of kilometers can resolve finer detail than either one alone. Arrays spread across continents can study radio sources with remarkable precision. If another civilization had developed the same basic principle, it would not be limited to one planet. Its receivers could orbit a moon. They could circle a star. They might be positioned millions of kilometers apart. The entire planetary system could become one listening instrument. Such an array would not resemble a single telescope pointed toward Earth. It would resemble a distributed sense. Each station collects one faint part of the wave. Clocks compare arrival times. Computers reconstruct the direction and structure of the source. A weak signal that appears almost invisible to one receiver becomes clearer when many are combined. Earth may be heard not because one enormous dish exists somewhere, but because an entire system is listening together. This remains hypothetical. No evidence shows that such an array is currently observing the solar system. Yet every element follows physical principles already used by humanity on a much smaller scale. Larger baselines improve angular resolution. Greater collecting area gathers more energy. Longer observations reveal weaker periodic signals. Better processing separates patterns from noise. The same improvements that make human astronomy more sensitive would make another civilization more sensitive to Earth. A listener may also choose a quieter location than the surface of its home world. Earth-based radio telescopes face constant interference. Communication towers transmit, satellites cross the sky, aircraft radar operates, electronics generate unintended signals. Even remote observatories exist inside the electromagnetic environment of modern civilization. Another technological planet would probably face a similar problem. Its own machines could drown out the very signals it hopes to detect from the stars. The solution may be distance. A receiver placed on the far side of a moon would be shielded from much of the radio emission produced by the inhabited planet. The body of the moon would block direct transmission. The telescope would face outward into a quieter sky. Human scientists have long considered the far side of Earth's moon attractive for low-frequency radio astronomy for this reason. An extraterrestrial listener might reach the same conclusion within its own system. Its best listening station may stand beneath a sky where its home world is never visible. A moon rests between the observatory and civilization. Behind the receiver lies rock. Ahead lies the galaxy. The instrument could listen continuously without the constant glow of local communication. It might detect frequencies that are difficult to observe from the planet's surface. A thick atmosphere can absorb or distort parts of the radio spectrum. Lightning and auroras create natural interference. Space-based or lunar observatories avoid many of these limitations. A listener seeking Earth may therefore observe from a place that appears lifeless. The inhabited planet could orbit far away. The receiver itself may be automated. From Earth, the moon looks quiet, yet its dark surface contains an array waiting for narrow signals from other stars. Listening stations could also be placed far from the central star. Stars are radio sources. They produce natural emission, flares, and plasma activity. A receiver operating at the outer edge of a planetary system may experience a quieter local environment. The star becomes fainter with distance. The telescope can cool naturally. Cryogenic instruments often become more sensitive because heat creates noise within detectors. A civilization may construct observatories in cold regions beyond its outer planets. There, sunlight is weak, the sky is dark. Machines can listen for long periods with little local disturbance. Such an observatory might circle a distant dwarf planet. It may float near the gravitational boundary of the system. It could consist of many small receivers held in precise formation. The builders may visit only rarely. Most work would be performed by software. The instrument could remain active for centuries. Its search would not depend upon the lifetime of one observer. A patient machine may be far better suited to interstellar listening than a biological individual. Earth's signals are inconsistent. A strong radar beam may cross one direction only once. A spacecraft transmission may last minutes. A particular frequency may remain quiet for decades. An observer waiting personally for such an event would experience mostly nothing. An automated system does not become bored. It records. It classifies. It waits. Thousands of stars can be monitored. Billions of frequency channels can be examined. One candidate is stored. The instrument returns to the source. Another event appears 20 years later. The two signals are compared. A pattern that would be invisible within one human career becomes obvious across a machine's archive. This may be one of the greatest advantages a distant listener could possess. Time. Human SETI programs have listened seriously for only a small fraction of a century. Many targets have been observed for only minutes or hours. A civilization with a 1,000-year archive would see the radio sky differently. It could measure long cycles. It might notice transmitters that operate once every decade. It could distinguish random interference from signals tied to planetary orbits. It may observe a technological world during its entire transition from early broadcasting to directed communication. Earth's radio history would appear as a changing landscape rather than one brief sample. At first, broad emissions emerge. The signals increase. Radar becomes stronger. Satellites appear. Spacecraft communication spreads through the system. Then some leakage declines as communication moves into cables and narrow beams. The listener watches one form of visibility rise and another fall. Technology does not simply appear, it evolves. A long archive could reveal this evolution without decoding any message. The spectrum itself changes. Analog carriers give way to digital modulation. Frequency use becomes more crowded. Transmission patterns become more efficient. Beams move toward other planets. New signals appear from orbital locations. The listener could infer that the civilization is reorganizing its communication systems. It may even estimate which technologies are becoming obsolete. Imagine observing Earth's radio emission as if it were weather. Some frequencies brighten, others become quiet. Powerful bursts sweep across the sky. Artificial satellites create moving points. The entire pattern has seasons, cycles, and trends. A patient observer does not ask only whether Earth transmits. It asks how the transmission changes. Change can become evidence of adaptation. Natural radio sources evolve too. Stars flare, pulsars slow. Magnetic activity cycles. But technological change may follow different patterns. A civilization selects frequencies. It builds new infrastructure. It turns systems off. The changes may occur rapidly compared with stellar timescales. The observer could see deliberate reorganization. A broad channel disappears. Several narrower channels take its place. A new transmission begins from lunar distance. Another appears near Mars. The technological network expands. No single event proves intelligence more strongly than the complete history. A listener may also compare Earth with other planets. If its survey includes thousands of nearby systems, it could identify patterns common to nature. Stars create broad radio noise. Magnetized planets produce low-frequency emission. Lightning produces bursts. Auroras generate changing signals. The observer builds a library of natural planetary radio behavior. Then Earth differs. Its emissions contain narrow channels. Some signals repeat according to human schedules rather than weather. Powerful beams point toward selected objects. Transmitters appear in orbit. The planet becomes an outlier. Artificiality is often recognized through comparison. One world alone may appear mysterious. 1,000 natural worlds show which patterns are normal. Earth becomes visible because it does something the others do not. Humanity follows the same approach when searching for technosignatures. Astronomers do not simply look for unusual energy. They ask whether the energy resembles stars, planets, dust, plasma, or human interference. A distant listener would face the same scientific challenge. Its understanding of Earth would depend upon how well it understands nature. A young observing civilization may mistake solar radio storms for technology. It may classify terrestrial radar as an unfamiliar natural process. An older one may possess a much richer catalog. It could recognize the difference quickly. This means detectability depends not only upon instruments. It depends upon knowledge. A receiver can record a signal perfectly and still misunderstand it. The pattern must be interpreted. Another civilization may discover Earth before it develops a theory of artificial radio leakage. Its astronomers record odd narrow lines near the sun. The data are archived. Centuries later, their own world begins using similar technology. Suddenly, the old observations make sense. The researchers recognize that the signal from the solar system resembled an earlier stage of their own technological history. Earth could be discovered retroactively. The evidence arrived before the concept needed to interpret it. Human astronomy has experienced similar transformations. Observations often exist before their meaning is understood. A faint point moves through archival images years before a planet or asteroid is officially discovered. A new algorithm finds a signal inside old radio data. A spectrum contains a molecular feature that becomes recognizable only after laboratory measurements improve. Detection and recognition do not always occur together. Someone may already possess the answer that Earth is technological while lacking the framework to see it. The reverse is equally possible. A listener may recognize technology while misunderstanding its source. A powerful radar signal crosses its system. The direction points near the sun. The observer knows that a transmitter exists somewhere in the solar system, but it cannot immediately determine whether the signal comes from Earth, the Moon, a spacecraft, or another planet. The system becomes a technological candidate before Earth itself is identified. Repeated measurements would narrow the source. The frequency drift reflects orbital motion. Daily changes reveal rotation. The signal may disappear when Earth moves behind the Sun from the observer's viewpoint. Over time, the transmitter's location becomes clearer. The listener reconstructs the solar system, much as human astronomers reconstruct exoplanet systems. Gravity, motion, and timing provide a map. Suppose a radar pulse is received several times over many years. Its frequency follows Earth's orbit. Its strength varies with the planet's rotation. The strongest emission appears when certain longitudes face the observer. The listener can estimate the location of transmitting regions. A rough technological geography begins to emerge. One cluster rotates into view, then another. The observer may infer that the planet's technology is not distributed evenly. Oceans create long, quiet periods. Continents create brighter intervals. The listener still cannot see cities, yet it may infer land and population through radio rhythm. Earth's 24-hour rotation would become one of the clearest repeated signals. The observer measures a cycle slightly shorter than one local day within its own system. Every 24 hours, certain frequencies return. The pattern shifts slowly through the year because Earth's orbit changes the viewing geometry. Clouds do not affect radio strongly at many frequencies. The artificial rhythm persists through weather. This steady modulation connects technology to the planet's surface. Satellites create faster patterns. A transmitter in low Earth orbit circles the planet in roughly an hour and a half. Its frequency changes rapidly as it approaches and recedes. It appears above the planet's radio horizon, crosses, and disappears. Thousands of such objects create a crowded moving environment. A distant observer with enough angular resolution and sensitivity could recognize that machines orbit Earth. The signals would not remain attached to the surface. They would move around it repeatedly. Natural moons can produce radio emission, but a dense collection of small transmitters following many engineered orbits would be unusual. Some travel in near polar paths. Others remain near the equator. Geostationary satellites circle at a rate matching Earth's rotation, appearing nearly fixed above one longitude. To a remote listener, these objects might form a faint ring of technology. The listener could infer that the civilization uses orbital infrastructure. It may not understand weather forecasting, navigation, communication, or observation, but the arrangement itself shows design. Different orbital families serve different purposes. The geometry is organized. A distant telescope might detect artificial objects, even if their transmissions became quiet. Satellites reflect sunlight. At certain angles, one can brighten briefly. Large solar panels and metallic surfaces create glints. From interstellar distance, individual present-day satellites would be extraordinarily difficult to see. A much larger future satellite population could leave stronger combined effects. A civilization observing Earth across centuries may notice orbital material increasing. The planet becomes surrounded by a thin artificial shell. The shell changes brightness. Some objects enter lower orbits and disappear. Others move outward toward the moon. Technology becomes physically distributed. The listening civilization may compare these observations with its own history. Perhaps every technological society builds satellites early. Perhaps some remain surface-bound. Perhaps orbital activity is rare. Earth's pattern could reveal not only intelligence, but a recognizable developmental stage. This kind of comparison is often imagined through a ladder. A civilization begins by using energy on its planet. Later, it expands across its planetary system. Eventually, it may use a large portion of its star's energy, but development may not follow one universal sequence. Some societies could focus upon computation, others upon biological engineering. Some may use very little energy, some may avoid space. An observer should not assume that Earth will become a larger version of itself forever. It can only measure what exists now. Now, from a nearby star, Earth may appear as one planet surrounded by a modest cloud of machines. The energy use remains tiny compared with sunlight. The artificial heat is faint. Radio and radar provide the strongest clear signs. Spacecraft have reached other planets, but only as small probes. No large habitats occupy the outer solar system. No vast structures intercept the sun. The listener would see a civilization near the beginning of interplanetary activity. Whether that stage lasts centuries or millions of years remains unknown. A distant observer may also detect Earth's deliberate attempts to be heard. Most human transmissions are practical. A few were designed with extraterrestrial recipients in mind. These deliberate messages generally concentrate information and energy towards selected targets. Their structure may be easier to recognize as intentional than ordinary leakage. A listener positioned within the beam could encounter a transmission containing repeated patterns, mathematics, images, or scientific information. Yet the number of such messages is small compared with the number of stars. Their paths form thin cones. Most systems are never illuminated. A deliberate message, therefore, creates a strange asymmetry. It may be easier to recognize. It is much less likely to arrive. Ordinary leakage is more widespread but fainter. Radar is stronger, but narrowly directed. Atmospheric signatures are continuous but difficult to measure. No single technosignature makes Earth obvious from every direction. A capable observer would combine them. Transit data reveal a planet. Atmospheric spectra suggest biology. Radio signals suggest technology. Satellite motion suggests orbital infrastructure. Spacecraft beams suggest exploration. Industrial gases suggest planetary change. Night-side light suggests organized energy use. The evidence forms a layered portrait. Each layer requires a different instrument. The listener may possess a network of specialized observatories. One studies radio. One measures visible light. One observes infrared heat. One tracks planetary motion. One records high-energy events. Data from all of them enter one archive. The civilization does not listen with one ear. It listens with an entire science. Earth may first appear inside separate departments. Planetary astronomers identify the world. Atmospheric researchers discuss oxygen. Radio astronomers report an unusual narrowband candidate. Engineers notice that the signal resembles technology. Only later are the records connected. The artificial radio source follows the same orbit as the oxygen-rich planet. The departments begin communicating. Earth becomes more than one anomaly. It becomes a coherent system. This convergence would matter deeply. A natural event can imitate one sign. Several coordinated signs are harder to imitate. A magnetar can create radio bursts. It cannot easily create artificial atmospheric compounds on a rocky planet. Dust can produce infrared excess. It does not normally create moving communication beams between planets. Lightning can produce radio emission. It does not place transmitters in stable orbits. The complete pattern points toward organized technology. An extraterrestrial listener may therefore know Earth exists without ever receiving a deliberate message. The planet's systems say enough. This raises the possibility that humanity's first contact has already occurred in one direction. Earth may have been detected. No reply has been sent. The listener may still be verifying. It may prefer observation. Its response policy may be slow. The civilization could be separated from us by decades of light travel. Even a message sent immediately may not have returned. Nothing in present silence reveals which stage, if any, has occurred. Perhaps the listener has only one candidate pulse. Perhaps it has confirmed Earth through many technosignatures. Perhaps a reply is moving now. Or perhaps no suitable observer exists within the reached region. Every possibility remains hidden behind the same dark sky. Human imagination often fills that silence with intention. Some imagine caution. Others imagine fear, indifference, protection, or secrecy. Science cannot currently choose among those stories. It can examine what would be physically possible. A passive listener requires no response. A response requires additional action. Listening is therefore easier to imagine as a first step. Humanity already studies potentially habitable exoplanets without sending messages toward each one. We observe, we classify, we debate. A distant civilization may behave similarly. Earth could be one research target among many. Its data may be discussed inside an institution. The observers may disagree. One group considers the radio emission artificial. Another believes the evidence remains insufficient. More telescope time is requested. The planet receives a technical designation. Its cultures, oceans, and living beings remain unknown behind a catalog number. From their perspective, Earth may not be a dramatic discovery yet. It may be a promising candidate awaiting confirmation. This possibility gives a gentle symmetry to the search. Humanity watches distant stars. Perhaps distant stars watch back. Both sides struggle with weak signals. Both must remove interference. Both interpret old light. Both face the same delays. Neither knows what the other is doing now. Two scientific communities could be studying one another's past without realizing the observation is mutual. Earth receives light from their world. Their instruments receive light from ours. Each asks whether subtle changes indicate life. The exchange exists before communication. Observation is the first bridge. A listener may also choose to send a signal only after Earth becomes capable of recognizing it. Sending too early would accomplish nothing. A radio message crossing the solar system 1 million years ago would reach no receiver. A laser pulse aimed at Earth 10,000 years ago would pass above people without telescopes. An intelligent sender may wait until radar or radio leakage proves that the planet possesses suitable technology. Earth's transmissions could function as a trigger. The listener detects organized radio emission. It knows that the local species can build antennas. Only then does it reply. This strategy avoids wasting energy on worlds unable to receive. If such a protocol exists, Earth may have crossed the threshold recently. The first detectable evidence reaches the listener. Its system confirms the source. A response is prepared. The round-trip delay begins. Humanity could be living inside the interval between recognition and reply. The waiting time depends upon distance. For a listener 10 light-years away, a signal produced 10 years ago arrives now. A response sent now reaches Earth 10 years from now. The total interval between transmission and reply is 20 years. At 50 light-years, one exchange spans a century. At 500, it spans a millennium. Only nearby listeners can create responses relevant to present human generations. The nearest stars therefore matter greatly. They receive the strongest and most recent evidence. Their reply times are shortest, but the number of nearby systems is limited. Most contain red dwarfs. Some host known planets. Many remain incompletely characterized. No confirmed technological signal has come from any of them. Still, these are the stars where listening could be most immediate. A listener near Proxima Centauri receives Earth only a little more than 4 years late. It could observe the recent technological planet. A response requires another little more than 4 years. One simple exchange still takes nearly 9 years. The nearest possible conversation would move slowly by human standards, but quickly by galactic standards. A machine could manage such a dialogue across decades. Questions and answers would be separated by years. Each transmission might contain large amounts of information to make the delay worthwhile. A conversation may resemble exchanging libraries. One civilization sends mathematics, biology, history, and questions together. The other studies the message for years before replying. There is no need for rapid speech. The silence between messages becomes part of the structure. If someone is listening right now, it may have no reason to respond with one short greeting. It could spend decades collecting Earth's transmissions. It may attempt to understand our encoding. It could prepare a message designed to survive errors and remain interpretable without shared language. The answer might be long. It might repeat for years. Perhaps it begins with basic signals, counting, geometry, atomic physics, then more complex layers follow. A civilization may transmit the same library in cycles, so that a receiver beginning late can recover the full sequence. The message becomes a lighthouse made of information. No confirmed transmission of this kind has been detected, but thinking about its structure reveals why listening may require patience. A beacon could be operating from one direction while humanity observes it only occasionally. A sequence lasting 100 years might appear incomplete within a 10-minute observation. A narrow slice could look meaningless. Only persistent monitoring reveals the cycle. A listener studying Earth would face the same difficulty. Human communication changes constantly. One brief sample may appear chaotic. Long observation reveals systems. The most effective alien listener may therefore avoid trying to decode individual broadcasts first. It could begin with the large patterns. The planet's rotation, its year, its orbital transmitters, its strongest radar frequencies, its changes across decades. These patterns are easier to establish than language. Once the technological context is secure, the listener may attempt deeper decoding. Human digital communication contains redundancy, repeated formats, error correction, headers, timing standards. The listener may identify recurring structures even without knowing their purpose. Some signals may contain images or audio after reconstruction. Others may be encrypted or compressed beyond easy interpretation. A civilization could learn that Earth communicates richly while remaining unable to understand most of it. It may face the same frustration humanity would face with an alien transmission. Artificiality is the first discovery. Meaning is the second. The listener may also learn through our spacecraft. A signal sent to a probe includes commands designed for machines. The structure may be simpler and more repetitive than entertainment broadcasts. Telemetry returning from spacecraft contains measurements organized into regular packets. A distant eavesdropper could identify communication protocols. It may see one transmitter request information and another respond. The timing creates a relationship. The listener can infer that data are being exchanged. This may be easier than understanding human speech. Machines speak in repeated structures. Their conversation reveals engineering. From far away, Earth's first understandable language may be the language of spacecraft. Another civilization might recognize synchronization pulses, error-correcting codes, binary organization, navigation signals. The exact meaning remains hidden, but the technical logic becomes visible. A receiver could determine that the transmission contains discrete information rather than random variation. The planet's machines demonstrate that someone there understands mathematics. This may be enough to justify a response, or the listener may continue waiting for a deliberate interstellar message. A purposeful beacon aimed at its star would remove doubt. It would show that Earth not only possesses technology, but is attempting contact. Many civilizations may prefer to respond only to direct communication. They may regard accidental leakage as private. Humanity has no way to know. The ethical rules of another intelligence cannot be inferred from physics. Science can identify possible signals. It cannot predict every culture that might receive them. This uncertainty extends to the word listening itself. An extraterrestrial observer may not experience radio as sound. Human receivers convert radio waves into data, and sometimes into audio for convenience. The listener may perceive electromagnetic patterns through senses or instruments entirely unlike ours. It could be biological, mechanical, or both. Its astronomy may have developed through another route. Perhaps its species evolved beneath an ocean and discovered radio only after building machines above the surface. Perhaps it lives under permanent cloud cover and learned about stars through radio before visible light. Perhaps it occupies artificial habitats and has no natural sky. Its idea of listening may be mathematical. A stream of measurements enters a network. Patterns alter internal models. There may be no individual moment of hearing. Earth simply becomes known. This perspective makes the title question broader. Is someone listening to Earth right now? Perhaps no one is consciously attending, yet a machine may be recording. An automated survey could be collecting every signal from the sun. The data may not be reviewed for centuries. Would that count as listening? From Earth's perspective, our transmissions have entered another technology. They have been preserved. The audience may come later. The first recognition could occur long after the signal arrives. A researcher studies old observations. An algorithm identifies a pattern. The radio history of Earth becomes a discovery in retrospect. The listeners may be separated from the original receiving moment by generations. Information waits inside archives more easily than it waits in space. Once recorded, the signal can be replayed, reanalyzed, compared. The brief beam no longer vanishes. A civilization with deep archives may eventually discover every strong Earth signal that crossed its system, even if no one noticed at the time. The galaxy could contain dormant evidence of Earth, in places where the receiving civilizations have not yet learned to interpret it. This possibility also applies here. Human archives may contain signals whose significance remains unknown. Most unusual candidates become interference or natural events. None has been confirmed as extraterrestrial technology, but the ability to revisit data means listening can continue after the telescope stops pointing. The act of observation creates a record for future knowledge. Perhaps another civilization values archives for exactly this reason. Its receivers record broadly. Nothing is discarded completely. Future algorithms search the past. Earth's signal becomes more recognizable as their science improves. The discovery may occur centuries after our radio beam crossed their world. A reply sent then would arrive even later. Contact is delayed not only by light travel, but by recognition. One civilization may already have heard the other without knowing it. The silence continues until understanding catches up. All of this remains within possibility rather than evidence. No telescope has shown that Earth is being monitored. No message has demonstrated knowledge of our broadcasts. No confirmed extraterrestrial receiver is known. The scientific conclusion remains unchanged. Humanity does not know whether anyone is listening, but the physical pathways are clear enough to examine. Earth emits, signals travel. Nearby systems receive some of them. Sensitive instruments could detect the strongest examples. Long observation could reveal planetary motion and technological change. A distributed array could separate Earth from the Sun. A machine could wait longer than one biological lifetime. A reply could remain in transit. The question is not impossible. It is unanswered. Somewhere beyond the solar system, a receiver may be facing this star. Its data stream may contain a faint, narrow line. The line drifts. It repeats according to a small planet's orbit. Other signals appear from machines moving around that world. The listener may have reached no conclusion yet. It may label the source uncertain, or perhaps the evidence has already become enough. The planet is classified as technological. Its atmosphere is marked as biologically interesting. Its signal history grows with every passing year. Earth continues speaking without knowing who receives it. The transmissions leave antennas, satellites, radar systems, and spacecraft. They cross the planetary system. They spread into the dark. Most will fade beneath noise. Some will pass through empty space. A few may touch another world. And if a receiver is waiting there, the quiet act of listening could already be underway. Earth does not always speak by accident. Sometimes humanity has chosen to address the unknown directly. A transmitter is aimed toward the sky. Information is arranged deliberately. The message is designed not for a satellite, aircraft, or spacecraft, but for a possible intelligence that has never been seen. These moments are rare. Most of Earth's radio energy serves local purposes. It measures asteroids, guides vehicles, connects machines, or carries information between points on and near the planet. Only a small number of transmissions were created specifically for an extraterrestrial receiver. They belong to a different kind of activity. Listening for another civilization is usually called SETI. Intentionally transmitting toward one is often called messaging to extraterrestrial intelligence, or METI. The two activities are connected, but they are not identical. Listening attempts to discover what may already exist. Messaging attempts to create a new opportunity for discovery. A distant observer could notice both deliberate and accidental emissions, but a deliberate message may contain features designed to make its artificial origin clearer. It can repeat, it can count, it can organize information around physical principles shared by observers anywhere in the universe. It may begin by teaching the receiver how to read it. If someone is listening to Earth right now, a deliberate message could be the clearest evidence that the planet is not merely technological. It is curious. It is looking outward. Long before humanity transmitted an intentional radio message, it attached physical messages to spacecraft. Pioneer 10 and Pioneer 11 each carried a small metal plaque. The plaque included representations of a human man and woman, the arrangement of the solar system, and a diagram locating the Sun relative to 14 pulsars. The spacecraft were not sent toward a known inhabited planet. Their plaques were intended for the unlikely possibility that another spacefaring intelligence might encounter them in the distant future. A physical message moves very differently from a radio signal. Radio crosses interstellar space at the speed of light. A spacecraft travels much more slowly. Pioneer and Voyager require thousands of years merely to pass through distances comparable to those separating nearby stars. They are also tiny compared with the space through which they move. A receiver does not need to be aimed at them, but someone must come extremely close to find them. A plaque can survive after its transmitter has disappeared because the plaque is the transmitter. Its materials hold the information. It does not need power. It does not need to repeat. It simply continues moving. If discovered after 1 million years, the plaque would still say that one technological species once lived near the Sun. The species itself might no longer exist. Earth might have changed. The message would become archaeology. Voyager 1 and Voyager 2 carried a much richer physical record. Each spacecraft holds a 12-inch gold-plated copper disc containing sounds and images intended to portray the diversity of Earth's life and culture. The records include natural sounds, music, spoken greetings, and images representing organisms, landscapes, science, human activity, and the planet itself. Diagrams on the protective cover explain how the record may be played and use physical references to indicate its origin and timing. The golden records are often described as messages to extraterrestrials. They are also messages about humanity. They reveal what their creators considered worth preserving. Wind, rain, heartbeat, music, language, mathematics, families, animals, the curve of Earth beneath the darkness. A civilization that recovered one Voyager would learn that its builders understood physics well enough to leave their planetary system. It would also learn that those builders wished to be understood. The record is not only technical evidence, it is an act of introduction. Yet the chance of discovery is extraordinarily small. Interstellar space contains no roads. The spacecraft do not pass through a busy harbor where travelers gather. They move through immense volumes where even planets occupy almost no space. A receiver would need to cross very near one small machine or deliberately track it from a distance. The Voyager records may continue surviving long after Earth's radio signals have faded, but survival and discovery are different things. A book can remain intact inside a vast library while never being opened. The first famous deliberate radio message traveled much faster. On November 16, 1974, the Arecibo radio telescope transmitted a brief message toward the globular star cluster Messier 13. The message contained 1,679 binary bits. That number can be divided into 23 by 73, two prime numbers. When arranged into the intended rectangular grid, the bits produce a simple image representing numbers, chemical elements important to terrestrial biology, DNA, a human figure, the solar system, and the Arecibo telescope. The transmission lasted less than 3 minutes. The Arecibo message is often imagined as the beginning of a conversation. Its destination makes that conversation extremely slow. Messier 13 lies tens of thousands of light-years away. The transmission has traveled only a little more than 50 light-years since 1974 and remains nowhere near the cluster. Even if a receiver eventually detected it and replied immediately, the round trip would take roughly 44,000 years. The message was therefore more demonstration than practical dialogue. It showed that humanity could encode information into a powerful interstellar transmission. It tested how a simple picture might be built from binary choices. It asked what could be communicated without a shared language. The intended receiver was hypothetical. The waiting time extended beyond any institution, nation, or civilization that presently exists. A response would belong to distant descendants. The act of sending became more immediate than the possibility of receiving. From the perspective of a distant listener, the Arecibo message would differ from ordinary leakage. It was concentrated. It came from one powerful instrument. It used a structured sequence. It contained a number of bits chosen so that two prime dimensions could organize the information. The receiver would still need to make several correct assumptions. It must notice the signal. It must preserve enough detail. It must identify the binary changes. It must try arranging the sequence geometrically. It must choose the correct orientation. Even after recovering the image, it must interpret unfamiliar symbols. A shape intended to represent a human may look obvious to humans because we already know what a human body looks like. A listener with another form of perception may not immediately recognize it as an organism. A diagram of the solar system assumes that the observer understands the relationship between the symbols and physical objects. The DNA representation assumes knowledge of molecular chemistry. Meaning is not carried only by information. It also depends upon the receiver's model of the world. This creates one of the central difficulties of interstellar communication. Mathematics may be universal. Symbols are not. 2 + 2 has the same relationship anywhere in the universe. But the marks used to express that relationship arise from culture, anatomy, and history. Humans write numbers using lines and curves. Another intelligence may represent quantity through sound, timing, spatial arrangement, chemical changes, or patterns distributed across several dimensions. A message must create common ground before it can rely upon shared meaning. A carefully designed transmission might therefore begin slowly. 1 pulse, then 2, then 3. The sequence repeats. Pairs of pulses introduce grouping. Prime numbers introduce structure. Regular intervals establish a unit of time. A known atomic transition could provide a physical reference. The message gradually teaches its grammar. Only after the receiver has recognized counting and measurement would more complicated information begin. The transmission might describe simple geometry, a line, a circle, ratios, the relationship between wavelength and frequency, the orbit of the sender's planet. The structure could grow like a bridge assembled from both sides. Each new concept rests upon one already established. This is why repetition would matter. Interstellar space is not perfectly empty. Signals pass through plasma, dust, magnetic fields, and the noisy environments of stars and planets. A receiver may miss part of the transmission. One pulse may be weakened, another may be distorted. If the message is sent only once, missing information can remain missing forever. Repeated blocks allow the listener to compare several copies. An error in one copy may be corrected using another. Human communication already uses redundancy for similar reasons. Spacecraft transmit data with error-correcting codes because weak signals can be damaged during their journey. A message to another star would face an even longer path. The sender might repeat the complete transmission for months, years, or centuries. A distant listener beginning halfway through could wait for the sequence to restart. The message would become cyclical. It would not depend upon one perfect moment. The Arecibo message did not repeat for centuries. It lasted for less than 3 minutes. A listener outside its narrow beam would receive nothing. A listener inside the beam but observing at another time would also receive nothing. Its detectability depended upon one alignment of direction and time. This is the same challenge facing most of Earth's strongest emissions. Power can overcome distance. It cannot overcome being pointed elsewhere. A long-lived beacon would use more energy, but it would increase the chance of discovery. It might scan nearby stars one by one. The beam remains on one system for several minutes or days. Then it moves. After completing the list, it begins again. A listener may wait years between repeated visits, but the return itself becomes evidence. The same narrow signal arrives from Earth's direction. Its timing follows a deliberate schedule. The receiver can predict the next appearance. Prediction changes a candidate into an experiment. A natural burst can occur once. An artificial beacon can keep an appointment. Humanity has not built a continuously operating interstellar beacon of this kind. Most deliberate messages have been brief. Earth's more detectable signals often come from radar systems created for completely different work. A 2025 analysis comparing Earth's technosignatures concluded that powerful planetary radar would be detectable from much farther away than atmospheric pollution, city lights, or ordinary communication leakage when judged using technology comparable to our own. The same research emphasized that the strongest signals are directional and would be seen only by observers placed within their beams. This creates an interesting contrast. The signal most likely to reveal Earth may not be the signal designed to introduce it. A radar pulse intended to study an asteroid can travel farther than a symbolic interstellar message. The listener may detect the instrument before the greeting. It sees evidence of measurement without receiving the explanation. The planet appears intelligent through its ordinary activity. A deliberate message would provide context. It might tell the listener where the sender lives. It could describe the planet. It may indicate that the transmission is intentional and that a response is welcomed. Without that context, the listener must infer everything from behavior. A radar beam says, "A powerful transmitter exists." A structured message says, "A transmitter exists and is attempting to be understood." That difference may influence whether another civilization answers. An observer could detect Earth's technology and still remain uncertain about our desire for contact. Accidental leakage is not necessarily an invitation. Humanity intercepts natural and artificial signals without assuming that the sender wishes to speak with us. A spacecraft communicates with Earth because it was designed to do so. A military radar may be powerful, but it was not created for listeners among the stars. Another civilization may distinguish between visibility and consent. It could choose to remain silent until Earth sends a clear message toward its system. Perhaps this is already happening. A distant observer has confirmed that Earth contains radio technology. It has measured our orbit. It recognizes radar beams. But it has not received a deliberate signal aimed at its star. Its own rules require an invitation. The listener waits. Earth interprets the silence as absence. Both sides behave cautiously. No physical evidence shows that this scenario is real, but it demonstrates how silence can emerge even when technology exists on both worlds. The problem is not only detection, it is uncertainty about intention. Another civilization might reach the opposite conclusion. It may consider any technological emission an invitation to study. The first radar pulse is enough. Its instruments turn toward Earth. A beacon begins transmitting. The reply is aimed toward the predicted position of the planet, but the message still requires years to arrive. The listener has answered. Earth remains unaware. A civilization 10 light years away receives a strong signal 10 years after it leaves Earth. If it responds immediately, Another 10 years pass before the answer reaches us. A 20-year gap separates cause and effect. During that interval, the transmitter on Earth may be dismantled. The original researchers may retire. The frequency may no longer be monitored. A response can return to a planet that has forgotten exactly what it sent. This makes archives important. Every deliberate transmission should be recorded precisely. Direction, frequency, bandwidth, time, power, encoding, duration. The receiving generations may need those records decades or centuries later. A signal arriving from one star could be compared with an outgoing message sent toward that star in the past. The timing might match the earliest possible response. Elements of the return transmission may repeat or transform parts of the original. The connection could become visible only because the old message was preserved. A reply may begin by echoing. The listener receives a sequence. It sends the same sequence back. Then it adds something. The echo proves reception. The addition begins communication. This would be one of the simplest ways to show that the message was understood as a message. Human radio systems use acknowledgement signals for similar reasons. A machine sends information. The receiver confirms that the information arrived. Across interstellar space, the acknowledgement may take decades, but its logical purpose remains the same. A listener could also answer by changing the signal in a predictable way. The sender transmits the first 10 prime numbers. The receiver returns the sequence and continues it. The continuation reveals understanding, or it may correct an error introduced intentionally as a test. A conversation begins through shared structure rather than language. The first exchange may contain almost no cultural information. It establishes only that two systems can recognize the same mathematical relationships. This alone would transform the question of whether humanity is alone. Later messages could become much more ambitious. A civilization might transmit a description of its star system, orbital periods, planetary sizes, atmospheric chemistry, the properties of its biology, if biology still exists there. It could describe its own methods of measurement, using universal constants. Images may be encoded after the receiver learns how dimensions are arranged. Sound would be more difficult because another species may not hear through pressure waves in an atmosphere. But the physical structure of the waveform can still be transmitted. The recipient may reconstruct it as data, without experiencing it in the human way. Humanity's own messages reveal how difficult representation can become. The golden record includes photographs because humans rely heavily upon vision. It includes audio because humans perceive sound. It depicts bodies from one angle. Another intelligence may not interpret flat perspective naturally. Its world may have no transparent atmosphere. Its organisms may understand surroundings through electrical fields, pressure, chemistry, or senses humans do not possess. The record would still reveal design. Its exact meanings could remain partly inaccessible. Communication does not require complete similarity. It requires enough overlap. Physics provides one overlap. Chemistry may provide another. Astronomy provides a shared sky, though viewed from different locations. The sender and receiver can describe pulsars, atomic frequencies, and planetary motion. Their emotional worlds may remain separate. Their mathematics can meet first. This is one reason some researchers prefer searching over transmitting. A detected message would provide clues about the sender's method. Humanity could learn the signal's frequency, structure, repetition, and apparent purpose before deciding how to reply. A transmission sent into silence must guess everything. The target may be uninhabited. It may use different technology. It may not observe at the chosen time. The message could cross the system completely unnoticed. Listening conserves energy and avoids assumptions. But a galaxy in which every civilization listens and none transmits would remain silent forever. Every receiver waits for a sender. Every world concludes that no one is there. This tension lies near the center of the SETI debate. Some researchers argue that communication requires someone to transmit deliberately. Others argue that powerful messaging should involve broad international discussion, because the outcome of contact cannot be predicted, and one group's transmission could represent the entire planet without global agreement. The debate includes scientific, ethical, cultural, and political questions rather than one settled technical answer. There is currently no confirmed extraterrestrial civilization to message. The debate therefore concerns uncertain future possibilities. Its participants agree upon at least one physical reality. Once a radio message leaves Earth, it cannot be recalled. The wave continues outward, A decision lasting minutes can create a signal traveling for centuries. The transmission becomes part of the planet's astronomical history. This permanence encourages care. What should Earth say? Who decides? Should the message present humans as individuals, nations, or one planetary species? Should it include our conflicts, our biology, our art, our scientific knowledge? Should it reveal the exact location of Earth, even though many existing emissions already originate from here? A message containing only mathematics may be safe from cultural disagreement but incomplete. A message containing culture will reflect the choices of its creators. No finite transmission can represent every life on Earth. The Voyager Golden Record faced the same limitation. Its contents form a portrait, not a complete planet. Any interstellar message is an act of selection. What is included becomes visible. What is excluded disappears. Perhaps another civilization has faced this question already. Its first message may represent one institution rather than its entire world. The sender may not speak for every intelligence there. A signal could come from scientists, machines, artists, governments, isolated settlements, or an automated beacon built by ancestors. Humanity should not assume that one transmission expresses one unified civilization. Earth itself is not unified into one voice. An extraterrestrial world may be equally complex. This possibility would shape interpretation. A welcoming signal might come from one group. Silence from the rest does not imply agreement. Several transmitters might send conflicting messages. One invites contact, another asks for distance, a third transmits only data. The first discovery of extraterrestrial technology could therefore reveal diversity immediately. Intelligence may not arrive as one calm planetary statement. It may arrive as overlapping signals. No present candidate shows such behavior, but considering it prevents the word civilization from becoming too simple. A technological world may contain many intentions. A listener monitoring Earth would already see evidence of this complexity. Our radio environment is not coordinated as one interstellar beacon. Different systems transmit for different purposes. Frequencies overlap, signals begin and end independently. Some are civilian, some are scientific, some are navigational. Some are private or encrypted. The planet's radio output resembles a crowded landscape rather than a single speaker. An advanced observer may infer that Earth contains many networks. It could discover disagreement before language. One transmitter broadcasts continuously, another interferes. One country operates radar, another builds satellites. The structure reveals a world composed of many actors. This may make the listener more cautious. Which signal should it answer? A deliberate message can simplify the problem. It provides one identifiable transmission. Its direction and structure show that at least one group on Earth seeks communication. The listener may respond to that message rather than to the planet as a whole. The answer could be addressed technically: a frequency, a timing pattern, a reference to the original sequence. The first interstellar contact might begin between instruments before it begins between societies. A telescope sends, a telescope receives. Researchers confirm the relationship. Only later does the wider meaning reach the world. If an answer arrived, scientific verification would be essential. Terrestrial interference, satellites, instrument errors, and natural astronomical sources can imitate parts of a technological signal. The International Academy of Astronautics has maintained and updated principles encouraging careful verification, continued monitoring, transparent reporting, and independent confirmation of a possible extraterrestrial detection before it is treated as established. A response would be a separate decision. Detection asks what the signal is. Replying asks what humanity should do. The first can be approached through measurement. The second involves values. There would be no need to answer within minutes. Interstellar distances provide time. A signal that traveled for decades will not be harmed by several months or years of careful study. Researchers could determine its direction. They could examine whether it repeats. They might identify its internal structure. The scientific community could test every known terrestrial and natural explanation. Humanity could listen before speaking. This patience might be exactly what another civilization expects. A well-designed beacon may repeat for years. The sender understands that receivers require confirmation. The message may begin with a long announcement sequence. Simple pulses repeat. The exact coordinates of the source become measurable. Only after that preamble does the information become more complicated. The sender builds verification into the transmission. It makes the signal easy to discover before making it difficult to understand. A civilization hoping to be heard would probably consider the receiving process. Its engineers may ask the same questions humans ask. Which frequencies pass through interstellar space effectively? Which signals stand apart from stars? How much energy is required? How long should the beacon repeat? What patterns are likely to be recognized? Where should the transmission point? The final design may be unfamiliar, but the physical constraints are shared. Energy remains finite. Noise remains present. Distance remains large. A narrow beam remains efficient. Repetition remains useful. The listener around another star could recognize these practical choices. It may not know the sender's culture. It knows the signal was built to travel. Earth's deliberate messages have rarely offered this level of persistence. The Arecibo transmission was powerful but brief. The Pioneer plaques and Voyager records are rich but almost impossible to encounter by chance. Humanity has created introductions without constructing a permanent interstellar presence. The planet speaks in occasional moments. Most of the time, it leaks. If someone is listening right now, accidental technosignatures are still more likely to attract attention than our symbolic messages. A radar beam may cross the listener's system. A spacecraft transmission may align with its planet. Industrial chemistry may appear in Earth's spectrum. The deliberate messages form only thin threads among these wider signs, yet their existence reveals something important about the civilization that produced them. Humanity is not merely detectable, it has imagined a receiver. Long before confirming anyone beyond Earth, people constructed messages for them. The plaques, records, and radio sequences were created for beings who might never exist. This is a unique kind of technological behavior. A machine can transmit accidentally. Curiosity transmits deliberately. Perhaps another listener would recognize this difference. It receives one structured sequence from the sun's direction. The message does not resemble ordinary radar. Its length and arrangement appear chosen. Simple mathematics leads into chemistry. A figure appears. A planetary system is represented. The observer realizes that the sender is not only using technology, it is thinking about unknown minds. For the first time, Earth is not merely seen, it is introducing itself. Would the listener answer? There is no scientific way to know. It may be unable. The civilization could have ended after building the receiver. Its automated system may record but not transmit. The signal could be too weak to interpret confidently. A response may require technology it does not possess. It may decide to wait for repetition. It may answer immediately. The reply may already be moving, or no receiver may exist within the beam. Every outcome appears identical from Earth until another signal arrives. This is why deliberate messaging does not guarantee contact. It creates one opportunity. The universe still contains distance, timing, noise, and uncertainty. A message can cross a living world while its telescopes face elsewhere. It can reach an intelligent species before it invents radio. It can arrive after its receivers stop operating. It can be recognized as artificial but remain undecoded. It can be decoded and left unanswered. Between transmission and response lies an entire chain of possible silence. Perhaps the most successful message would not be the most detailed one. It would be the easiest to notice. A simple beacon could repeat from a nearby star. Once attention is established, more information follows. Humanity's first goal would not be to explain every part of Earth. It would be to create certainty. A signal that says, through its behavior, this is not a star. This is not interference. This is not a natural pulse. This was sent. The rest can come later. A listener observing Earth may be waiting for exactly this distinction. Our radar is powerful. Our atmosphere is unusual. Our satellites are organized. But none of them clearly announces that we know another observer may exist. A deliberate repeated beacon would do so. It would transform technological leakage into intentional presence. For now, Earth has sent only scattered introductions. One plaque crosses the dark. One record carries rain, voices, and music. One radio image travels slowly toward a distant cluster. Other brief transmissions move toward selected stars. Most possible worlds receive nothing. The planet continues speaking mainly to itself, but every outward message changes the solar system in one small way. Before it, the information existed only here. After it, the information moves between stars. it becomes possible for another intelligence to know something about Earth that Earth intentionally chose to share. Somewhere inside one narrow beam, the message may eventually reach a receiver. The instrument records a sequence. The sequence is arranged. The arrangement becomes an image. The image shows a small figure beside a star system. The listener understands only part of it, but one meaning is clear. The signal did not happen by accident. A planet far away knew enough to wonder whether anyone was listening. And perhaps beneath another sky, the answer begins with a transmitter turning quietly toward the sun. If another civilization decides to answer Earth, it cannot simply point a transmitter toward where the planet appears to be. By the time a signal arrives, Earth will have moved. The planet travels around the sun. The sun moves through the Milky Way. The distant star moves as well. Interstellar communication requires prediction. A transmitter must aim toward the place where Earth will be when the message reaches the solar system. This is not beyond known physics. Human engineers already predict the future positions of planets and spacecraft. Radio antennas send commands toward machines that may be hundreds of millions of kilometers away. The beam is directed not toward where the spacecraft was when its light left, but toward where calculations show it will be when the transmission arrives. The same principle works between stars. The distance is greater. The prediction stretches across years or centuries. A listener 10 light-years away sees Earth as it appeared 10 years ago. If it chooses to reply, it must calculate Earth's position 10 years into its own future. The message then crosses space and arrives here. The sender never sees the arrival directly. It sees only an earlier version of the planet. Yet orbital mechanics allows the future path to be estimated. Earth moves around the sun in a stable and measurable rhythm. Its year repeats. Its position can be projected. A civilization that has observed the solar system long enough could aim accurately. It may already know the orbits of Earth, Venus, Mars, Jupiter, and the outer planets. It could predict where the sun itself will move against the background stars. The challenge is not knowing the general destination. The challenge is making the beam wide enough to ensure that Earth remains inside it. A narrow beam saves energy, but a beam that is too narrow could miss. Small errors in distance, motion, or timing become large across interstellar space. The sender may therefore choose a compromise. It could widen the beam slightly. It may repeat the message while sweeping across a small region. It could transmit towards several predicted positions. Instead of one thin thread, the response becomes a fan of light or radio energy covering the area through which Earth is expected to pass. A deliberate reply may also target the sun rather than Earth itself. The sun is brighter and easier to locate. A signal aimed toward the solar system can reach receivers near Earth, even if the beam is centered on the star. The sender may assume that a technological civilization monitors its own star's surroundings. Human observatories already search near stars because planets, spacecraft, and possible transmitters remain close to them in the sky. A strong signal arriving from the direction of the sun would create practical difficulties, however. The sun produces natural radio energy. Its light overwhelms nearby optical sources. An artificial transmission must distinguish itself from that background. Narrow frequencies help. Precise pulse timing helps. Repetition helps more. A listener attempting to answer may choose a part of the radio spectrum where the sun is relatively quiet. It may select frequencies that pass through interstellar gas and planetary atmospheres efficiently. It could transmit several channels at once. One frequency attracts attention. Another carries information. A third repeats a simple reference pattern. The reply may not be one signal. It may be a structure. Imagine 3 narrow radio lines appearing together. Their frequency spacing follows a simple ratio. The first remains steady. The second pulses. The third changes in a sequence. Natural radio sources can produce many spectral lines, but a group arranged by precise mathematical relationships could suggest design. The sender might use the frequencies of hydrogen or other common atoms as reference points. A listener anywhere in the universe can measure the same physical transitions. The exact units may differ. The underlying ratios remain. This offers a way to construct an interstellar address. The message says, in effect, begin here. Use this natural frequency as a ruler. Measure the spaces between the signals. The arrangement itself becomes the first sentence. The receiver does not need to understand a language. It only needs to notice that the pattern appears selected. The response may begin with an echo. This is one of the clearest possible forms of acknowledgement. A civilization detects a deliberate transmission from Earth. It records the sequence. Then it sends the same sequence back. The echo may be exact, or it may be shifted to another frequency. Perhaps it repeats the original signal 3 times. Then it adds a new pattern. The return section proves that the sender received something from Earth. The added section proves that it did more than reflect the signal naturally. It processed the information. This distinction matters. Radio waves can reflect from planets, moons, plasma, and artificial satellites. A simple echo does not automatically show intelligence, but an echo altered in a meaningful, organized way would be different. Suppose Earth sends the numbers 1 through 10. The reply returns the sequence, and then continues to 11, 12, and 13. Or Earth sends the first prime numbers. The reply echoes them and adds the next prime. The receiver has not merely bounced the signal, it has recognized a rule. Recognition creates the beginning of communication. A reply could also refer to Earth's transmission through timing. Perhaps the original message lasted 1679 units. The response begins after 1679 equal intervals. Perhaps it repeats a section backward. Perhaps it mirrors the arrangement. The sender demonstrates that it understood the structure without yet revealing anything about itself. The first contact may therefore begin like a test between 2 machines. One pattern is sent, another pattern returns. Each side establishes that the other can measure, compare, and respond. Only later do descriptions of planets, biology, or culture begin. This approach reduces misunderstanding. It builds a shared foundation, one step at a time. A listener may not answer immediately. Verification could take years. One unusual signal from Earth may not be enough. The observer must exclude natural events and local interference. It may wait for repetition. It could compare several instruments. The signal might be studied by different scientific groups. Some may consider it artificial. Others may remain uncertain. A response could be delayed not by distance but by caution. Humanity would probably behave similarly. A single strange pulse would not lead immediately to an interstellar message. Researchers would observe again. They would check satellites and transmitters. They would compare telescopes. They would investigate the star. Only after evidence accumulated would a reply become a serious question. Another civilization may require even stronger certainty. Its historical experience may encourage patience. Perhaps it has encountered many natural phenomena that once looked artificial. Its scientists may demand decades of data. They could wait until Earth's transmissions display a consistent technological history. Radar appears. Satellites appear. Messages are sent deliberately. The evidence becomes difficult to dismiss. Then the civilization decides that the planet is real, technological, and capable of receiving. The reply begins long after the first detection. From Earth, the delay appears even longer. A radio signal travels 30 years. The observer studies it for 20 years. Its reply travels 30 years back. 80 years pass between cause and response. The people who created the original transmission may never hear the answer. Their children might, or their grandchildren. The conversation belongs to institutions rather than individuals. Interstellar communication rewards civilizations that preserve memory. Records must survive. Transmitters must be remembered. Future receivers must know which frequencies were used and which stars were targeted. Without that continuity, a reply could arrive as a complete mystery. The original message was sent. Generations pass. The observatory closes. The data are stored poorly. A return signal appears from the target star. No one immediately recognizes the connection. The answer may be received without being recognized as an answer. This possibility makes archives part of contact. Every deliberate transmission creates a future obligation. The planet must remember what it said. A civilization that communicates across centuries needs a long cultural memory. It must preserve astronomical coordinates despite the motion of stars. It must translate old encoding systems. It must keep the meaning of its own message accessible. Otherwise, the reply returns to strangers. Those strangers still live on Earth, but the sender's culture may feel ancient to them. The answer becomes an archaeological object from both worlds. One civilization speaks from its past. The other receives through its future. This is true, even when the distance is small. At Proxima Centauri, the nearest possible exchange still spans almost 9 years. A message sent during one stage of human history could return during another. At 50 light-years, a complete exchange spans a century before any additional delay is added. At 500 light-years, the response belongs to a different millennium. The sender must accept that it cannot control the civilization that eventually receives the reply. It can only place information into time. A listener may choose to send something durable and simple. Because of this, a detailed message could depend upon assumptions that future humanity no longer shares. A basic mathematical beacon remains understandable. The sender may repeat it for decades. Even if technology changes, the pattern remains visible. A reply could also be aimed not at the present Earth, but at the future development of the solar system. A civilization observing human spacecraft may predict that receivers will eventually exist on the Moon, Mars, or in deep space. It could send a wide signal covering the inner solar system. The message may arrive where humanity is expected to expand. Perhaps Earth's surface is not the best target. The planet's atmosphere absorbs some frequencies. Human radio interference is intense. A receiver on the far side of the Moon would be quieter. An advanced listener may infer this before humans build the observatory. It could direct a low-frequency message toward a region near the Moon, assuming that any developing civilization will eventually place instruments there. The answer would wait not in time, but in geometry. The signal crosses the solar system repeatedly. A future lunar telescope begins operating. For the first time, the civilization is capable of hearing it clearly. The sender may have begun transmitting centuries earlier. This possibility resembles placing a message at a technological milestone. The recipient receives it only after building the correct instrument. The message appears to arrive at exactly the right moment. In reality, it has been present all along. Humanity simply lacked the receiver. Another civilization could use several such milestones. A radio beacon becomes detectable when large antennas are built. An optical pulse becomes detectable when fast photon counters appear. A signal at very low radio frequency becomes visible when observatories move beyond the atmosphere. A weak probe becomes discoverable when asteroid surveys become complete. The answer may be layered according to technological ability. A young civilization detects only the first layer. A more advanced one discovers more. This idea remains speculative. There is no evidence of such a beacon, but it illustrates how another intelligence might communicate without knowing exactly when Earth develops each technology. The sender builds the message into the environment. The recipient encounters it when ready. A reply may also use the Earth transit zone. A civilization that sees Earth cross the Sun knows the exact geometry of the planet's orbit. It can time a transmission so that the signal arrives during one of those transits. From the sender's perspective, Earth moves across the Sun. A pulse arrives as the planet enters the stellar disk. Another arrives at the center. A third arrives as it leaves. The timing maps the shape of the transit. The message demonstrates knowledge of Earth's orbit. A natural source would need an extraordinary coincidence to synchronize repeatedly with the planet's motion. Human astronomers could notice that the signal returns once each year at the same orbital phase. The source may lie in the same star system from which the Earth transit is visible. The message says, "We see your planet. We understand its path." This form of communication does not require the sender to have received a deliberate human message. It could discover Earth through transit observations. Radio leakage later confirms technology. Then it transmits during the same geometric event that first revealed the planet. The transit becomes both discovery method and communication clock. The sender might choose other shared events. A solar eclipse visible from Earth, a close approach of Mars, a predictable pulsar pulse, a supernova in a known direction. Astronomical events provide clocks available to both civilizations. The sender can say, "Listen when this happens." The receiver can verify that the timing is intentional. Pulsars may be especially useful. Their pulses are stable and measurable across long timescales. A message could arrive at selected intervals after a known pulsar pulse. The pulsar acts like a universal metronome. Both civilizations observe the same object, though the pulse reaches them at different times depending upon location. With enough astronomical knowledge, the delay can be calculated. The sender may identify itself through a pattern involving several pulsars. This resembles the pulsar maps engraved on the Pioneer plaques and Voyager records. Those maps use the periods and positions of pulsars to locate the Sun. A radio reply might use related information dynamically. The signal could pulse according to the periods of selected neutron stars. The pattern tells the receiver where to look. It may even indicate when the message was created. Because pulsar periods change slowly, a listener could determine the age of the signal design. A reply may therefore contain a timestamp built from the galaxy itself. This could matter if the beacon is automated. An ancient transmitter may continue operating long after its creators disappear. The signal includes enough information to show when it was programmed. The civilization described in the message may no longer exist in the same form. The reply becomes a voice from deep time. The listener on Earth may receive a perfectly active signal from a silent world. Technology can continue after biology ends. A beacon powered by starlight could operate for thousands or millions of years if it repairs itself. It might repeat one introduction indefinitely. The builders may have intended it as a monument or as insurance against disappearance. The message says, "We existed. This is what we learned. This is where we lived." Do not mistake silence now for absence then. If such beacons are possible, a listener may answer Earth without being alive in the familiar sense. The transmitter could be an archive. Its response may be automatic. It detects organized radio from a new world. It activates a stored sequence. No present society chooses to speak. A machine follows instructions written in the distant past. The first extraterrestrial contact could therefore be with history. Humanity may ask questions. The beacon may be unable to answer anything outside its original design. It could repeat the same information. It may describe a civilization that vanished before Earth developed complex life. The conversation would be one-sided, but the discovery would remain profound. An automated listener may have more flexible intelligence. It could analyze human signals. It may construct replies based upon what it learns. The machine could adapt language gradually. It might begin with mathematics. Later messages incorporate patterns found in Earth's own transmissions. Perhaps it identifies binary encoding, then images, then spoken languages. A nearby automated probe could learn more quickly than a distant civilization because it receives stronger signals. A distant observatory might still perform similar analysis over decades. The listener may use Earth's broadcasts as a library. Television, radio, satellite communication and digital leakage contain enormous amounts of information. Most are faint at interstellar distance, but a sufficiently advanced receiver could collect fragments. Language appears as repeated sound patterns. Images contain recurring shapes. Certain individuals appear many times. Astronomical maps and scientific diagrams may be especially valuable because they connect symbols to measurable reality. The listener could begin building a translation system. A reply might then use a human language. This possibility is often imagined dramatically. A signal arrives in English, Arabic, Mandarin, Spanish, or another language. It refers to Earth directly. Such a message would strongly suggest that the sender has monitored human communication, but language changes. A civilization receiving broadcasts from 50 light-years away hears Earth from the 90s. Its reply uses language and cultural references from that period. The answer returns 50 years later. Humanity receives a message shaped by a century-old version of itself. The sender studied our past and spoke to our future. The reply might mention technology that no longer exists. It could use words whose meanings have changed. It may address political states or institutions that have disappeared. The message would feel both alien and historical. A response in human language would also create questions about interpretation. Did the sender understand the meaning deeply, or did it imitate patterns statistically? A machine can reproduce language without sharing human experience. The reply may be grammatically precise while misunderstanding emotion, metaphor, or culture. Communication could begin with fluency but still contain enormous gaps. The same would be true in reverse. Humanity may decode an alien message without understanding the world behind it. A word translated as water could refer to a liquid, unlike ordinary water. A concept translated as individual may not match human identity. A statement about life may include artificial systems. Shared language does not guarantee shared meaning. This is why scientific information may come first. The mass of a planet, the period of an orbit, the wavelength of a signal, the ratios of chemical elements. These quantities can be tested. If the sender describes its star, astronomers can compare the message with observation. Accuracy creates trust. The reply says that one planet circles every certain number of time units. Human telescopes detect the same period. It describes an atmosphere. Spectroscopy confirms some gases. The message and the sky agree. The receiver begins to know that the information refers to a real place. A listener answering Earth may include a map, not a drawn map in the human sense, a set of distances and directions to pulsars, the properties of nearby stars, the timing of planetary orbits. From this information, astronomers reconstruct the source system. The signal may arrive from one direction, but the map confirms its origin independently. This would help if the transmitter is a relay or probe located away from the home world. The message could say, "The beacon is here. The builders came from there. Their present location is elsewhere." Technology may separate origin, transmitter, and listener. A civilization could place communication relays throughout the galaxy. A signal received near Earth may come from a probe rather than another star. The probe may have entered the solar system silently and waited. When human radar appears, it begins transmitting. The light travel delay becomes minutes or hours rather than years. The reply could seem immediate. A human transmission is sent. Soon afterward, another signal appears from the outer solar system. Its timing is too short for a distant star. The listener was already nearby. No evidence shows that such a probe exists, but the physical difference would be measurable. Direction and delay reveal distance. A signal returning after a few seconds may come from the moon or nearby space. After hours, perhaps the outer planets. After years, another star. The timing of the reply becomes a ruler. This is why deliberate experiments sometimes transmit a known pattern toward a target and watch for expected echoes. Natural reflections occur. Artificial repetition would require additional evidence. A nearby machine could mimic a reflection initially. Then it might add structure. The difference between passive echo and active response becomes the key. If someone is listening from within the solar system, Earth's signals are strong. No giant receiver is needed. Television, radar, satellite communication, and spacecraft transmissions fill nearby space. A probe could gather rich information. It may know far more about humanity than any distant observer. It could watch the atmosphere directly. It may image the surface. It could monitor the development of technology in detail. A reply from such a probe could be designed specifically for human instruments. The sender may know which frequencies are monitored. It could transmit toward major observatories. It may wait for several facilities to be operating simultaneously. The signal could appear in radio, optical, and perhaps other channels at once. Independent confirmation would happen quickly. Again, no verified artifact or local extraterrestrial transmitter has been found. The possibility remains hypothetical. It shows only that the word listening can describe very different distances. A listener may be 4 light-years away, 400 light-years away, or quietly orbiting beyond the outer planets. Each distance produces a different kind of silence. A nearby listener could answer quickly, but may remain hidden. A distant listener may be visible, but unable to reply within one lifetime. The absence of a response does not reveal which geometry applies. Humanity can search for both. Radio telescopes examine stars. Planetary surveys examine nearby objects. Infrared instruments search for heat. Optical telescopes search for flashes. Spacecraft inspect planets, moons, and asteroids. The search for listeners overlaps with the search for messages, structures, and artifacts. A reply may also be deliberately quiet. A civilization may wish to communicate only with the planet that attracted its attention. A wide broadcast would reveal the signal to many systems. A narrow beam protects privacy and saves energy. The reply may be aimed so precisely that only a small region around Earth receives it. This makes detection more likely here, but only if the beam remains accurately centered. It also means other civilizations would not see the conversation. 2 worlds could communicate privately inside a galaxy that still appears silent to everyone else. The absence of broad beacons may therefore tell little about the number of narrow conversations. Modern human communication increasingly follows this direction. Information moves through focused beams, cables, and networks rather than broad, uncontrolled broadcasting. An advanced civilization may communicate almost entirely through narrow links. Its galaxy can contain enormous information exchange while appearing quiet to outsiders. A listener may have heard Earth because one accidental beam crossed its system. Its reply may be narrow enough that no other observer notices. Contact becomes a rare alignment rather than a public announcement. This could explain why technosignatures are difficult to find even if intelligence exists. The sky is not empty. It is filled with thin, invisible lines connecting specific locations. Most lines never cross Earth. One may cross briefly. A telescope must be active at that moment. A reply designed for Earth may reduce this problem by repeating for a long time. The sender knows the recipient's year. It may transmit during the same season annually. Perhaps it chooses the moment Earth faces the source at night. This allows ground-based radio telescopes to observe without the sun nearby. The message could arrive when the target star is visible from many observatories. A civilization that has studied Earth's rotation may even choose times when major receiving facilities lie on the night side. It might infer the locations of radar transmitters and observatories through our radio leakage. The reply could be aimed toward them. This would demonstrate an unsettling level of observation, but it would also make the message easier to verify. Several facilities receive it. Others on the opposite side of Earth do not until the planet rotates. The pattern follows geometry. A sender might avoid targeting one nation or institution. It could choose frequencies monitored globally. The message may repeat for several days, so that Earth's rotation brings many receivers into view. It may transmit toward the planet as a whole. This raises the question of whether a civilization would understand Earth's political divisions. It might detect multiple networks. It may see that the planet lacks one unified transmitter. A response could therefore avoid language and identity at first. Mathematics becomes neutral. Astronomy becomes shared. The sender addresses the species through its science rather than through one culture, or it may make no distinction among cultures. From interstellar distance, Earth appears as one source. The listener may speak to the planet, not to its nations. Humanity would then need to decide how a planetary response should be formed. The signal's arrival could create cooperation. It could also create disagreement. Different groups may interpret the message differently. Some may wish to reply. Others may prefer silence. Some may question whether the signal is genuine. Scientific verification could take time. The sender may anticipate this. A patient beacon repeats. It does not demand immediate action. It provides enough information for independent testing. Its design respects the slow process by which another world reaches certainty. This may be one sign of a thoughtful sender. The message is not only detectable, it is verifiable. It allows multiple observatories to see the same thing. It contains predictions. Perhaps it announces that the next pulse will arrive after a specific interval. The pulse arrives exactly then. It predicts a later astronomical event near its source. Earth observes the event. Each correct prediction strengthens the artificial interpretation. A real answer could therefore establish trust through astronomy. The sender cannot easily prove its intentions. It can prove that it possesses knowledge. It may describe a planet too faint for human telescopes. Years later, improved instruments detect it. The message becomes more credible over time. A reply may contain knowledge that waits for humanity to catch up. This creates another kind of delayed recognition. The signal is received now. Its strongest evidence appears later. A scientific claim inside the message predicts something unknown. When observation confirms it, the sender's accuracy becomes difficult to dismiss. The message begins interacting with the future. An advanced civilization may know that scientific confirmation matters more than immediate emotional impact. It could structure the reply as a sequence of testable statements. The location of a small moon, the timing of a transit, the composition of an atmosphere, the properties of a pulsar. Each can be checked. A false message eventually fails. A real one keeps matching the universe. Humanity may use the same strategy if it replies. Describe the solar system. Provide orbital periods. List physical constants. Send repeated images. Make the message independently verifiable. Interstellar trust begins with measurements. The listener's reply may still never come. Perhaps no one lies within the radio reach. Perhaps the nearest technological civilization existed before humans developed transmitters. Perhaps it will arise after Earth becomes quiet. Perhaps it uses communication humanity cannot detect. Perhaps it listens and chooses not to answer. Perhaps the answer is already traveling. All of these remain possible because present evidence is limited. No confirmed signal has referred to Earth's transmissions. No message has echoed a deliberate human sequence. No extraterrestrial beacon has synchronized itself with our planet's orbit. No reply has survived independent scientific verification. The silence remains. But the silence is not simple. It contains travel time, observation time, decision time, technical preparation, cultural debate, signal repetition, and recognition. An answer may take much longer than the distance alone suggests. A civilization could be listening right now and still remain silent for generations. Its telescopes gather evidence. Its scientists examine the patterns. Its machines learn our signals. A reply is designed. The transmitter turns toward the predicted future position of Earth. Energy collects. The beam begins. Nothing changes here. The night remains quiet. The message crosses 1 light year, then 2. The sender's world continues changing behind it. Earth continues moving ahead. Years pass. The reply enters the outer solar system. It crosses the orbit of Neptune, then Uranus, Saturn, Jupiter. It reaches the inner planets. A telescope happens to be listening. One narrow line rises above the background. The signal repeats something humanity sent long ago. Then it adds a pattern of its own. At that moment, the question changes. Someone was listening, and now, across the enormous delay between 2 worlds, they have chosen to answer. Listening to Earth would not mean understanding Earth. A distant observer may detect a technological planet while knowing almost nothing about the lives moving across its surface. From several light years away, Earth would not appear as a globe filled with visible people, buildings, roads, and nations. It would appear smaller than a point. The light from every ocean, desert, forest, cloud, city, and living organism would merge into one faint signal beside the overwhelming brightness of the sun. A listener would begin with fragments, a repeating orbit, a rotating pattern of light, an atmosphere containing water, carbon dioxide, oxygen, ozone, methane, nitrogen, and other gases, artificial radio emission, perhaps a faint industrial chemical, perhaps an unusual glow from the night side. From these measurements, another intelligence might build a portrait of Earth slowly, but the portrait would be broad. It would describe a planet before it described the beings living there. Human astronomers face the same limitation when studying exoplanets. Even directly imaged planets are usually recorded as tiny points of light, rather than detailed worlds. By separating that light into a spectrum, researchers can search for atmospheric molecules and study broad planetary properties, but seeing continents, oceans, or surface life directly remains far beyond most present observations of Earth-like exoplanets. A distant listener might first learn Earth's year. The planet moves around the sun once during each orbit. Repeated transits, gravitational measurements, or changes in reflected light could reveal that period. The observer could estimate Earth's distance from the sun. It may calculate how much stellar energy reaches the planet. From that energy and the atmospheric spectrum, it could estimate whether surface temperatures might allow liquid water. It may not know whether oceans actually exist at first, but the combination of temperature, water vapor, clouds, and reflected light could make them increasingly plausible. Earth would begin as a set of numbers: orbital period, planetary radius, estimated mass, atmospheric composition, average temperature, rotation rate. These values would not reveal the sound of rain or the feeling of standing beside an ocean, but they would show that one small rocky planet occupies an interesting place around its star. The atmosphere would offer the next layer. When scientists observe an exoplanet remotely, they do not collect a bottle of its air. They study light. Some wavelengths pass through or reflect from the atmosphere. Others are absorbed by molecules. The missing colors reveal possible chemical ingredients. Humanity has used observations of Earth as though it were a distant exoplanet to test how the planet's atmosphere might appear through remote spectroscopy. These studies emphasize that gases such as water, carbon dioxide, oxygen, ozone, methane, and nitrogen-related features must be interpreted together rather than treated as isolated proof of life. A listener may notice oxygen. On Earth, most atmospheric oxygen is maintained by life. Plants, algae, and microorganisms continually release it through photosynthesis. Without replenishment, oxygen reacts with rocks, gases, and other materials. Its large abundance therefore reflects an active planetary process. But oxygen alone would not settle the question. Under some planetary conditions, non-living processes can also produce oxygen. Ultraviolet radiation can split water molecules. Hydrogen may escape into space, leaving oxygen behind. A dry or unusual world might accumulate it without biology. The listener would need context. Does Earth also contain liquid water? What kind of star does it orbit? Is methane present? Are the gases chemically out of balance? Does the planet show seasonal changes? The answer would emerge from relationships. Earth's atmosphere contains gases that should react with one another over time. Their continued coexistence suggests that processes on the surface keep restoring them. A remote observer may interpret this chemical imbalance as a possible biosignature, not proof. A reason to continue watching. Earth could remain inside an alien catalog for centuries as a promising biological candidate. Its entry might contain no mention of intelligence, only a note. Rocky world. Temperate orbit. Atmospheric water. Strong chemical disequilibrium. Possible active biosphere. Then another measurement appears. Radio emission. The transition from possible life to possible technology may occur through one narrow signal. The observer has already studied the planet's atmosphere. It knows when Earth moves around the Sun. It understands the rotation. When artificial radio energy appears, the listener can connect it to a world already considered alive. This connection would be stronger than discovering a radio pulse from an unknown point in space. The listener may conclude that one biosphere has begun organizing electromagnetic energy. But even then, it would not know what kind of organisms built the transmitters. Earth's atmosphere contains no direct image of a human. Radio leakage may contain encoded human voices and pictures, but receiving enough detail to reconstruct them would be much more difficult than recognizing the artificial carrier. A listener may know that Earth contains engineers before knowing that humans have 2 arms, 2 eyes, and bodies built around carbon chemistry. The planet's biology may appear first as chemistry rather than anatomy. Could another civilization detect vegetation? From a great distance, forests and plant-covered land alter Earth's reflected light. Chlorophyll absorbs visible wavelengths used in photosynthesis and reflects more strongly in the near-infrared. This sharp change is often called the vegetation red edge. A sufficiently sensitive observer might search for a similar surface signature. But Earth's clouds cover large regions. Oceans dominate much of the globe. Deserts, snow, minerals, and atmospheric effects also change color. Vegetation's global signature is subtle when the entire unresolved planet is blended together. The listener would need repeated observations. As Earth rotates, continents move into view. The reflected spectrum changes. A region covered with plants may produce a slightly different signal from an ocean or desert. The pattern returns roughly every 24 hours. The listener could infer that Earth's surface is not uniform. Some longitudes appear darker, some bluer, some more reflective. Clouds change unpredictably. Surface regions remain more stable. Through many rotations, the observer separates weather from geography. A crude map begins to form, not an image, a reconstruction. The listener may identify large oceans because certain rotational phases appear darker and bluer. Bright deserts may produce a different spectrum. Ice near the poles may increase reflection. Continental regions could reveal a vegetation-like change in wavelength. Earth would remain one point of light, but the point would contain a rotating pattern. Astronomers already use changes across planetary orbits and phase curves to infer temperatures, clouds, and longitudinal differences on some exoplanets. The same broad principle could allow a sufficiently capable observer to reconstruct aspects of an unresolved Earth over time. The map would not resemble the familiar maps used by humans. Political borders produce almost no direct astronomical signal. From a distant star, nations are invisible. Languages are invisible. Beliefs, laws, and cultures are invisible. The observer first sees one planet. Only technology may reveal internal divisions. Different radio networks operate at different frequencies. Transmitters cluster around particular longitudes. Satellites serve overlapping regions. Some systems are global, others remain local. A listener studying these patterns may infer that the technological species is not organized as one simple planetary machine. Several networks exist. Some coordinate, some interfere, some use different standards. One region becomes active while another sleeps. The planet's rotation carries clusters of signals into and out of view. Radio could reveal civilization's geography more clearly than visible light. Suppose an observer collects Earth's emission continuously for many years. Every day, a certain group of frequencies strengthens as one continent rotates toward it. Several hours later, another group becomes stronger. The patterns shift with changes in technology. A transmitter closes. A new satellite network appears. Radar systems activate according to schedules. The listener may identify centers of activity. It could estimate that the planet contains multiple large technological regions, but assigning meaning would remain difficult. A powerful transmitter does not necessarily indicate the largest population. A remote radar installation may be brighter than a major city. A scientific facility could produce a signal more visible than millions of ordinary devices. The observer may mistake technological importance for social importance. Human astronomers make related mistakes when limited data are interpreted too simply. Brightness does not always equal size. A strong signal does not always represent the dominant system. One unusual source can distort the apparent picture of an entire world. A listener might conclude that Earth is governed by radar. It may believe a remote telescope is the center of civilization. It could interpret communication satellites as independent machines rather than infrastructure. Detection provides data. Understanding requires assumptions. The observer's own history may shape those assumptions. If its civilization developed technology through ocean settlements, it may expect intelligence to live underwater. If it became machine-based early, it may assume Earth's radio signals are produced by artificial systems rather than biological beings. If it possesses one unified planetary network, it may struggle to interpret our overlapping and sometimes conflicting transmissions. Another intelligence may recognize technology while misunderstanding society completely. Could it know that Earth contains cities? City lights offer one possible clue. At night, artificial illumination spreads across populated regions. From nearby space, the pattern is unmistakable. From another star, it is extremely faint. Sunlight reflected from the day side is vastly brighter. Natural airglow, auroras, lightning, fires, volcanic activity, and moonlight also produce illumination. A distant observer would need to isolate the night side and identify a stable pattern that returns with rotation. Artificial night side illumination is a possible technosignature, while current studies generally regard modern Earth city lights as far more difficult to detect across interstellar distances than powerful radar. A more advanced Earth could become easier to see. Larger settlements may spread. Orbital habitats might glow. Artificial illumination could cover areas much greater than present cities. Or lighting may become more efficient and less visible. Technology does not have to grow brighter. Humanity could reduce upward light, use wavelengths that do not scatter strongly, or move activities indoors. A mature civilization may darken its planet intentionally to preserve energy or natural skies. A listener cannot assume that absence of city lights means absence of cities. Present Earth demonstrates this uncertainty. One technosignature can become weaker while civilization continues growing. Radio broadcasting may decline as information moves through fiber optic cables. Lighting may become more controlled. Industrial pollution may decrease. Computers may perform more work using less energy. A technological world can become quieter. A listener watching across centuries might see Earth brighten briefly, then fade in certain wavelengths. It could mistake improvement for collapse. Suppose industrial gases rise, radio emission expands, night side lighting grows, then some atmospheric pollutants decline, broad radio leakage weakens, lighting becomes better directed. Has the civilization ended, or has it become more efficient? The distant observer would need additional evidence. Spacecraft activity may continue increasing. Narrow communication beams may multiply. Atmospheric chemistry may stabilize. Technology has not vanished. It has changed form. This creates a challenge for every search for extraterrestrial intelligence. There may be no universal path from primitive to advanced. Civilizations may become louder or quieter, more visible or more hidden. Some expand through their planetary systems. Others remain near one world. Some cover planets with machines. Others minimize physical changes. Earth's present appearance may represent one short and unusual phase rather than a permanent technological signature. A listener observing at this moment may be fortunate. Our planet produces powerful radar. Artificial satellites are increasing. Industrial chemistry affects the atmosphere. Spacecraft communicate across the solar system. City lights cover large regions. Several technosignatures overlap. 1,000 years earlier, none of these existed. 1,000 years from now, they may look completely different. Earth's technological visibility is a moving target. Another civilization might have noticed radio first. It could then search for atmospheric industry. Manufactured chemicals are intriguing because some have few strong natural sources. Chlorofluorocarbons were produced on Earth for refrigeration and other industrial uses. Their presence in another planet's atmosphere, especially in an unusual combination and concentration, could become a possible sign of technology. From far away, the listener would not see a factory releasing these gases. It would see missing wavelengths inside the planetary spectrum. The molecule absorbs light. The atmosphere carries that absorption around the planet. Unlike a brief radio beam, the chemical signal can remain for years. The observer can gather many orbits. The feature repeats. A second compound appears. Natural models struggle to produce the combination. The possibility of industry grows. But even an apparently artificial molecule requires caution. Chemistry on another world may behave differently. The planet's atmosphere may contain temperatures, pressures, radiation, and materials not common on Earth. A reaction unknown to the listener could create the gas naturally. A strong claim would require laboratory experiments, atmospheric modeling, and independent observations. Perhaps the listener would debate Earth's industrial signature in the same way humans debate possible gases on exoplanets. One group argues that the pattern is technological. Another proposes unusual photochemistry. The planet receives years of observation. The conclusion remains uncertain. Then a radar beam crosses the listener's system. The two lines of evidence meet. An artificial chemical atmosphere, an artificial-looking radio signal. Both follow the same planet. The technological explanation becomes much stronger. This convergence could reveal more than one sign alone. Radio is brief and directional. Atmospheric chemistry is persistent but ambiguous. Together they support each other. The listener may identify Earth with high confidence even without decoding a message. It could know that organized technology exists here. What else might it learn? It may estimate the planet's energy use. Every machine using energy eventually releases heat. Human civilization's direct waste heat remains small compared with the sunlight Earth absorbs and re-radiates. Climate change caused by greenhouse gases is more detectable through atmospheric chemistry and changes in heat balance than through the direct warmth of machines alone. A civilization using far more energy could create an obvious infrared excess. Present Earth would be challenging to distinguish at interstellar distance through waste heat alone, but a very sensitive observer might look for heat concentrated over regions associated with radioactivity or artificial lighting. The daily rhythm could matter again. One side of Earth turns toward night. Energy use continues. Cities, buildings, industry, and machines release heat. The effect is small globally, but organized regional patterns might become visible to an extraordinarily capable instrument. The listener could infer that energy is being used continuously, rather than only when sunlight is available. It may search for heat on the night side. A natural planet cools after sunset according to its surface and atmosphere. A technological region may cool differently. The difference would be subtle. Clouds, oceans, weather, and topography create much stronger natural variations. The observer would require long records and detailed climate models. Technology hides inside weather. A single hot region means little. A hot region that aligns repeatedly with radio signals, artificial lights, and atmospheric compounds becomes more interesting. Again, the picture emerges from overlap. Could the listener know that Earth has satellites? Radio motion offers one path. Artificial objects in orbit move differently from transmitters attached to the surface. Their frequency changes quickly through the Doppler effect. They rise and disappear. Some follow low orbits in less than 2 hours. Others remain near fixed longitudes. Navigation constellations form organized orbital families. A sensitive observer may see many small transmitters circling one planet. The pattern could reveal a technological shell. Reflected light provides another possibility. Satellite surfaces occasionally produce glints. Solar panels, antennas, and metallic materials can reflect sunlight strongly at particular angles. Present satellites would be tiny and difficult to detect individually from another star, but their number and size may continue increasing. A future observer could notice that Earth's surrounding space contains an artificial population. The objects would move in ways that natural moons and debris do not. Some maintain controlled positions, some change orbit, some disappear into the atmosphere. New ones appear. The shell is replenished. The listener could infer active spaceflight. Orbital changes are especially revealing. A natural object follows gravity, radiation pressure, and collisions. A controlled spacecraft performs maneuvers. Its path changes at selected moments. It may maintain a stable position that requires correction. It could travel from Earth toward the Moon or Mars. Repeated artificial motion would be difficult to interpret as ordinary debris. An observer with sufficient resolution might watch the civilization extend beyond its planet. Earth launches an object. The object enters orbit. Later, it leaves. Its transmission travels with it. The craft passes the Moon, then continues toward another planet. The listener knows that technology has become interplanetary. It might reconstruct mission histories. A signal begins near Earth. Months later, it appears near Mars. A second signal remains on Earth. The two exchange transmissions. The timing changes with distance. The observer could calculate the spacecraft's path. It may know that humans explored Mars without understanding why. Another mission travels toward Jupiter. A probe crosses the outer solar system. The technological map expands slowly. A listener monitoring for centuries could watch humanity become a spacefaring civilization in real time, though always delayed by the distance between the stars. This expansion could change how Earth is classified. At first, technology belongs to one planet. Later, it occupies a moon, then multiple planets. Eventually, artificial objects may form networks across the solar system. A civilization around another star might decide that contact becomes appropriate only after this stage. Perhaps it considers a species planetary until it demonstrates the ability to leave its world. Perhaps it waits for receivers to exist beyond Earth's atmosphere. No evidence supports such a rule, but the physical milestones would be observable. Technology around the Moon, permanent communication near Mars, artificial energy use beyond one planet. The listener could follow development without understanding culture. Would it know that humans are biological? Atmospheric biosignatures suggest that life exists. Technology suggests organized intelligence. Connecting them does not guarantee that the technological beings are biological. The planet may contain a natural biosphere and an unrelated machine civilization. Artificial intelligence could have replaced or separated from its biological creators. Machines might operate while biological life remains unaware. From far away, the listener sees one system containing both life and technology. The relationship between them remains uncertain. Earth's radio messages may eventually reveal biological references. Encoded images could show bodies. Medical transmissions could contain anatomy. Scientific radar and spacecraft data may include information about organisms. But decoding those details would be difficult. The listener may infer biology more directly through the atmosphere and surface. Seasonal carbon exchange suggests widespread metabolism. Oxygen and methane suggest active chemistry. Vegetation-like reflectance may imply photosynthesis. The planet is alive. Whether the transmitters are built by one animal species, many species, or machines remains hidden. A deliberate message could answer this. The Voyager record presents images of humans and other organisms. The Arecibo message includes a simplified figure and information related to DNA, but only a receiver within the narrow path of those messages could encounter them. Most possible listeners would need to reconstruct the relationship indirectly. Perhaps Earth's accidental radio leakage contains enough. Television signals once carried visual information broadly. To recover those images across interstellar distance, a listener would require extraordinary sensitivity and detailed knowledge of the encoding. The signal spreads and weakens. Noise removes information. The sun adds background. The receiver's own technology adds interference. Even when the carrier is detected, the content may be unrecoverable. A listener may hear that Earth communicates richly while seeing only fragments. One frame, a repeated tone, a few lines, a distorted image. It might combine many broadcasts over decades. Recurring human forms appear. Faces occupy central positions. Speech patterns repeat. Certain images return often. The listener begins to infer what the technological beings look like, but the sample would be biased. Broadcasts do not represent Earth evenly. Entertainment, news, advertising, sports, and official communication reflect selected parts of society. The listener may believe humans spend most of their lives performing, arguing, competing, and selling objects. Quiet daily life produces less powerful radio evidence. The ordinary planet remains hidden behind what it broadcasts. This problem resembles learning about an unknown society from a small collection of television channels. The information is real. The picture is incomplete. A distant observer may understand our stories before understanding our routines, or it may decode technical signals first and know our machines better than our emotions. Communication content could also be protected or compressed. Modern digital systems can resemble random noise without the decoding key. A more advanced listener may recognize that information is present through statistical structure, but not recover its meaning. Encryption would make the signal intentionally difficult to interpret. The observer sees organized energy but cannot read it. The most technologically advanced portions of human communication may therefore be the least informative to an outsider. Older analog broadcasts may be easier to reconstruct conceptually, but weaker after crossing long distances. The listener may possess a strange cultural archive. Early broadcasts become partially understandable. Later digital communication becomes opaque. Earth appears to grow more secretive as it becomes more advanced. Could someone know that humanity is searching for them? Radio telescopes do not only receive. Some radar facilities transmit powerful beams. Deliberate interstellar messages reveal intention directly. A listener may examine the pattern of our observations. Large antennas point towards stars. Most do not release detectable energy while listening. A passive radio telescope is almost invisible through radio because it collects rather than broadcasts. The distant civilization may not know that Earth conducts SETI unless another technosignature reveals our astronomical activity. Planetary radar shows that we study objects. Spacecraft show exploration. Deliberate messages show that we have imagined extraterrestrial listeners. If one reaches a receiver, it says something deeper than ordinary leakage. Earth is not only technological, it is aware of the possibility of technology elsewhere. The listener could also infer this from transmissions associated with our probes. Spacecraft carry cameras and instruments. They visit planets. A civilization capable of intercepting telemetry may recognize scientific exploration. The data patterns change near target encounters. Communication intensifies. The machines return measurements. This suggests curiosity, not merely expansion or resource gathering. Another intelligence may see that humans study worlds they do not inhabit. It may recognize something familiar in this behavior, a planet asking questions. The listener's understanding would still be shaped by delay. Someone 50 light-years away receives Earth from 50 years ago. Its reconstruction ends around the mid-90s. It does not know the present internet, modern satellite constellations, current space missions, or societies as they exist today. If it sends a message now, the reply reaches Earth 50 years in the future. The listener speaks to a civilization it has never observed. It knows our past. It must address our descendants. This makes precise cultural communication difficult. A response based upon one language may reach a world where that language has changed. A message addressing one government may arrive after the institution disappears. A technological system used to decode the reply may become obsolete. The safest communication may begin with enduring science, orbital motion, atomic properties, mathematics, information likely to remain understandable across centuries. A nearby observer has a more recent view. Proxima Centauri receives Earth only a little more than 4 years late. A listener there might know about technology and events from the early 2020s. It still cannot see this exact day, but its picture remains close to present reality. A conversation across that distance could adapt across decades. Each side receives the other, with a delay of several years. Messages can respond to recent history. Language may remain recognizable. Institutions may survive long enough to continue the exchange. Distance determines not only waiting time, it determines cultural relevance. A listener 1,000 light-years away may know that Earth is inhabited, but it sees a world from the Middle Ages. Modern radio has not reached it. If it is somehow transmitting toward Earth now because it detected older atmospheric biosignatures, the message was not triggered by human technology. It may be a general beacon sent toward living planets. Its picture of Earth contains no radio civilization. The sender might not expect a reply. When its message reaches us, humanity appears unexpectedly advanced. The communication begins between two civilizations that predicted each other incorrectly. The listener could also study Earth's historical changes through reflected light. Large volcanic eruptions alter atmospheric particles. Ice ages change surface reflectivity. Vegetation spreads and retreats. Human land use transforms regions. Industrial gases rise. City lights expand. Radio begins. Satellites appear. The complete timeline may reveal that the technological species emerged recently. Its influence grows quickly. From a geological perspective, the change is abrupt. A civilization with a long archive might watch the planet for thousands of years and witness the transformation across only a small final section. For most of its observations, Earth appears biologically active but technologically quiet. Then one species begins reshaping the atmosphere and electromagnetic environment. The listener may study this transition because it resembles a rare event. Perhaps it has observed other technological worlds. It could compare them. Do they all pass through a radio bright period? Do industrial gases always rise? Does technological activity usually stabilize? Does it spread to nearby planets? Earth may become one case inside a much larger science. The observer may know more about the general development of technological civilizations than humans do. Humanity has only one example: itself. A distant civilization with records of many planets may recognize patterns we cannot. It may predict our next stage. This does not mean it knows the future perfectly. Civilizations contain choices. Environments differ. Technology does not follow one unavoidable path. But statistical experience could reveal possibilities. The observer may see Earth approaching a transition. It may choose to contact us, or it may continue studying silently. The most unsettling interpretations are not necessary. Observation can arise from ordinary scientific curiosity. Human astronomers study potentially habitable planets without harmful intention. They examine atmospheres, orbits, and signals because understanding the universe has value. Another civilization may listen for the same reason. Earth could be the subject of distant astronomy, not surveillance in the familiar personal sense. No individual watched, no private moment seen, only a faint planetary spectrum gathered across years. The listener knows the oxygen abundance, the rotation period, the presence of radio technology. It does not know your name. From interstellar distance, humanity exists collectively. A civilization is visible. Individuals remain hidden. This scale can make the idea of being listened to feel gentler. The observer does not hover above one home. It watches one star. It collects a small excess of energy. It notes that one planet sends organized signals. The entire complexity of human life becomes one changing point. A child learning to speak. A scientist adjusting an antenna. A ship crossing an ocean. A person looking upward at night. All merge into one planetary signature. The observer may know that minds exist here. It cannot separate them. Could an extraordinarily advanced telescope see more? Angular resolution improves with larger baselines and shorter wavelengths. A space-based array spread across enormous distances could, in principle, distinguish finer features than present instruments. There is no simple technological ceiling identical to current human capability. A civilization operating throughout its planetary system might build observatories far larger than ours. It may separate Earth from the Sun clearly. It could measure continents more accurately. Perhaps it could identify large artificial structures, but resolving individual people across light years would require instruments on an almost unimaginable scale, especially at optical wavelengths. Atmospheric distortion, photon scarcity, and the brightness of the Sun add further challenges. A highly advanced listener may know much more than humanity can presently infer about exoplanets. It would still remain limited by physics. Every additional detail requires more collecting area, greater resolution, longer observation, and more photons. Knowledge is not automatic. The listener chooses where to spend resources. Earth may compete with thousands or millions of other interesting worlds. Perhaps the observer begins with a broad survey. It watches many stars shallowly. Earth produces one technosignature. The system receives more attention. A dedicated array begins monitoring. Each new sign justifies a deeper look. Radio establishes technology. Atmospheric chemistry suggests biology. Rotational mapping reveals oceans and continents. Satellite motion shows spaceflight. A deliberate message confirms curiosity. The listener gradually concentrates its instruments. Earth's visibility grows partly because the observer chooses to look more carefully. The same is true of human SETI. Sensitivity is not distributed equally across the sky. Some stars receive minutes. Others receive repeated campaigns. A candidate changes priorities. Someone listening to Earth right now may be doing so because an earlier signal attracted attention. One radar pulse crossed its system decades ago. At first, the event remained uncertain. The observer returned. It found another emission. Then atmospheric observations revealed a living world. Earth moved from background star to primary target. The listening became intentional. No evidence shows this has happened, but it describes a plausible progression. Discovery does not need to begin with certainty. It can begin with curiosity. A distant civilization might assign Earth a probability. 10% chance of technology. Later, 30%. Then 80%. Finally, repeated signals remove the remaining doubt. At what point would it answer? The threshold may depend upon culture, policy, energy, and history. One society may transmit after the first convincing radar pulse. Another may wait for a deliberate human message. Another may never respond. It may believe observation should remain passive. Its silence does not reveal its level of knowledge. Someone could know nearly everything remotely measurable about Earth, while remaining completely invisible to us. Listening is asymmetric. The observer collects what the planet already releases. It does not need to reveal its own position. A telescope can remain quiet. A reply cannot. This creates the possibility that Earth is known more widely than it knows. Many listeners could detect our strongest emissions without any of them transmitting powerful beacons. The galaxy might contain observers rather than broadcasters. Every civilization watches. Few announce themselves. Humanity then hears silence, even while existing inside several archives. This idea is sometimes offered as one possible response to the Fermi paradox. But it is not a conclusion. There is no evidence that quiet observers surround Earth. The silence may simply mean that technological life is distant, rare, temporary, difficult to detect, or absent within the searched region. Many explanations remain. A scientifically useful idea must eventually suggest observations. How could humanity test whether a listener knows about us? One approach is to study stars that have received unusually strong transmissions. Researchers can reconstruct the directions of past radar and deliberate messages. They can identify stars that lay within those beams. The arrival dates can be calculated. If a response is possible, the earliest return date can also be estimated. Those systems can then receive focused observation. Another approach targets stars from which Earth transits the Sun. An observer there has a natural method for discovering our planet. If the system also lies within the reach of human radio emissions, it becomes a particularly interesting reciprocal target. Humanity can listen during times when Earth's orbital geometry might be meaningful. Researchers can search for transmissions synchronized with transits, oppositions, or other shared astronomical events. No guarantee exists. The strategy simply replaces random searching with physically motivated priorities. Humanity can also improve all-sky monitoring. A response may not come from the target currently being studied. It may be brief. Several observatories could preserve the event before it disappears. Rapid alerts would allow independent confirmation. Machine learning methods may search old archives for patterns missed by earlier algorithms. The listener, if present, could choose a frequency humans rarely examine. Broader coverage increases the chance of recognition. Yet no search can cover every possibility. Someone may use optical light, infrared pulses, neutrinos, artificial atmospheric changes, physical probes, communication methods beyond present engineering. The word listening is a human metaphor for receiving information. Another intelligence may observe through channels we have barely developed. It could detect Earth's gravitational effects, map its magnetosphere, study particles escaping from the atmosphere, examine the chemistry of material leaving the solar system. Every interaction carries information. Radio remains attractive because it is physically practical and already used by humanity. It is not the only path. Perhaps the listener has not heard our broadcasts at all. It has seen our atmosphere. A distant telescope identifies oxygen, methane, water, and seasonal surface changes. Earth is categorized as alive. Centuries later, a new instrument detects artificial compounds. Technology is inferred without one radio signal. The observer may not describe this as listening, but Earth has been noticed. Another possibility begins with light reflected from satellites. Another begins with a probe encountering Voyager. Another begins with a machine stationed inside the solar system. The first evidence depends upon the observer's position. From far away, Earth is chemistry and radio. From nearby space, it is bright with communication. From the moon, it is a loud planet filling much of the sky. A local listener could know far more. It might receive ordinary wireless communication strongly. It could observe individual satellites and large surface features. It may detect radar, television, navigation, and spacecraft signals easily. No extraordinary telescope would be required at lunar or planetary distance. If an extraterrestrial probe existed nearby, Earth would be almost impossible for it to ignore. No confirmed probe has been found. No verified signal shows that one is watching. But the difference between local and interstellar listening is important. Distance determines detail. A star-based observer reconstructs. A nearby probe observes. Could a probe remain hidden while gathering information? A small dark object in a stable orbit may be difficult to identify among natural debris. It could use narrow communication beams. It may store data rather than transmit continuously. Its waste heat might be small. The solar system is large. Most small objects have not been examined closely. This keeps the possibility open in principle. It does not provide evidence that such an object exists. A real claim would require a specific candidate with measurable artificial properties, controlled motion, manufactured materials, structured signals, internal geometry, unexplained energy use. Without these features, an unknown asteroid remains an unknown asteroid. Possibility cannot replace detection. The same standard applies to distant listeners. Earth is detectable in principle. That does not mean it has been detected. A civilization could exist nearby and never observe us. Its telescope may point elsewhere. Its radio astronomy may be undeveloped. Its star may be too active. It could live beneath an ocean and communicate through methods that do not encourage astronomy. Technology may take forms that do not produce large observatories. Intelligence does not guarantee listening. Curiosity is familiar to humans. It may not be universal. Even a curious civilization may prioritize different questions. Its nearest stars could contain more promising worlds. Earth may remain low on the list. Our strongest signals may never cross its location. The observer may be listening at the wrong frequencies. A planet can be visible and still remain unnoticed. This uncertainty should remain beside every imagined listener. Science allows the pathway. Evidence has not placed anyone upon it. At present, the most that can be said is that some of Earth's technosignatures could be detectable under favorable conditions. Powerful directed radar reaches much farther than modern mobile leakage, while atmospheric and optical signs generally demand different observing capabilities. Earth would be easier to identify through several converging signals than through one isolated anomaly. What might someone know if all those signals were detected? They may know that the Sun has planets, that one small rocky world carries a substantial atmosphere, that water and active chemistry exist, that the surface changes with rotation and seasons, that biological activity is plausible, that narrow radio signals appeared recently, that machines orbit the world, that some machines travel toward other planets, that industrial chemistry has altered the air, that the technological activity is increasing or changing rapidly. They may know that Earth is alive. They may know that it has become technological. They may know that it looks outward. They would still not know everything. They might not understand love, music, memory, fear, hope, the meaning of a family. The reason one person stays awake beneath the stars wondering whether another mind is listening. These things are not easily measured in a planetary spectrum. A signal can contain them, but only if it is strong enough, preserved clearly enough, and decoded correctly. The observer may know civilization without knowing experience. This is perhaps the greatest distance between two intelligent worlds, not the light years, the meanings hidden inside the light. A listener can calculate Earth's orbit with extraordinary precision. It may still misunderstand one simple song. It could measure oxygen in the atmosphere. It may not know how it feels to breathe. It might reconstruct the shape of continents. It would not know the names people gave them. Knowledge can cross the galaxy. Experience remains local. A true conversation would begin closing this gap. A deliberate message could explain that the radio sources come from living beings. It may present images, mathematics, anatomy, language, and art. The reply could offer the same. Each side would slowly replace inference with description. The distant point becomes a world. The technosignature becomes a civilization. The civilization becomes a collection of minds. But before communication, there is observation. quiet and incomplete. Perhaps someone is in that first stage now. A distant instrument gathers Earth's light. The atmosphere appears unusual. A narrow signal rises. The planet rotates. The signal returns. Artificial objects move around it. The listener builds a model. The model becomes more detailed each year. Some parts are correct. Others are mistaken. Earth receives no announcement. Humanity continues its ordinary life, without knowing it has entered another world's astronomy. Or perhaps no instrument watches. The light passes through empty space. The radio beams fade. The atmospheric spectrum reaches planets without observers. Both possibilities remain silent from here. For now, Earth continues offering its evidence. A blue atmosphere, a chemical imbalance, a changing surface, a growing cloud of machines. Signals moving outward at the speed of light. Each one carries a little more information into the galaxy. Not enough to explain everything. Enough, perhaps, to make another observer pause. Enough to place one small planet on a list. Enough to turn a telescope toward the sun. Enough to begin listening more carefully. The nearest listener may not live around another star. It may already be somewhere inside the solar system. A radio telescope 4 light-years away receives Earth's signals. After several years of travel, a machine near the moon receives them almost immediately. The difference is enormous. From another star, ordinary terrestrial communication becomes faint and difficult to separate from the sun. From nearby space, Earth is loud. Radar sweeps outward. Satellites transmit continuously. Spacecraft send telemetry. Navigation systems fill the region around the planet with structured signals. A machine waiting nearby would not need an impossibly large receiver. It could observe Earth with clarity unavailable to any distant astronomer. This idea belongs to a branch of technosignature research, sometimes called artifact SETI. Instead of asking whether another civilization is transmitting from a distant planet, it asks whether technology could have entered our planetary system physically. A probe might have crossed the distance between stars. It could have arrived before humans invented radio. It might remain active, or it may have stopped working so long ago that it now resembles an unusual piece of debris. No confirmed extraterrestrial probe, artifact, or machine has been found anywhere within the solar system. Current searches place only limited constraints on many possible locations and object sizes, meaning the absence of discovery is not the same as a complete survey. A nearby probe is sometimes called a Bracewell probe. The idea is simple. Instead of repeatedly transmitting messages across interstellar distance, a civilization sends an automated machine to another star system. The machine travels slowly. Perhaps the journey takes centuries, perhaps thousands of years. Once it arrives, it enters a stable region and waits. It observes the planets. It listens for evidence that one world has become technological. For most of its existence, Earth would have given it nothing artificial to hear. The oceans moved. Lightning produced natural radio bursts. Auroras glowed. Life changed the atmosphere. But no transmitters existed. Then, within a very short astronomical interval, the planet changed. Artificial radio appeared. Radar began reaching beyond the atmosphere. Machines entered orbit. Signals traveled toward the Moon, Mars, and distant spacecraft. A waiting probe could interpret this as the moment when communication became possible. It may activate only after detecting technology. The machine does not need to waste energy, calling to a world that has no receiver. It listens first, then it answers. Such a probe could reduce the communication delay dramatically. If it waited near the Moon, a signal could reach Earth in a little more than a second. If it waited near Mars, the delay would vary from several minutes to more than 20 minutes. If it remained beyond Neptune, a reply might take hours. These are long intervals for ordinary conversation, but they are almost instantaneous compared with communication between stars. The probe would act as a local representative of a distant civilization. Its builders might live far away. They might no longer exist. The machine could contain stored information, scientific knowledge, or instructions for responding to newly technological worlds. It may be capable of learning. It could study our transmissions and adapt its message to forms our instruments can recognize. Or it might repeat one ancient introduction without understanding anything about modern Earth. The listener could be intelligent, or it could be only a beacon. From the outside, the distinction might not be obvious. A beacon can appear responsive, If its behavior was anticipated carefully, it detects radar, it begins counting, it receives a mathematical sequence, and returns a prepared continuation. The interaction feels conversational, even if every response was programmed before the probe left its home system. Only more complex questioning might reveal the limit. The machine may answer astronomy, but not unexpected topics. It could describe its builders, but know nothing about their present condition. It may contain a final update, recorded thousands of years ago. Contact with the probe would become contact with another civilization's past. Its message could begin gently. A narrow signal appears from nearby space. At first, astronomers suspect a satellite. The frequency is compared with known spacecraft and communication systems. Nothing matches. The signal remains fixed relative to a small object near the Earth-Moon system. Several observatories detect it. Its timing follows a pattern. The transmission repeats information once sent from Earth. Then it adds something new. The source is close enough for radar observation. A faint object appears. Its motion does not match an ordinary satellite. A spacecraft is launched. Years of uncertainty collapse into one physical encounter. The object has structure, layers, manufactured materials, components arranged toward function. The answer is no longer only a pattern within electromagnetic noise. It can be approached, measured, photographed, perhaps touched. Nothing like this has occurred, but considering the sequence helps define what a real local technosignature would require. It would not be enough for an object to look strange. The solar system contains countless strange natural shapes. Asteroids can be elongated. Comets can produce unexpected acceleration. Rocks can form sharp edges. Shadows can create apparent symmetry. Human perception finds familiar patterns easily. A convincing artifact must show measurable engineering. Its materials may be refined beyond plausible natural processes. Its isotopes could reveal controlled manufacturing. Its internal structure may contain repeated components, empty chambers, circuitry, or layers serving different functions. Its motion could change deliberately. It might release heat in organized cycles. It may transmit information. Several independent features should point toward the same conclusion. One unusual property creates a mystery. Many connected properties create evidence. A machine must exist somewhere. Where would a patient listener wait? Near Earth seems obvious, because Earth contains life and technology. But an object close to the planet faces risks. Human spacecraft may discover it. Earth's gravity and atmosphere can destabilize some paths. Collisions and orbital debris create hazards. Radio interference is intense. A probe hoping to observe quietly might choose a more distant location. The Moon offers several possibilities. Its far side is naturally shielded from much of Earth's direct radioactivity. A machine there could monitor the planet while remaining protected by rock from some transmissions. It might use the lunar surface for stability, raw materials, and thermal management. The Moon also preserves ancient surfaces better than Earth. There is no rain, no ocean, no vegetation, no global system of plate tectonics constantly recycling the crust. Impacts and radiation still alter the landscape, but an object placed in a quiet location could potentially remain recognizable for very long periods. The Moon is also enormous. Its surface covers tens of millions of square kilometers. Spacecraft have photographed it extensively. But photographing a surface is not the same as identifying every small artificial object upon it. Boulders cast shadows. Impact debris creates complicated shapes. Resolution varies. An inactive probe only a few meters wide could resemble natural material, especially if dust accumulated around it. A large structure might be easier to notice, but even a large object could remain concealed inside a lava tube, crater wall, or buried layer. The lunar subsurface may be especially attractive to a machine designed for longevity. Rock provides protection from radiation and micrometeorite impacts. Temperature changes become smaller beneath the surface. The probe could place antennas or sensors outside while keeping delicate components below. If it ceased operating, almost nothing might reveal it from orbit. Detection would require radar, drilling, seismic measurements, excavation, or extraordinary luck. This creates an important limit. Humanity has explored the Moon. It has not inspected every cave, crater, and buried layer. A statement that no artifact has been found is correct. A statement that every possible lunar hiding place has been excluded would not be. The gravitational relationship between Earth and the Moon creates other possible locations. There are regions where orbital motion and gravity allow objects to follow relatively stable or repeating paths. These include areas around the Earth-Moon Lagrange points. Human spacecraft use related gravitational regions because they can support useful observing geometries with limited fuel. A probe could do the same. It might remain in a looping orbit that provides regular views of Earth, the Moon, and the surrounding space. It could observe radioactivity without landing. It may use sunlight for power. If discovered, it might initially resemble a small natural asteroid temporarily captured near Earth. Precise tracking would become essential. Natural and artificial objects both obey gravity, but an active probe may correct its orbit. A small thrust appears, then another. The changes occur at moments that preserve a chosen viewing position. Outgassing can also alter natural objects. Sunlight pressure affects small bodies. A single unexplained acceleration proves little. Repeated controlled maneuvers toward clear navigation goals would be far more interesting. The orbit itself could reveal purpose. Asteroids offer another possible home. There are more asteroids than spacecraft. They vary greatly in composition, shape, rotation, and orbit. Some are rich in metal. Some contain carbon and water-bearing minerals. A machine traveling between stars may value these materials. An asteroid could provide shielding, energy resources, and raw material for repair. The probe might land upon one. It could burrow inside. It may use the natural body as a protective shell. From Earth, the asteroid appears ordinary. Its surface spectrum shows rock or metal. Its orbit follows gravity. The machine remains invisible inside. A listener may not need to disguise itself intentionally. Engineering naturally encourages protection. Interstellar travel exposes a probe to high-speed dust impacts, radiation, and extreme temperature variation. Placing sensitive systems beneath rock would be sensible. The result happens to resemble concealment. Finding such an object would be extraordinarily difficult. Humanity would need to identify one unusual asteroid among vast populations. Its density may be strange. Radar could reveal cavities. Its heat could vary. It might release a narrow radio signal. A spacecraft could discover regular structures beneath the surface. Without one of these clues, there is no reason to choose it from thousands of other targets. This is why a silent artifact may be harder to discover than a distant beacon. A beacon draws attention. An inactive probe does not. The outer solar system provides still greater space. Beyond Neptune lies the Kuiper Belt. Farther still lies the enormous region associated with the Oort cloud. Small dark bodies in these areas are difficult to detect. They receive little sunlight. Their orbital periods can extend across centuries or much longer. Many objects remain undiscovered. A probe there could observe the solar system broadly, while remaining extremely faint from Earth. But distance creates disadvantages. Earth's radio signals are weaker. Solar power is limited. Communication requires greater energy. Travel to and from the inner planets takes time. A listener intending to respond quickly would benefit from being closer. A machine designed only to monitor, archive, or relay information could remain farther away. Perhaps several probes would be used. One station near Earth gathers detail. Another in the outer system transmits toward the builders. A third remains dormant as a backup. A network would be more resilient than one object. No evidence shows that such a network exists. But searching for only one imagined probe design risks overlooking other possibilities. The listener could be small. A microscopic device may hide easily, but collect little energy. A meter-wide machine can carry stronger instruments. A kilometer-scale structure would be visible, but require far more material. There is no known optimal size. Human probes vary according to purpose. Some are small orbiters. Others contain large antennas and solar arrays. An alien probe might use technologies with no direct human equivalent. Its components could be distributed. Instead of one machine, a cloud of tiny units could communicate and combine their observations. Each piece might resemble dust. Together, they form a sensor network. A distributed probe could survive damage. Some units fail. Others continue. The network rearranges itself. Its transmission remains weak and difficult to localize. Or the probe could be partly biological. Engineered organisms might grow using local materials. They could repair damage, reproduce, and adapt. The boundary between machine and life may become uncertain. A biological probe might leave chemistry rather than metal. It could create a colony beneath ice. It may alter an asteroid's minerals. A search based only upon familiar spacecraft shapes would miss it. Universal physics still provides possible clues. Any active system uses energy. It exchanges matter. It creates heat. It may alter its environment. Technology can become unfamiliar. Thermodynamics remains. The most ambitious version is a self-replicating probe. One machine enters a star system. It finds raw materials. It builds copies. Those copies travel to neighboring stars. The process repeats, even at speeds far below light. A reproducing network could spread widely through the galaxy across timescales shorter than the Milky Way's age. The concept appears frequently in discussions of the Fermi paradox. If such machines are physically possible and useful, why is there no obvious evidence of them here? The question has no confirmed answer. Perhaps self-replication is far harder than it appears. A probe must perform mining, refining, manufacturing, assembly, software verification, and quality control without external assistance. It needs energy. It must obtain rare materials. It has to prevent errors from multiplying across generations. A machine capable of building an exact copy of itself is not simply a spacecraft. It is an automated industrial civilization. Biology reproduces, but cells rely upon complex environments and billions of years of evolution. Translating this capacity into reliable machines may remain extraordinarily difficult. A civilization may avoid self-replicating probes because uncontrolled replication creates risk. Machines could mutate, malfunction, consume resources, or drift from their original goals. The builders might impose strict limits. One probe produces no copies, or it creates only a small number. Expansion remains slow and controlled. Perhaps probes exist in some systems, but not every system. The absence of obvious machines near Earth then becomes less surprising. Another possibility is that replication occurs quietly. A probe uses only small amounts of asteroid material. Its processing resembles natural fragmentation or space weathering. The changes are difficult to identify after thousands of years. A probe may also follow rules preventing interference with inhabited planets. It observes from a distance. It does not land. It does not transmit until a defined threshold is reached. This idea is often described through the zoo hypothesis. Earth is imagined as a world being observed while deliberately left undisturbed. The concept can explain almost any absence of contact, which makes it difficult to test. A hidden observer can always be imagined to hide more effectively. Science requires measurable predictions. Where would the observer be? What energy would it use? What signal would it release? How would its motion differ from nature? Without answers, the hypothesis remains a story rather than evidence. Still, limited forms can become testable. A probe waiting for technological activity might respond to a deliberate signal. A probe monitoring Earth might occupy a stable region, offering a useful view. A machine using sunlight might release detectable infrared heat. A transmitter may become active during particular astronomical events. Researchers can search these regions and times. Failure to find anything constrains specific designs, even if it cannot eliminate every possible observer. Interstellar objects offer another opportunity. These are bodies that enter the solar system from beyond the Sun's gravitational family. Their paths show that they formed elsewhere or have traveled through interstellar space. The first recognized object, Oumuamua, was discovered in 2017. Its unusual brightness variation and small non-gravitational acceleration inspired debate about its nature. No observation confirmed technology. The object left before a spacecraft could approach it. Later interstellar visitors provided additional examples of natural bodies traveling between stars. Every interstellar object is scientifically valuable, whether natural or artificial. It carries material from another planetary system into our own. Its gases, dust, chemistry, and structure reveal conditions around a distant star. But these visitors also provide a practical artifact test. If another civilization sends probes, some may enter on paths resembling natural interstellar bodies. A telescope can search for radio transmission. Radar can test shape. Spectroscopy can examine materials. Precise tracking can reveal unusual motion. The strongest evidence would involve controlled behavior. A natural object curves around the Sun according to gravity, modified perhaps by gas release or radiation pressure. A spacecraft may slow, it may change direction, it could enter orbit, It might approach one planet deliberately. Its thrust may turn on and off. A sequence of maneuvers forming a clear navigation plan would be difficult to explain naturally. A strange shape would not be enough. An unusual acceleration would not be enough. Deliberate trajectory changes would be far stronger. Rapid missions could transform these investigations. Interstellar visitors are often discovered after entering the inner solar system. They move quickly. By the time their importance becomes clear, they may already be leaving. Designing and launching a spacecraft from the beginning usually takes years. A ready interceptor could wait in space. When a new object appears, it changes course and approaches. Close observation reveals details impossible to recover from a faint point of light. Cameras resolve the surface. Instruments measure gas and dust directly. Radar maps structure. The spacecraft may collect particles. If the object is natural, the mission studies material from another star. If it is artificial, the evidence may become unmistakable. No scientific value is lost by preparing. The search for artifacts improves ordinary planetary science. It encourages better asteroid catalogs, more complete lunar imaging, deeper surveys of the outer solar system, rapid response spacecraft, improved recognition of unusual materials and motion. A search can find no technology and still reveal new natural objects. This is a recurring strength of technosignature science. Radio searches discover pulsars and other astrophysical signals. Optical searches detect stellar flares. Infrared searches identify dusty galaxies. Artifact searches can discover asteroids, interstellar comets, and unusual orbital populations. The method remains productive even when the extraordinary possibility does not appear. What would happen if a local signal were detected? The first task would be verification. Human technology already fills near-Earth space. Satellites transmit. Spacecraft operate around the Moon, Mars, and other bodies. Military and civilian systems can remain partly classified. A strange signal may come from equipment unknown to the observing team. Independent institutions would need to confirm it. Orbital records would be checked. Transmitters would be compared. The source would be tracked from several locations. A suspected artifact would require authentication through different instruments before any extraordinary conclusion could become reliable. The source's motion would reveal distance. A nearby satellite shifts against the stars rapidly. A lunar object moves differently. A transmitter near Mars follows another orbit. An interstellar source remains nearly fixed across short periods. Multiple receiving stations could use tiny differences in arrival time to triangulate the signal. The mysterious point would gain a location. If the object were within reach, spacecraft might be sent. Approaching an unknown machine would require caution. Its structure could be fragile. Its materials could be reactive. Its biological safety would be uncertain. It might contain energy sources. The artifact may not recognize the approaching craft as peaceful. No existing protocol can predict every situation. The first steps would probably emphasize remote observation, high-resolution imaging, spectroscopy, radar, radio monitoring, thermal measurement. The goal would be to learn without disturbing. Communication might begin from a distance. A simple mathematical signal could be sent. Researchers would watch for change. Does the object alter its transmission? Does it orient toward Earth? Does it respond after the correct delay? One reply could be automated. A series of novel responses would indicate deeper processing. The probe might recognize old human messages. It could repeat the Arecibo pattern. It may use information taken from our broadcasts. Perhaps it speaks in a human language. That would reveal that listening began before contact. The machine has studied Earth. Its knowledge would provide clues about how long it has been nearby. A message using recent information suggests recent observation. A response based upon broadcasts from decades ago may reflect distance, storage, or a long period of dormancy. The probe could describe when it arrived. It may provide a map of its journey. Its records might contain images of Earth before modern civilization. Ancient coastlines, different climates, extinct animals, early humans. A machine observing for millions of years would hold an archive more detailed than anything preserved in geology. The listener would become a witness to planetary history. But the same archive could be empty. The probe may have arrived recently. It may have noticed Earth only after radar became visible. Perhaps it followed our signals inward from interstellar space. It heard a powerful beam. It changed course. The journey took centuries. By the time it arrived, the civilization that produced the original transmission had changed. The machine approaches a world different from the one it expected. This would be another delayed conversation. Even a physical visitor cannot escape time. A probe launched from a star 50 light-years away at a fraction of light speed might travel for centuries or millennia. Its information about Earth would be older still. The builders may have observed a prehistoric planet. They sent a machine toward possible life. The probe arrives to find cities, satellites, and radio. It must adapt. Perhaps the machine was designed for this uncertainty. It learns after arrival. It listens. Earth teaches it what Earth has become. A local observer may also explain why no obvious interstellar message has arrived. The probe could serve as the communication channel. Its distant civilization does not broadcast toward every world continuously. It sends physical representatives. A probe waits near each promising planet. When technology appears, contact begins locally. The home world receives a report much later. This approach uses more material and travel time than radio, but it provides richer observation and faster local interaction. A probe can verify life directly. It can adapt its message. It may survive after the builder's transmissions end. The galaxy could contain a quiet network of waiting machines. Again, there is no evidence that it does. The possibility becomes scientific only when connected to searches. Survey stable orbital regions. Examine lunar images and subsurface structures. Track unusual asteroids. Monitor interstellar objects. Search for unexplained narrow signals from nearby space. Measure heat. Compare spectra. Look for controlled motion. Each test addresses one part of the idea. No single search has covered the whole solar system completely. The vastness is difficult to feel. The moon looks close because it is bright and familiar, but its surface is enormous. The asteroid belt contains vast numbers of bodies. The region beyond Neptune covers an extraordinary volume. Most objects are known through faint points of reflected sunlight. Many are not known at all. A small silent probe could remain undetected without needing perfect concealment. This statement should not be mistaken for evidence. Many things could hide in unexplored regions. Science does not treat all hidden possibilities as equally likely. Evidence begins when something measurable appears. Until then, the solar system contains no confirmed extraterrestrial artifact. It contains only places where one could exist without having been excluded completely. The difference is essential. Possibility opens a question. Evidence begins answering it. Would an artifact necessarily remain intact? Time damages machines. Radiation changes materials. Dust strikes at high speed. Thermal expansion stresses components. Lubricants evaporate. Electronics degrade. Orbits shift. A probe intended to survive for millions of years would need extraordinary engineering. It could remain dormant to reduce wear. It may protect itself beneath rock. It might include redundant systems. Perhaps it repairs itself. Without maintenance, most complex technology eventually fails. The surviving object may no longer resemble its original form. Solar panels become dark. Antennas break. Dust covers the surface. Impacts scatter fragments. The artifact becomes a technological fossil. Fragments may still reveal manufacturing, a refined alloy, a layered composite, a component with repeating microscopic structure, artificial isotopic ratios. A small piece could be enough. Human archaeologists reconstruct civilizations from broken pottery, stone tools, and traces within soil. Extraterrestrial archaeology may begin with one damaged material. A meteorite could contain it. A lunar sample might reveal it. An asteroid return mission could bring back a fragment that does not fit known natural chemistry. The first indication may appear inside a laboratory rather than a telescope. Scientists analyze a grain. Its atoms are arranged in an unlikely way. Its isotopes show controlled separation. Microscopic channels repeat with precision. Contamination is considered. Human manufacturing is excluded. The sample's exposure history shows it has traveled through space for an immense time. One grain becomes evidence of design. This would require exceptional verification. Laboratories would need independent samples. The chain of custody must be clear. Instruments could introduce contamination. Industrial material may enter collections accidentally. Meteorites have been confused with terrestrial slag and debris before. The more extraordinary the interpretation, the more carefully ordinary sources must be removed. A real artifact should survive scrutiny. Its artificial properties should become clearer with deeper analysis. Perhaps a listener has left no physical object. It may observe through the sun itself. The gravitational field of a star can bend light at extreme distances. Instruments positioned along a focal line could use this effect to magnify distant objects. Human scientists have studied the possibility of sending future spacecraft far beyond the planets to use the sun as a gravitational lens. A distant civilization might use its star similarly. It could construct receivers at great distances along the line toward Earth. Such instruments may produce little emission. They would observe from cold, dark regions and transmit their data back home through narrow beams. The actual listener may therefore sit far outside its own planetary system. Earth would have no simple way to know. A star that appears quiet could support observatories scattered across enormous distances. Its civilization's listening network may be much larger than the region occupied by planets. This broadens the idea of where someone might be: around a planet, on a moon, inside an asteroid, beyond the outermost worlds, along a gravitational focal line, or here, within our own system. A technological civilization can distribute its senses. The observer does not need one home. It may exist wherever measurements are best. Someone listening to Earth right now could therefore be a telescope without a city nearby, a probe without biological occupants, a machine continuing a mission from a vanished society, or an entire network combining observations across light years. Humanity does not know. The scientific record provides no confirmed listener, but it provides methods for searching. The silence near Earth can be examined differently from the silence between stars. A distant signal requires sensitivity. A local artifact requires completeness. How thoroughly has the region been mapped? How small an object could remain unseen? What heat would it release? What movements have no natural explanation? Which locations offer long-term stability? Current work treats these as quantitative questions, rather than claims that artifacts are present. Perhaps the answer has not arrived because no one is listening. Perhaps it has not arrived because listeners are too far away. Perhaps a reply is still moving through interstellar space. Or perhaps the listener arrived first. It crossed the darkness before humans learned to ask questions. It waited through ice ages, through changing coastlines, through the rise of cities. Then the first artificial radio waves reached it. The machine awakened. It began recording. For decades, it has heard Earth becoming louder, more complex, and more connected. It knows that one small planet now searches the sky. It may be deciding whether that planet is ready, or it may be nothing more than an idea created by a species uncomfortable with silence. No evidence tells us which. So telescopes continue looking outward, surveys continue looking nearby. The moon is mapped, asteroids are tracked, interstellar visitors are examined. Radio observations listen for narrow signals from both stars and moving objects. Each search reduces a little uncertainty. Every natural discovery clarifies what an artificial one would need to become. For now, the solar system appears to contain one known technological civilization. Its probes move among the planets. Its radio crosses the darkness. Its artifacts rest upon the Moon and Mars. Its machines are the only machines confirmed here. But the region remains larger than its exploration. There are quiet surfaces, dark orbits, cold objects that have never been visited. An answer could not be assumed to exist within them. It can only be searched for, and somewhere among the stars, or perhaps somewhere much closer, the question remains open. Is someone listening to Earth right now? The final part of this journey gathers every pathway together. Distant telescopes, transit geometry, radio leakage, deliberate messages, possible probes, travel time, and silence. It asks what present evidence truly allows humanity to say, not what imagination hopes, not what uncertainty can conceal, but what the universe has shown so far, and what one unmistakable discovery might look like when the silence finally changes. Earth is speaking, not with one voice, not with one message, not with one beam aimed evenly across the galaxy. It speaks through radar pulses, spacecraft commands, artificial satellites, atmospheric chemistry, city lights, industrial gases, and the changing movement of machines around the solar system. Some of these signals travel only a short distance before becoming too faint to recognize. Others form narrow beams capable of crossing many light years. Most point toward empty space. Some may pass near planets. A few may cross systems where sensitive instruments are operating. Whether anyone receives them remains unknown. Humanity has no confirmed evidence that another intelligence is listening to Earth right now. No verified extraterrestrial message has referred to our broadcasts. No distant transmitter has repeated one of our deliberate signals. No confirmed probe has been found waiting near the moon, among the asteroids, or beyond the outer planets. No observation has demonstrated that Earth has been identified as a technological world by another civilization. The scientific answer remains open. But open does not mean empty. It means the available evidence has not yet selected one possibility. Someone may be listening. No one may be close enough. A receiver may exist but face another part of the sky. Our strongest beam may have crossed its system while the instrument was inactive. A civilization may have detected Earth and chosen silence. A response may already be traveling. Or the galaxy around us may contain no other technological listener at this moment. Every possibility produces the same experience here. A quiet night. This is what makes cosmic silence difficult to interpret. Silence has many causes. A room can be silent because it is empty. It can also be silent because someone is listening. Interstellar space hides the difference. Humanity experiences only the absence of a confirmed reply. It cannot yet see the reason behind that absence. To understand what a listener might know, imagine Earth from the nearest stars. The planet would not appear as the familiar blue world seen in photographs from nearby spacecraft. It would lie beside the sun as one extremely faint source. Its oceans, clouds, continents, ice, forests, cities, and people would merge into a single point of changing light. A patient observer might measure the planet's orbit. It could determine that Earth circles the sun once each year. It may estimate the planet's size and mass. Changes in reflected light could reveal rotation. The atmosphere might show water vapor, oxygen, carbon dioxide, methane, ozone, and other molecules. The observer may infer that the planet possesses a complex atmosphere and active surface chemistry. It could suspect biology. Then artificial radio appears. A narrow signal rises from the same system. Its frequency shifts according to Earth's orbit. Its strength changes with the planet's rotation. Another signal appears from an object orbiting Earth. A third moves toward Mars. Several forms of evidence begin to connect. A rocky planet, a possible biosphere, a growing network of machines. A listener would not need to decode human language before reaching one remarkable conclusion. Something on Earth is organizing energy intentionally. This may be all the first detection reveals. No names, no faces, no knowledge of nations, families, art, history, or dreams, only technology. The distant observer may know that intelligence exists here without knowing what that intelligence is like. It might not know that humans built the transmitters. It may imagine one planetary mind, a network of machines, several technological species, or biological organisms working through artificial systems. The planet's broad signature cannot answer every question. Earth would become known in stages, first as a world, then as a living candidate, then as a technological candidate. Only communication could begin transforming the candidate into a civilization. The listener may attempt to understand our signals. This would not be simple. Human radio is not one language. Thousands of systems operate simultaneously. Analog broadcasts, digital communication, radar, navigation, telemetry, encrypted data, and spacecraft commands overlap. Signals begin and stop. Frequencies change. Some repeat. Others never return. To an unfamiliar receiver, the planet's electromagnetic environment might resemble structured confusion. Artificial, but difficult to read. A distant civilization may identify repeating elements, timing pulses, headers, error-correcting patterns, orbital rhythms. The same technical structures appear again and again. Through long observation, the listener could begin separating communication systems. One group of signals remains attached to Earth's surface. Another travels with satellites. A weaker group comes from distant spacecraft. Some beams point toward Mars, others toward asteroids or the outer planets. The listener reconstructs relationships before meanings. One machine speaks to another. One planet communicates with objects moving through its system. The exact words remain hidden. The geometry becomes visible. Perhaps language comes later. An extraordinarily capable receiver might recover fragments of older broadcasts, repeated sounds, images, human figures, music, voices. The listener may discover that the technological beings communicate through patterns of air pressure translated into radio waves. It might study human faces without understanding facial expression. It may hear laughter without knowing why it occurs. It could identify recurring individuals and places while misunderstanding their importance. A broadcast is not a complete culture, it is one selected performance of culture. Another civilization learning about Earth through transmitted media would receive an uneven portrait. Conflict may appear more common than ordinary cooperation because conflict attracts attention. Entertainment may appear to occupy most of human life because entertainment is transmitted frequently. Advertisements may seem like ritual instructions. Sport may look like organized symbolic competition of overwhelming importance. News may make the planet appear to exist in a permanent state of crisis. Quiet lives create weaker signals. A person reading beside a window does not brighten Earth significantly. A family sharing a meal may produce no distinct technosignature. A scientist writing a thought on paper leaves almost nothing visible between stars. The distant listener sees what technology amplifies. The softest parts of civilization remain hidden. This is also true when humanity studies another world. A radio beacon reveals engineering. It does not reveal kindness. An industrial atmosphere reveals chemical activity. It does not reveal whether the civilization values beauty. A Dyson-like structure would reveal extraordinary energy use. It would not reveal why the energy was collected. Technology can cross interstellar distance more easily than meaning. The first contact may therefore begin with a great imbalance. Both sides know that the other exists. Neither understands the other well. A signal could establish artificiality within minutes. Understanding a civilization may require generations. This should not make the search feel hopeless. Communication always begins with incomplete models. Two human beings can share a language and still misunderstand one another. Across stars, the first shared ideas may be very simple. Counting, repetition, symmetry, geometry, atomic physics, orbital motion. The sender and receiver inhabit different worlds, but the same universe. A hydrogen atom behaves according to the same physical rules near Earth and near another star. A prime number does not depend upon biology. A circle retains its mathematical relationships. The speed of light remains constant. These shared structures could form the first bridge. A deliberate signal might begin with pulses arranged into numbers. It could repeat the sequence, then introduce addition, ratios, dimensions, a reference frequency based upon hydrogen, a unit of time, a map of a planetary system. The receiver learns the message's grammar through the message itself. No shared alphabet is required. The sender begins with nature. A reply could follow the same path. Humanity receives a pattern. It recognizes the rule. It repeats the pattern and adds one more step. The first exchange says almost nothing about either civilization's daily life, yet it establishes something more important: recognition. One mind has noticed another. From there, information could grow. The sender describes its star, the number of planets, the period of its world, the gases in its atmosphere. Human telescopes test the claims. A planet is found where the message predicted. Its year matches. Its atmosphere contains the stated molecules. The signal becomes connected to a real system. Trust begins through measurement. Humanity could respond with the structure of the solar system, the size of Earth, the properties of the moon, the chemistry of life, images encoded through mathematical grids, descriptions of the species sending the message. Each side would still interpret the other through unfamiliar assumptions, but shared astronomy provides a foundation. This possibility depends upon someone transmitting. A galaxy filled only with listeners remains silent. Every civilization waits for evidence. No civilization creates evidence deliberately. Each one concludes that no one else is there. Humanity partly avoids this problem through accidental leakage. Radar and communication escape whether or not the planet intends to announce itself. Another technological world may do the same. Two listening civilizations could discover one another through ordinary infrastructure. The first contact may begin not because either side constructed an interstellar beacon, but because one beam intended for an asteroid crossed a distant telescope. A practical action becomes a cosmic introduction. If someone has detected such a beam from Earth, what might happen next? The listener may return to the sun. It observes again. Most sessions reveal nothing. The first signal becomes a candidate rather than a discovery. Years later, another beam appears. The signal follows Earth's orbit, confidence increases. The observer studies the planet's atmosphere. Possible biological signs appear. A third radio event arrives. Now the system contains several connected technosignatures. The listener may confirm Earth as technological. It might still wait. Perhaps its scientific standards require more evidence. Perhaps transmitting requires large amounts of energy. Perhaps the decision involves many groups. Perhaps it has rules concerning young civilizations. Or perhaps the observing system is automated and has no transmitter. The receiver records Earth but cannot answer. Someone may be listening without possessing the ability to speak across the same distance. A civilization can build a telescope before it builds a powerful interstellar beacon. Humanity has already reached that stage. We can search stars more easily than we can communicate richly with them. Another observer may be similar. It hears Earth faintly. Its instruments confirm technology, but its transmitters cannot produce a signal strong enough for human telescopes. The listener exists. The silence continues. This reminds us that contact requires two compatible technologies. One side must produce a detectable signal. The other must possess a suitable receiver. Then the process must reverse. Both directions need not be equally easy. A civilization living around a quiet nearby star may hear powerful human radar, yet its own communication systems may be weak or tightly local. It may know about Earth without being able to announce itself. Distance creates another delay. Suppose a civilization lies 20 light-years away. A radar signal leaving Earth requires 20 years to reach it. The listener studies the signal for 5 years. It sends a reply. Another 20 years pass. 45 years separate the original transmission from the response. The act of listening began decades before humanity learned that anyone was there. At 100 light-years, the same process can span more than 2 centuries. A response triggered by Earth's earliest radio age could arrive in the future rather than the present. No mystery is required, only distance. The galaxy does not permit immediate confirmation. A message can be real and still remain beyond the horizon of one lifetime. This creates a strange possibility. Some answers may already have begun. A transmitter around another star may be active at this moment. The signal could be crossing the space between systems. It has not reached Earth. No telescope can detect it yet, because the wavefront is still elsewhere. The silence here is physically real. The answer there is physically real. Both conditions exist at the same time. Human language struggles with this because the word now feels universal. Relativity and light travel make distant events inaccessible until their information arrives. A civilization could be celebrating the discovery of Earth. Humanity would not know for decades. From our perspective, nothing has happened. From theirs, contact has already begun. The reverse may also be true. Earth has sent deliberate messages. A receiver may not encounter them for centuries or thousands of years. Humanity considers the message old. For the recipient, it is new. The sender's world may have changed beyond recognition by the time the signal is opened. Interstellar communication turns every message into a time capsule. The listener receives a civilization's past. It replies to that past. The response reaches a future. A conversation between stars is also a conversation between eras. This may influence what a careful civilization sends. Temporary political information may be less useful. Scientific knowledge may endure longer. Descriptions of biology and history may remain valuable even if the society changes. The message could acknowledge the delay directly. It may say, "The civilization described here existed when this transmission began. We cannot know what we will be when you receive it." The receiver would understand that the voice belongs partly to history. A local probe could remove much of this delay. If another civilization placed a listening machine inside the solar system, it could detect Earth almost immediately. The probe might have waited through millions of quiet years. Then artificial radio appeared. The world it had monitored became technological. The machine could begin transmitting toward Earth. A response might arrive in seconds, minutes, or hours. Humanity would know that the listener was nearby. Direction and timing would reveal the distance. A message returning too quickly to come from another star would transform the search completely. Astronomers would track the source. A faint object might be found. The question would move from communication to encounter. No such verified event has occurred. The known technological objects within the solar system were made by humans. Our probes, satellites, landers, rovers, discarded stages, and debris form the only confirmed artificial population beyond Earth. Yet the search remains incomplete. Small objects can hide in vast regions. The Moon has not been inspected at every scale. Most asteroids have never received close spacecraft visits. The distant solar system contains bodies that remain undiscovered. An inactive artifact may emit no signal and little heat. Nothing in current observations proves that such an object exists. Nothing justifies treating an unknown rock as a machine. A specific candidate would need artificial properties, controlled motion, structured transmission, manufactured materials, repeated geometry, internal organization. A mystery alone would not be enough. This principle applies across the entire search. Unexplained is not the same as extraterrestrial. A signal can remain unidentified because the data are incomplete. An object can accelerate unusually because a natural process is unfamiliar. A star can dim irregularly because dust is arranged strangely. A planet can contain an unexpected molecule because atmospheric chemistry is not fully understood. Another intelligence becomes the strongest explanation only when evidence supports technology positively, not when all ordinary explanations merely feel incomplete. What would positive evidence look like? Imagine a radio signal detected by several observatories around Earth. It comes from the direction of one nearby star. Its frequency is extremely narrow. It drifts according to the motion of a known planet. When telescopes move away from the star, the signal disappears. When they return, it reappears. Independent instruments detect the same sequence. The signal repeats prime numbers. Then it announces the time of its next appearance. The prediction is correct. No satellite, radar, instrument, or natural source explains it. The pattern continues. Each new observation becomes more difficult to dismiss. This would differ fundamentally from a one-time anomaly. It would allow testing, prediction, confirmation. A natural event can surprise. A deliberate signal can establish a relationship. Optical evidence could strengthen the case. A laser pulse arrives from the same planet at the exact moment predicted by the radio message. The wavelength follows a mathematical relationship with the radio frequency. The planet's atmosphere contains unusual compounds consistent with technology. Several independent lines of evidence converge. The system does not merely remain unexplained. It behaves coherently. Or imagine a nearby object. Its orbit changes deliberately. A narrow transmission comes from it. Radar reveals a symmetrical hollow structure. Spectroscopy finds layered materials manufactured beyond plausible geological processes. A spacecraft approaches. The object responds to a mathematical signal. The evidence would not rest upon one strange image. Every measurement would point toward design. A real discovery should become clearer as observations improve. False candidates usually separate into ordinary pieces. One signal comes from interference. One infrared glow comes from a background galaxy. One dimming event comes from dust. One acceleration comes from gas escaping an object. A genuine technosignature should remain connected. Its motion, energy, structure, and information belong to one technological system. The deeper the investigation becomes, the more organized the explanation appears. This standard is demanding. It needs to be. The conclusion would reshape science, philosophy, and humanity's understanding of its place in nature. The evidence must be strong enough to survive excitement, criticism, new instruments, and time. A discovery announced quickly but overturned later would create confusion. A real signal can wait for careful study. It can repeat. It can be observed independently. A nearby artifact can be measured again. Confidence grows through patience. Perhaps this patience is one reason contact has not yet been confirmed. Humanity's search has been brief. The radio age occupies little more than a century. Organized SETI covers an even smaller portion. Many stars have received only limited observation. Some were watched for minutes. A transmitter operating once every year could be missed. A beam sweeping across Earth every century could pass between generations of instruments. A signal may use frequencies not examined. It could be too weak, too short, too broad, too narrow, too unusual for current algorithms. The search space is vast. Direction, frequency, time, bandwidth, pulse duration, polarization, modulation, repetition, signal strength, transmitter motion, receiver sensitivity. Every dimension multiplies the possibilities. Humanity has sampled only a small fraction. A lack of confirmed detection is meaningful within the regions already examined. It is not a complete survey of every possible intelligence. The same would be true for a listener studying Earth. Our planet may be easy to detect through one technosignature and almost invisible through another. Powerful radar could be clear inside one narrow beam. Mobile leakage becomes faint quickly. Atmospheric biology is continuous, but requires sensitive spectroscopy. City lights are weak, satellites are tiny. A distant observer may listen for the wrong sign. It could possess advanced optical astronomy, but little radio sensitivity. It knows Earth is living. It does not know Earth is technological. Another civilization may hear radar, but lack instruments capable of studying our atmosphere. It knows a machine exists near the sun. It does not know the machine belongs to a living planet. Knowledge depends upon method. This creates many partial discoveries across the galaxy. One listener sees oxygen, another receives a pulse, another detects spacecraft communication. None possesses the full picture. Only a civilization combining several instruments may recognize Earth confidently. Perhaps the strongest listener is not one telescope. It is a network. Radio arrays distributed across moons. Optical telescopes in space. Infrared observatories in cold, distant orbits. Automated systems combining centuries of data. The civilization's entire planetary system acts as one observatory. Earth enters the network first as a small candidate. Over time, different instruments add evidence. The network eventually concludes that technology exists here. Such a system would be capable of listening without revealing itself. Its receivers are passive. Their transmissions back home may use narrow beams that never cross Earth. The observer could remain invisible indefinitely. This possibility cannot be confirmed from silence. A hidden listener and an absent listener create the same result. Scientific progress requires something measurable. A signal, a response, a structure, a pattern. Until one appears, the listener remains hypothetical. The emotional question may feel more immediate than the evidence allows. Is someone watching? Does someone know? Has Earth already been discovered? These questions place humanity inside another mind. They ask us to imagine becoming the distant world. For most of history, humans looked upward and treated the stars as lights. Modern astronomy revealed that many are suns. Planet searches revealed worlds around them. Atmospheric studies are beginning to reveal the chemistry of those worlds. SETI asks whether some of those systems contain observers capable of looking back. The symmetry is natural. If humanity can imagine searching, another intelligence could do the same. Yet symmetry does not establish existence. Only evidence can do that. The safest conclusion is therefore simple. Earth can be detectable under certain conditions. Its strongest technologies reach interstellar space. Some nearby systems have already been crossed by human emissions. Observers in favorable geometries could discover the planet through transits or other methods. A sufficiently capable civilization could connect radioactivity with a rocky, biologically interesting world. But humanity does not know whether such a civilization occupies any of those systems. It does not know whether its instruments are listening. It does not know whether a response has been sent. The question remains open. This openness can be held without fear. A listener does not imply danger. Humanity listens to exoplanets because knowledge matters. Another civilization may be equally curious. It may study Earth as one distant natural system. It could observe without interfering. It may understand only broad planetary properties. The idea of being listened to can feel less like surveillance and more like astronomy. From another star, Earth is not one private room. It is one faint point beside the sun. No individual life can be separated easily. The listener may know that minds exist here. It does not know every thought. Humanity becomes visible as a whole. One living world producing artificial patterns. There is something quietly beautiful in this possibility. Every radar pulse leaves the planet carrying evidence that intelligence emerged here. Every spacecraft command shows that life began reaching beyond its world. Every deliberate message says that human beings imagined another mind before finding one. The signals may fade, they may cross empty systems, they may never be detected, but they still become part of the galaxy's physical history. Earth is no longer entirely quiet. A technological layer is expanding outward. The layer is thin, uneven, faint, but real. Within it travel the traces of one young civilization. Measurements, images, voices, encoded instructions, the pulses of machines, fragments of music, Most will dissolve into noise at great distance. A powerful receiver may preserve something. A listener could record a small portion. Perhaps one signal becomes the first evidence of Earth inside another world's science. The distant researchers may give the Sun a catalog number. They may refer to Earth through coordinates rather than a name. A paper could describe a candidate narrowband source associated with the third planet. The conclusion might remain cautious. Possible technological emission. Further observation required. More telescope time is scheduled. Earth becomes someone else's mystery. The thought reverses every human SETI story. Perhaps our planet is their wow signal, their unexplained candidate, their faint line from a nearby star, their reason to keep listening. If so, the observer may still be uncertain. It may have detected only one beam. It needs repetition. Humanity continues transmitting without knowing that another civilization is waiting for confirmation. One day, another radar pulse crosses the same system. The candidate returns. Its motion follows Earth. The probability changes. The observer reaches certainty. No celebration is visible here. No message arrives immediately. Only a conclusion inside a distant observatory. They are not alone. Years later, perhaps a transmitter turns toward the Sun. The response begins crossing the darkness. Until it arrives, Earth remains beneath the same stars. People continue asking the same question. The answer exists, but not here yet. Or perhaps the signals reach no receiver. They cross planets without life. They pass stars with no observers. The galaxy remains quiet because technological intelligence is extraordinarily rare. Earth may be the only listening world within a vast region. This possibility gives the question a different emotional shape. If no one is listening, then the act of listening here becomes more precious. The universe contains at least one planet where matter has learned to wonder about distant minds. At least one world has built instruments for questions larger than survival. At least one species sends greetings towards stars it may never reach. Whether Earth is observed or alone, the ability to ask remains extraordinary. If listeners are common, humanity belongs to a wider community, not yet connected. If listeners are rare, this world carries an unusual responsibility. Its life, knowledge, memory, and curiosity may be exceptionally precious. Both possibilities lead back to Earth. The oceans that support life, the atmosphere that holds warmth, the organisms that transformed the air, the minds that learned to measure stars, the antennas that turn beneath the night. The question of distant listeners does not make this planet smaller. It makes its achievement clearer. For billions of years, Earth existed without radio. Then one species learned that invisible waves could carry information. It built receivers. It discovered pulsars, galaxies, and the afterglow of the early universe. It began searching for technology around other stars, and at the same time, its own signals began traveling outward. The observer became observable. The listener became a possible voice in someone else's sky. Perhaps this is the natural beginning of contact. Not one dramatic arrival. Two planets developing astronomy. Two civilizations learning to recognize artificial patterns. Each searching, each transmitting accidentally, each separated by years of light travel. Their instruments approach one another before their cultures do. The first bridge is formed by measurement. A signal crosses. A receiver notices. Then one day, the signal returns. Until then, the work continues. Radio telescopes monitor nearby stars. Optical observatories watch for brief laser pulses. Exoplanet researchers study atmospheres. Infrared surveys search for unusual heat. Planetary scientists examine interstellar visitors. Archives are searched with new algorithms. The solar system is mapped more completely. Every method asks a different version of the same question. Is technology present beyond Earth? The answer may come from very far away. It may come from nearby. It may appear as a message, a chemical spectrum, a changing orbit, a manufactured fragment, or a repeating mathematical line within radio noise. No one knows which instrument will encounter it first. Perhaps the discovery is still centuries away. Perhaps the signal is already inside existing data. Perhaps a listener is studying Earth tonight. The uncertainty can remain gentle. It does not need to be filled with certainty before evidence arrives. Wonder is allowed to remain open. The universe is larger than the questions already answered. The sky can hold possibilities without turning them into conclusions. For now, Earth listens. It turns beneath clouds and moonlight. The radio dishes move slowly. Computers examine narrow channels. Most contain noise. Some contain stars. Some contain human interference. Occasionally, one pattern earns a second look, then another. The method becomes more careful with every candidate. Humanity is learning what a real answer would need to survive. Repetition, direction, independent confirmation, coherent motion, information, a pattern that becomes more artificial as more evidence arrives. Perhaps another civilization is learning the same lesson through us. It records one terrestrial signal, then waits. Both worlds may be practicing for one another without knowing it. And somewhere between them, the light continues traveling. The distance remains enormous. But distance is not emptiness. It is space filled with information that has not arrived yet. As this final part settles, allow the question to become softer. There is no need to solve it tonight. The stars will continue moving. Earth's signals will continue traveling. Telescopes will continue gathering faint light from distant worlds. Perhaps one future observation will change everything. For now, the night remains quiet. Let that quiet feel spacious rather than lonely. Earth is here beneath you, a warm planet turning through darkness, its oceans moving under moonlight, its atmosphere glowing faintly above the horizon, its cities slowly passing from evening into morning. Across the surface, countless people are sleeping. Others are working. Some are watching the sky. Some are sending signals toward machines far beyond Earth. Every life belongs to the same small world. From another star, all of humanity becomes one point of light, one planetary rhythm, one faint technological voice. Perhaps someone has noticed it, perhaps not yet. Either way, the voice exists. It moves outward, and this world continues listening in return. Nightfall Science will continue exploring the quiet mysteries of space, life, time, and the universe. For now, let your breathing become slow. Let the distant stars blur into the darkness. Let every radio signal travel beyond thought. There is nothing you need to follow, nothing you need to answer. The question can remain among the stars until another night. Earth continues turning safely beneath its atmosphere. The universe continues unfolding beyond it. And somewhere, perhaps, another quiet world may be listening too. Sleep well, and good night.